See, in this chapter, basically, the first time we are starting off with magnetism after electrostatics, and everybody must have played with magnets at some point or the other in your life. So, this concept of magnetism, or these miraculous materials attracting each other, was actually known a long time back, right? Almost 2000 years, right? And it was only 200 years ago, which is just in probably 1820, that it was realized that electricity and magnetism are actually related, and there are many scientists who are actually involved in this. See, we know gravitational force, we know nuclear force, we know electric force, we know magnetic force. So these are like our fundamental forces in nature. People then realize that actually electric force and magnetic force are the different avatars of the same thing. Like maybe I dress up like a Santa Claus, I will behave like a Santa Claus. Maybe I dress up like a proper, school going kid, and probably I act in a movie. Probably you will be like, sir, you're acting so well, sir, as a school kid. I dress up like a teacher, I'll be like, yeah, fine, I'm a teacher now. So same way, electromagnetism, they are basically the same thing. They just dress up differently, they act differently, and sometimes you find them to show electric forces, and then you see them showing magnetic forces. So they are just manifestations in different forms. Okay, so electromagnetism are interlinked with each other, and the person who demonstrated that was none other than Ørsted. Ørsted was that guy who related first time experimentally that actually that electricity and magnetism are basically they are related to each other. They are basically related to each other. It's like sometime you meet somebody somewhere. Oh, you're from that city. Oh, I am also from that city. Oh, you know that person? Yes. How are you related? He's my uncle. Oh, you know what? He is my grandfather's brother, something like that. Oh, we two are related. So like that, they found out that they are related to each other. They are interlinked, and it was demonstrated by Ørsted. And what did he do? We'll come to that in a bit. If there is an experiment which is mentioned here, and he's all those observations which he noted are mentioned over here. The first thing which he says that the magnetic needle gets deflected when there is a current passing, and the deflection is more when you are close to the wire, and it is less when you are far away, and the deflection increases when you increase the current, and it reverses on basically reversing the current. So basically Ørsted was the guy who concluded that moving charges or currents produce a magnetic field surrounding the space. Okay, so let me tell you what exactly he did. So this is your, oops, what just happened? Oops. Okay, yeah. So Ørsted, what he did was, imagine you take a wire which carries some current. This is a wire which basically carries some current. He took a magnetic needle. He knew that there are some materials which basically deflect when you place it near another magnet, or because of the Earth's magnetic field, they start aligning themselves like your magnetic compass. He saw that this particular magnetic needle, it got deflected, basically deflected when it was placed near a current carrying wire. Now what is current? Flow of charges, meaning motion of charges. So that's why he thought when charges move in a wire, when motion of charges occur, then there must be some magnetic effect which is happening, because of which this magnetic needle got deflected. Otherwise, if there was no current, this needle did not deflect. So hence he concluded that moving charges or current produce a magnetic field in the surrounding space. Then what he says is that so these are the conclusions, if current is zero, then the deflection is basically zero. If current is present, then deflection is also present. Also, next thing he says, if current is increased, then he sees that the deflection also increases. Then he also sees if distance is increased, then he saw the deflection reduced. And finally, if current is reversed, then even the deflection is reversed. If it was deflecting this way, then it will deflect the other way. These were the observations which are mentioned in this particular paragraph. These were basically the observations. All these are basically the observations which is explained in the next slide, right over here. All these are the observations. It is written down in a very boring paragraph manner, but if you look at it like this, then it makes sense. So from this, what is the feeling that you get? The feeling that you get is, if you are close enough to the wire, there is stronger magnetic field. If you are far away from the wire, there is lesser magnetic field. Field is something where you can feel the aura, you can feel the effect, you can sense that there is something. Like some teachers, when they enter the class, they generate a positive field, motivating field, a learning field around them. The closer you are, you might want to sit on the front bench because the teacher is very interesting. But when the aura is very negative, you might be like, okay, I can sit at the back bench. So same way, guys, the closer you are, the stronger the aura or the presence which is felt by the magnetic substances. So the distance reduces, the aura increases, the current increases, the field increases. There is no current, then there is no deflection. If the current is reversed, then the magnetic field reverses the direction, and that's why the deflection also reverses. All right, Hayatluru Krishna, very good. Nice to see you back. Is this point absolutely clear till this point? Everybody with me on this? What Oersted saw? So from this, he was able to talk about something called as magnetic field and all of that. We'll come to that in a bit. Then they are mentioning about all the scientists. This is okay. In this chapter, we'll see how magnetic field exerts forces on charged particles, etc. We'll also learn how currents produce magnetic field. We shall see. It's talking about what we will see in this chapter. That's okay. On magnetic, we adopt the following convention: a current in the field emerging out, and okay, all these are fine. And basically, this diagram is very, very important. I'll explain you this diagram in these terms. See, if you look at the top view, if you look at it from the top view, meaning like from here, if you see, you will see the current coming towards you. That means I will show the current like this. A current coming towards you will be shown like a dot. This is out of the plane of the particular figure. Similarly, if somebody sees from below, that person will see the current going away. So it will be shown like a cross. It is in the plane of the figure. In the plane of the figure. This is your standard convention which you have learned even in vectors. A vector coming towards you is a dot. A vector going away from you on the paper is shown as a cross. It's like an arrow which is coming towards you or going away from you. So say for example, you are seeing like this, and it so happens that the current happens to come towards you. Then it is found that the deflection comes in such a way, or if you sprinkle some iron fillings are very magnetic in nature, they can get magnetized. Those iron fillings align themselves in a very peculiar manner, and that looks something like this. these iron fillings, they orient themselves like this. So you can see they are aligned themselves in circular manner, and you will see that their concentration is more when you are close. As you go far away, you will see there will be very few iron fillings which will tend to align as circular loops. So it is basically saying that there is a very strong magnetic field over here, and here the magnetic field is basically weak. So this is how they orient. If you reverse the current, if they were aligned like this, now they will be starting to align exactly opposite. I mean, they will look the same. It's just that they will flip. The north pole will become the south pole. The south pole of the iron fillings will then become the north pole. These iron fillings will flip their directions, and you will still see that they are circular. So it confirms with the observations whatever he saw, and he was able to then relate that electricity is related to magnetism. Magnetism is related to electricity. So the interlinking happened by experimental demonstration. I hope this is clear. And that is exactly what has been mentioned over here, that dot cross. Here they just tell what we are going to study, what we are going to study, what we are going to study. Okay, fine. There is nothing that we can underline over here. Main thing here, how do the magnetic field lines look like, iron fillings look like, that is something which I have already shown over here. Alright. Now, see, I will explain you in a very simple manner. When you have a stationary charge, then what happens? The stationary charge might create your electric field. It will create your electric field, and this electric field, when it passes through another charge, then that charge experiences a force. That force is given by charge which you have kept over here, into the electric field which is generated by this particular charge. This particular thing we have seen even before in the previous chapter of electrostatics. I hope you remember. Force is charge multiplied by field. But if you have a current carrying wire, then it is basically now creating a magnetic field around it. It is basically creating magnetic field around it. Obviously a magnetic field can affect any of these two things. What are those two things? First, it can affect other magnets. It can basically affect. When I say affect, that means it can apply a force. On other magnets. Example, let's say you have a bar magnet with north and south pole, or for example a horseshoe magnet with some north pole and south pole, and so many more. So it can apply forces on other magnets. You place a bar magnet, it will be deflecting. You place a horseshoe magnet, it might attract, repel, it might apply a torque, something will happen. This is one thing on which it can apply a force. The other thing which it can affect is basically moving charges, or basically currents. Current is also charges under motion, so moving charges or current. So in this particular chapter, mainly we focus our attention on this. In the next chapter, you basically study this, but mainly in this chapter we study the how the magnetic field affects the motion of charges or currents. Is this absolutely clear, my dear warriors? Everyone, let me know. Yes, Krishna, QE. Yes, Madhumati. Thank you so much, Atluru. Please suggest me some tests weekly chapter wise for improvements in the comment section. Definitely, Suchi Mama. I read your comment that you have taken some admission and you'll be following the classes here and time to time guidance you'll be seeking. Definitely, Suchi Mama. Why not? You have been my long-term student. I'll definitely be mentoring you. You can definitely leave a comment. Okay? Yes. All right. So, this is what we'll be studying. This is later on. That is what they have in fact told also. We shall see how magnetic field exerts forces on moving charged particles or current carrying wires. See this? This is exactly what they have told. In this chapter, we'll be studying how magnetic field exerts forces on moving charged particles or current producing magnetic fields. Okay? This is what we are going to study. Anyways, now in the starting part, they remind you of the previous chapters, like how electric field is produced. We have seen this. Electric field is kq by r square due to a point charge, and the force is field into the charge. All these things are reminders or revision of the previous chapters. We have seen this. Due to a point charge, if you measure what is the electric field, it will be kq divided by basically r square. And that same field will apply a force which is given by charge into field, which is exactly what I have told you over here. And this electric field due to a point charge is kq divided by r square. But if you write it vector wise, it will be r hat. This is just a unit vector, nothing great about it. Just to represent the direction. That's all. That is exactly what they have also written over here. No point writing the same thing. Now this was for electric field, but the problem is for magnetic field. How the magnetic field will apply a force? The force by electric field is given by QE. Okay, the force by electric field is given by QE and the field value is given by this. How will magnetic field apply a force is what we are interested in. So, there were a lot of experiments which were performed. So, this is exactly like a introduction or warm up, you can say, before they actually come to the formula or the final theory. They found out experimentally that it obeys all the fundamental laws like superposition, and the direction of the magnetic field is magnetic force is slightly weird. It's not as simple as the force of electric field. And they found out experimentally, before going ahead, I'll show to you over here. If you take a charge and move it with some velocity like this, and let's say there is magnetic field around it. Now, magnetic field, you might be wondering, sir, what is the unit, what is the symbol, etc. So, see, my dear students, magnetic field, okay, has the symbol of basically B. This is basically your symbol, of course. Okay, this is basically your symbol. It is a vector quantity. And the unit is basically Tesla. The short form is T. There is also another unit which is called as Gauss, and a Gauss is 10 to the power -4 Tesla. This magnetic field follows all those other properties which electric field obeyed. For example, you will see that if a magnetic field line is like this, then if somebody happens to draw a tangent to this at any given point, if somebody draws a tangent to it, then the direction in which the field is going along the tangent, that gives you exactly the direction of the magnetic field. They use the symbol B, not E, please mind it. Also, you will find that if you take two magnetic field lines, this cannot happen. They can't intersect, just like electric fields. They can't definitely intersect. This is not at all allowed. Similarly, if the magnetic field lines go like this, here the magnetic field is definitely very, very strong because they are crowded. Whereas if you go over here, they are very, very far away. So the field is basically weak. So the strength is decided by how closely they are packed or how far they are. And by chance the magnetic field lines are just parallel lines, then such a thing is just called as uniform field, as uniform magnetic field. There is one small difference though. There is one small difference though. Tamil movies, I will definitely continue this series, but I'm seeing that the motivation is going down day by day for many students. They are losing track. If you lose track and if you don't attend the series, then I will be like, okay, you guys don't want it. You guys again want some chapter 1 only. Again, fine, I'll start with some chapter 1. But if you continue watching, and how will that happen? See, you might be sincere, but you have to motivate your people around you. See what happens in many channels, especially these Hindi channels, these students form groups. They tell, listen, this teacher is teaching. He's teaching for us for free. And you know, every student is attending the classes. But the same thing when we do for our students, especially our South Indian students, students from Northeast and even students abroad, you too have to have that same feeling because nobody else is doing. And we can also say nobody is doing, okay, chill, we will also not do. But no, we want to be a revolution. We want to make sure our students succeed. We want to make sure our students get ranks at national level. As simple as that. So guys, please make sure that every student around you is motivated and watching all these classes. Every student around you should be subscribed to the channel and watching all the lectures. It's for free. What am I asking? Just watch the lectures, download the PDFs properly, be sincere, give the tests, whatever we are doing, just do it on YouTube also. You might be a part of some coaching, that's okay. But continue. All right. There is one thing which is different. There is one thing which is different, which is not there in electric field, and that is you will never see a magnetic field start and end somewhere. You will always see the magnetic field line wherever it started, it will end at the same point, meaning there is no start or no end. You can take anything as a starting or the ending point. So magnetic field lines, you will see they are always in the form of closed loops. That is very different. So they don't, what do they don't? They don't start, basically, they don't originate or terminate. They don't originate or basically terminate. That is a very different thing fundamentally as compared to electrostatics. Okay, because you cannot truly figure out the north pole or the south pole of a magnet. You might be wondering, sir, how? I mean, I thought the magnetic field lines start from a north pole and they end on a south pole. Yeah, that is what you thought until school or probably before this lecture. If this is north pole, this is south pole, I'm pretty sure you thought that, okay, sir, magnetic field lines originate here and they terminate here, just like an electrical dipole. But actually, it is not so. They continue even inside like this. These lines continue even inside like this. If you compare it with electrostatic charges, a positive charge and a negative charge, the different story over here is, here also the field lines go like this. They start from positive, go on to negative like this. But remember, they don't continue like this. Rather, from the positive only, they go like this towards the negative. So you can see inside this dipole, it's still going from positive to negative, but inside the bar magnet, it goes from negative to positive, that is south pole to north pole. South pole is considered as the negative magnetic charge. North pole is considered as the positive charge of magnetism. Not in coulombs, but in magnetism. Getting my point? So you can see they are same, but different. Same, but different. Right? Is that right, everyone? Same, but slightly different. So very, very important, they do not start or originate anywhere. It's always in the form of closed loop. Unit is Tesla, it's a vector quantity, and they don't intersect. It can be strong when they are close, and if they are parallel, it's basically a uniform field. So coming back, if a charge is in motion and then I tell you, listen, that there is a magnetic field over here acting like this. It's a vector quantity. Then the force acting on it happens to be something like this. But you have to visualize this in 3 dimension, my dear students. It's not only perpendicular to the magnetic field, but it is also perpendicular to the velocity. Very, very interesting. It's perpendicular to the velocity. It's also perpendicular to the magnetic field. This is the magnetic force acting on it. Very, very interesting. Usually, in our head, it is like wherever is the field, that's where the force is and all that. But that was in electrostatics. Force is in the direction of the field. But here, the force is in perpendicular direction of the field. Field is here, force is perpendicular to that. You have to visualize this in 3 dimensions, my dear warriors. This is something like in 3 dimensions, which you will have to visualize. Imagine a plane, that gray plane contains B and V. Perpendicular to that is the force. If velocity is here, magnetic field is here, force is perpendicular to this particular plane. It's like this. And the value of this force, the value of this particular force comes out to be charge into velocity cross producted with the magnetic field. Cross producted with the magnetic field. So it involves a cross product. That is something which you need to be very, very careful about. So this is the magnetic force, magnetic field, magnetic field's force on a moving charge, on a moving charge. Is that clear? That is the magnetic field's force on a charge which is moving. You will see some special conditions over here. One of the first special condition will be, say for example, if it is at rest, if the charge is basically at rest, that means what will happen? The velocity will be 0. You will immediately see that the force acting will also be 0, because 0 into any number will be 0. Makes sense. 0 into any number is basically 0. Not just that, just imagine this, the second special case. Say for example, velocity is parallel to the magnetic field, or it is basically velocity is anti-parallel to the magnetic field. This is also another case. In such conditions, what will happen? Theta will be 0 degree or theta will be 180 degree. V cross B will be VB sine theta. That theta will be 0 parallel, anti-parallel is 180. So in either of the two cases, the sine angle will be 0. Sine 0 is 0, sine 180 is also 0. So that also means that the force will be 0. So if by chance you see the charged particle going like this or like this, this is your charged particle going either parallel to the field or anti-parallel to the field, nothing will happen to the charge. It will continue its journey. There will be no force acting on it. This is what this formula also tells, and experiments also that were conducted followed these same things. Is this clear, my dear warriors, till this point? Everyone fine till this point? Another interesting thing which happens over here is this. Since force is perpendicular to the velocity, velocity is in the direction of displacement. If it is displacing here, velocity is here, force is perpendicular to that. Force, when it is perpendicular to the displacement, what will be the work done by it? What will be the work done by such a force? Put it up in the chat box. Force into displacement, but with cos theta is the work. Cos 90, guys, is 0. So the work done, therefore, the work done by it is nothing but 0. Yes, it will not do any work. And if it doesn't do any work, what does it mean? It can't change, it can't change its kinetic energy. Remember work kinetic energy theorem? Work changes the kinetic energy. W is equal to delta K. If no work, no change in its kinetic energy, which means the speed can't change. The speed can't change. So such a force acting on a particle, don't think this vector of velocity will become long or small. It can never change it, but that force can change the direction of it. So very, very important, but it can change, the direction of the motion. It can change the direction of the motion. Very, very important thing. It can't change, the speed, but what can it change? Very, very important. It can change the direction. Very crucial, important conceptual points that you are learning over here. Very good. Excellent. That is also what is explained over here, but there is something more to it which will be coming in a bit. Now, imagine there is a charge and it is, let's say, moving like this. So, there is a magnetic field which is acting, and apart from that, there is one more field, and that is, let's say, your electric field which is acting. So many fields are there. Electric field is also there, magnetic field is also there. Let's think one by one what will happen. Because of this magnetic field, if you do V cross B, if you basically do velocity cross B, V was here, cross B will give me the force. So V cross B gives me the force of magnetism. So the force of magnetism due to the magnetic field will be like this. And of course, it will be perpendicular to this also and this also. At the same time, do not forget this electric field will also apply a force on this charge, and maybe that force happens to be like this, and that force will be the electric field force. Both the forces are acting together. Together, when they act, they will superimpose and they will produce the net force. So if I use parallelogram law or triangle law or whatever vector addition law, I will be able to create the net force acting on it. This is using superposition. So by superpositioning, the net force acting on it will be F. The net force acting on it will be F, and it will be the force of magnetic field plus the force of electric field. How much is the force of magnetic field? We just saw it. It is charge into velocity cross producted with the magnetic field, and at the same time, what is the force by the electric field? It is plus QE. Q is the charge, E is nothing but the electric field. That is your total force. This type of combination of forces by superpositioning to find net force of magnetic and electric, this is also called as the Lorentz force. This is also called as the Lorentz force. Very, very important, guys. And this is exactly what has been written down over here. If you notice, this is exactly that same statement. Is that clear? And they have told that we can also superimpose and all of that, if you notice over here. So they have mentioned this. They have mentioned this right over here. It is found to obey the principles of superpositioning. The magnetic field of several sources in the vector addition of the magnetic field of each, blah, 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 blah. Okay. And then they tell over here, if there is a point charge moving with some velocity located at some distance in the presence of magnetic field, the force which it will experience is this. This was given by Lorentz, hence it is called as the Lorentz force. Okay. And like you said, see over here, it obviously depends on the charge, velocity, magnetic field, as well as the electric field. Okay. So these are the basic things which it depends on. Now they have also given you the conditions when the force is 0. I have already given you these conditions in this particular part, right over here. If the force is 0, either the charge is 0 or the vectors are parallel or anti-parallel. That's the same thing which they have given in these pointers over here, if you notice. Okay, so you can see that if they are basically, if the velocity and the magnetic field are parallel or anti-parallel, then the force becomes 0. Okay, I hope this is clear. The magnetic force is also 0. The magnetic force is also 0 if it is charge is not moving. That means the velocity is 0. All these points they have mentioned exactly the same way. All right. I hope this is clear. All right. And they have also specified the unit of Tesla right over here. Okay, SI unit is Tesla, the Gauss unit is 10 to the power minus 4 Tesla. And the Earth's magnetic field, just remember this value, is very, very small. Just look at this. Just look at this. It's in the range of 10 to the power minus 5 Tesla. 10 to the power negative 5 Tesla. That's how small Earth's magnetic field is. That's how small Earth's magnetic field is. If you are wondering how Tesla was defined, it was actually defined by this formula. I know the unit of charge, it is Coulomb. I know the unit of velocity, that is meter per second. So, force is in Newton, so magnetic field can be easily defined. How? Just go back over here, where did the field thing go? Yeah. So, since force is equal to QVB, can I not say, therefore magnetic field is force divided by QV. Therefore, I can just write 1 Tesla of field is when 1 Newton of force, 1 Newton force acts on a Coulomb of charge when it is moving a meter, per second. When it is moving a meter per second perpendicular direction, because then sin 90 will be 1. So that is the meaning of 1 Tesla. Force is Newton, Q is Coulomb, velocity is meter per second. So that's how they define it, and that's exactly what they have done over here. Newton, second, Coulomb, meter, and all of that. This unit is basically called Tesla. The units of be Newton, second, Coulomb, meter. Okay. I hope till this point everybody is clear. Understood? Give me a thumbs up. What is the meaning of Lorentz force and everything? All right. Now, before going ahead, let's do one thing. Let's just solve some questions so that you guys get a heads up or understanding of how to use this. I will give you some examples and you are just going to tell me which direction is the force acting on the moving charged particle. That's all you have to tell me. Okay? Chalo. Let's see if you guys can do this. This is the charge. E is electric field, B is magnetic field. E is electric field, B is nothing but magnetic field. Okay, that's all. So many diagrams are shown, some places electric and magnetic both are acting. So there might be a net force also, who knows? Okay, let's do case by case. Start off with this, then go to this, okay? So many examples are there. Let's do this. Come on, Atluru, Jasmine, Disha, Sukanya, Madhumati, Krishna. Come on, everyone. Let's go. Evening Star, Tanuja, come on. Let's go, guys. Let's start solving these questions. Maybe in your rough book or in your rough sheet, you can start doing it. So first of all, if you go over here, the first problem, only electric field is there. So only electric force will come. Only electric force will come. So the force obviously will be in this direction. Same direction as the field. That's it. That's how the force will be. In this case, only magnetic field is there. So the force will be in the direction of velocity crossed with magnetic field. Use your right hand thumb rule. First point the fingers in the velocity direction. Slowly turn it towards magnetic field. The thumb is coming towards you. So the force is like a dot. Force is like a dot. Remember, you have to use cross product. You have to use basically cross product, like I said over here. V cross B is the force. Use your right hand thumb rule. Okay. Next, here, no matter what the velocity is, force of electric field always will act in the direction of electric field. So the force is in this direction. This was electric force. This was magnetic force. This is electric force again. Okay. Next, here, velocity is here. Velocity is here. Magnetic field is towards you. Use your right hand. Point it in the direction of the velocity. Slowly move it towards you. The thumb goes up. Hence, the force acting due to magnetic field will be in the upward direction. Just check this out. It will be upward direction. Here, what happens? The charge is not moving. So actually speaking, the magnetic component of the force will be 0. Because no velocity, no force. Only electric field's force will be there, just like here. The force of electric field will be in this direction. Is that right? Very good. Next, let's go over here. Oh, this is magnetic field. Velocity is up 180 degrees. So the magnetic field's force will be 0. Parallel or anti-parallel, magnetic fields never apply magnetic force. Let's go over here. Same story repeats. Same story repeats. Magnetic field will not apply any force. But what about electric field? That will just apply the force in the direction of the field. That's it. Fe is in the direction of the field. Here, magnetic field is parallel to the velocity. So the magnetic component of the force is 0. Electric field will definitely apply a force over here. That's it. That's how it works. Let's take another example over here. It is given to you that it is an electron and that electron is going downwards, and it is told to you, listen, the magnetic field is right over here. Can you figure out where is the direction of the magnetic force? Quickly think and tell me. Where is the direction of the magnetic force? Velocity is down. You will have to really twist your hand, guys. Velocity. Hold your right hand like this and move it slightly in the direction of B. V cross B, it is coming towards you. So be careful. V cross B is towards you. But there is a problem. I'm multiplying with a negative charge. This is negative charge, so it will change the direction. So hence, it will make it exactly opposite. That's why the force will be in the plane. Lot of people will tell out of the plane, but that is a wrong answer. Got it? It's a negative charge, so be careful. If it was a proton, then it will be towards you. Cool? Let's do one more question coming up on your screen, guys. Imagine again there is a negative charge, negative E or negative Q charge, let's say, and it is going like this, and the magnetic field is inwards. Magnetic field is inwards, and let's say the electric field is downwards. Electric field is downwards. Come on, think about the forces due to each one of them. Think about the forces due to each one of them in this particular question. First, velocity is towards your right hand side. Magnetic field is inside. So place your right hand 4 fingers towards the right. Slowly bend it inside. The thumb will point in the upward direction. So therefore, the magnetic force is in this direction. But the electric field will apply a force in this direction. Now whichever is more will dominate and the net force will be in that direction. In this case, the forces are opposite, may or may not be equal. That depends. Okay, but they are definitely opposite to each other. That is what we are seeing. So I hope now you understand how to find out the net force acting on a moving charged particle, whether it is positive or negative. In fact, if you notice, one of these statements also mentions the same thing. The force on a negative charge is opposite to that on a positive charge. Very important line. The force on a negative charge is exactly opposite to that on a positive charge. So that is the reason why in these problems, we first find V cross B. V cross B would be out, but the moment you multiply it with a negative charge, it will go inside. Same thing over here also. V cross B was here, but it is a negative charge. So whatever the force was expected, you will have to draw it in the exactly opposite direction. So V cross B will be up, but since it's a negative charge, the force will be downwards. Same way, electric field's force QE should be downwards, but because it's a negative charge, that force of the electric field should be technically upwards. So because of this minus sign, this is the final answer. Otherwise, for positive charge, it would have been up for magnetism and it would have been down for electric force. Got it? Yes, Krishna. So the direction will change. So that was the point which I wanted to make over here. Okay, so that's why I made you underline this. Now I wanted you to see this. So all these things are important, small things. Cool. Now I think they have done the examples later on. So we can do this example and then we'll come back. Okay, we'll do this particular example and then we'll come back. If the magnetic field is parallel to the positive y-axis, okay, x is right, z is up, y is inside. So basically the magnetic field is inside the plane of the board. You can see that crosses, cross means going away inside the plane. And a charged particle is moving along the positive x-axis, which way the Lorentz force for an electron and a proton be acting. Okay, the magnetic field is there. So guys, very simple. Magnetic field is inside. The velocity of the charged particle is right over here. So if you do V cross B vector will be right over here. First put in the V direction, then B, it will be upwards. So if it was a positive charge, versus a negative charge, then on the positive charge, the Lorentz force would be like this, but on a negative charge, the force would be exactly opposite. That's the only difference. Got it? Positive charge, it would be like this. Negative charge, it would be like this. Something very similar to this example. Because it was negative, we had to reverse the direction. Is that clear, everyone? Yeah, same thing that what they have done over here. Great. Now, let's come back to section 4.2.3. See, Oersted said that moving charges produces magnetic field. Right at the beginning only, we have discuss this. Oersted said that moving charges or currents produce magnetic field, and then we said that, okay, listen, we have to find how this field affects moving charges or currents. This part we just did, which is the Lorentz force. This part is what we are going to see now. We just did how magnetic field affects motional charges. Now we have to see how magnetic field affects current carrying wires. So let's come to that particular point. Let's come to that particular point. Right over here only, they have mentioned all these things, and they have done some small derivation over here, and then they finally come up with some answer or solution. So what exactly have they done? Let me tell you that. See, simply put, if you have a current carrying wire, and let's assume that the direction of the current to be like this. I know negative charges go like this, opposite to the current, but isn't it the same as saying an equal amount of positivity, an equal amount of positive charge goes like this, equal amount of positive charge goes like this. So these positive charges are traveling with a drift velocity. I hope you remember drift velocity, which you have done in current electricity, and each charge being plus E, plus E, plus E, plus E, plus E like this. So they are moving with basically the drift velocity. I hope this is absolutely clear. So if moving charges can experience force, a current carrying wire is also moving charges, so that will also experience force. So I can say that the force on the charge carriers, will be nothing but the charge, in this case, is nothing but E into velocity of them, which is nothing but the drift velocity, and then it will be crossed with nothing but our magnetic field. That will basically give me the force on any of the charge carriers. But there will be many such charge carriers. In even a unit volume, there will be so many such charge carriers. I hope you understand that. So if you add all these forces, on all the charge carriers for that wire, so the force on the current carrying wire is the sum of all the forces on all the charges, and that force on that particular wire which carries current is given by I, okay, I, and then you have basically the length of the wire, and then you cross product it with the magnetic field. That's it. That is the final answer. So the force on a wire carrying current is given by I L cross B. This is the force on a current carrying wire, which is the sum of all the forces on the moving charges. This is exactly what they have given. Now usually what happens, our wire may not be straight, it might be basically bent. So what happens is, usually you do not end up blocking this. Rather, you say that, listen, my wire might be big like this, it is carrying some current I. You take a small part of that wire, which has a length of dl, and it is carrying that same current I, and maybe magnetic field is going like this over there. So it will experience some force in the direction of L cross B. Length is here, magnetic field is here. If you do the cross product, it will come towards you. So there will be a small force like this. It will be dF. So the force on the element of that particular wire is df, and this df technically is current into that small element which is dl, and you cross product it with the magnetic field. But when you want to find the net force on the wire, when you want to find the net force on that particular wire, that force on the wire will be the sum of all these forces, which means integration. Integration is summation. So therefore, you will see it will be always the net force on that particular wire will be integration of that current into dl cross the magnetic field. This is the main answer. This is your small answer. This is force on a small part. If you want to find the net force, you will have to sum up, add up, integrate all the small chintu mintu forces to find the net force. That is what it means. I hope this is clear. This is the main statement, and this is exactly what they have mentioned. This summation can be converted into integral for most cases. So this is the net force, which is I integration cross of length cross b. So they have written it in weird forms over here, but we have made it look very straightforward and simple. Okay, till this point clear? This formula, use it only for a straight wire. This formula, preferably use it for a straight wire, because then when you have a curved wire, what is the length, right? So it will not be the length in a curved manner. So use it for a straight wire. If the wire is bent, then you have to basically, use this integration. Okay, let's see a simple example right over here. There is a wire whose mass is 200 grams, not much. Length is 1.5 meters. It carries 2 amperes current, and it is suspended. Imagine a wire floating in air. Isn't it crazy? And why is it floating? Because of the magnetic field which is traveling inside that plane of that board. What is the magnitude of the field? Okay, so there is a magnetic field which is going, there is current which is going, and the weight is being balanced. So this problem has to be solved by drawing or showing all the forces. Obviously, the weight will act down. There must be an equal and opposite force so that it stays in equilibrium. It stays in equilibrium. How do I know it's in equilibrium? It's clearly mentioned. It is suspended in mid-air. Means it is balanced. Who will balance it? IL cross B force. I, length cross B force. See, the length of the wire is here. Magnetic field is inside. So can you tell me what is the angle between the length and the magnetic field which is inside? The length and the magnetic field which is inside. Clearly it is 90 degree. Clearly it is 90 degree. So my dear students, this magnitude will be ILB sine 90 being 1, it will just be ILB. So clearly ILB is equal to mg, rather B is mg divided by IL. Mass 0.2 kg, G is 10. Current how much? 2 amperes. Length is nothing but 1.5 meters. Point goes off with the 10, 2 cancels, 1.5 is nothing but 3 by 2. So it will be basically 2 by 3 Tesla. So magnetic field is basically 2 by 3 Tesla or 0.66 Tesla. Yep. I hope this is absolutely clear. Everyone? Yep. Correct, Madhumati? Yes, Atluru? Awesome. Now in the actual question, what they have done is they have taken the G value as 9.8. So they have got slightly less value. But we have taken the value of G as 10. So we have got slightly higher value, which is 0.66. So that's okay in the NEET exam or in the board. So you have to assume something. Either it will be given or generally you take G as 9.8. Unless the options are not matching, then you go to G is equal to 10. Yep. In NEET exam, all those things don't happen. Cool? Okay. So this is what we had done. Now there is one interesting thing I'll tell you about wire carrying current, especially if the wire is curved. A lot of people, will suffer if they do not know this trick. Imagine this is a curved wire, and this curved wire is placed maybe in some magnetic field, maybe it is going inside, and let's say it is uniform, for example. This is uniform magnetic field. If I want to find the force on this particular curved wire, you know what you can do? You can just find out by taking a straight line carrying that same current, a wire replacing that curved wire with a straight wire. This is like distance, this is like displacement. You just find the force on the straight wire. On the straight wire. Your job is done, which will then be basically current into that effective length cross-producted with that magnetic field. That's it. This makes the job very, very easy. So this is a very, very important simplification which you should know. There is another direct application of this. Imagine you have a loop carrying current. What is this? This is a loop of basically current, and maybe there is magnetic field which is probably headed like this, maybe. Who knows? This is again your uniform magnetic field. For such a loop, instead of a curve, the final point is the initial point. That means what should be the effective length? What should be the effective length? It will be the 0, because the start is the end. The end is the start is the end. So the effective length is 0. So if you had to replace the loop, you will replace it with nothing, because there is no start or end, it is just 0. So hence the force acting on any such loop in a uniform magnetic field is 0. Again, a very, very important statement. This is a result of this then. Isn't it amazing? A uniform magnetic field will never apply a force on a current carrying loop, but it will apply a force on a curved wire. There are many such examples which are based out of it. Say, you have a semicircular wire. You have a semicircular wire carrying current, let's say like this. You have to find the force acting on this particular semicircular wire. So what you do is basically forget it is a semicircular wire, replace it with a straight wire carrying that same current, which means when you replace it with this, in that same magnetic field, of course, in that same magnetic field, the length which is there effectively now from here to here is the diameter, which is basically 2 times the radius. So therefore that force will be, current is there, length is basically 2r, magnetic field is inside, the angle between the length and the magnetic field is inside, length is here, is 90. So it will be basically sine of 90 degree. Hence the force will be 2IRB. Hence the force will be 2IRB. Got it, everyone? Cool. How easy it is to solve the problem by using this simple property. Not just that, there were very tricky questions also which I have seen in NEET or probably even in CBSE they can ask you. Say there is a wire which comes in like this. Okay, we'll do one thing. The current comes in from here and the current goes out from here, and the magnetic field of course is like this, and it is uniformly present everywhere. Magnetic field is present everywhere. This is a square. So you have to find the force on the square of side length A? That is the question. Force on the square only, don't calculate the force on the outer elements, okay, whose side length is A. Now you will be like, sir, it is a loop, sir. And you just told me whenever it is a loop, the net force acting on it is 0. Sir, so the answer should be 0, right? That is what one would normally guess. But be little careful. Be little careful. In a loop, the current starts and comes back to the same point. This is not a loop. Please understand. Even though it looks like a loop, it is not a loop, because actually speaking, the currents are not traveling like this and coming back. Rather, the current over here is getting distributed like this and like this. I by 2 and I by 2. Half here and half here. Is that so? Everyone? So be very careful. So now you find the force on any one segment, you can say that the same force acts on the other part. So if you multiply by 2, you will get the net force. So say, for example, you just find the force on the upper element, which has the current of I by 2, side length is A and side length is A. This diagram is a bent wire, is a curved wire. You can replace it with a straight wire. You can replace it with the same wire carrying current I by 2. How much will the length be? Well, if you think carefully using Pythagoras theorem, if this is A, this will be nothing but A root 2. A square plus A square is 2A square, so it will be A root 2. Got it? So this is a common mistake, otherwise you would get the answer as 0. So now think as if this is placed in that magnetic field. How much will be the force on this part? The force on this particular part will be I, which is I by 2, length, which is A root 2, into B, into basically sine 90. Sine 90 because angle is 90 degree. So it will be root 2 IAB divided by 2. That is the force on this particular part. But let's not forget that there were two parts. One part was also here. So there was a part here and there was a part here. So both these parts will experience the same force, I L cross B. So one force here and this will also experience the force. They will not cancel out each other. Currents are in the same direction. So therefore, the net force will be 2 times this force on any one part. So it will be 2 times of root 2 IAB by 2. 2 cancels. It will become root 2 IAB. That is the final answer on that square loop. Is that clear? Answer is definitely not a 0. Got it? Did you love this question? Was it an interesting question? Okay. So this is how you find the force on current carrying wires. Force on current carrying wires and loops using this particular formula. Great. Now, let's come back to the force on moving charges, which we just studied some time back right over here. This one, the Lorentz force. And there are some special cases on this. There are some special cases which you need to know, and you will see it regularly being asked in many examinations. So let's come back to that. That is what the next section is all about. So they talk about motion of a charge in magnetic field and the different cases, and then there are problems on it. Let's start one by one. Here they talk about, okay, we consider in great detail the motion of charge in a magnetic field. We have learned the mechanics, blah, blah, blah. Charge particle in a circular motion. So work done is not changing the magnitude of the velocity produced. So by the way, this part I have already done in the starting of the lecture. Okay. Motion of a charged particle in magnetic field, the magnetic force is perpendicular to the velocity of the particle. So no work is done and no change in the magnitude of the velocity is produced, though the direction can be changed. Notice this is unlike the force due to electric field. Notice unlike electric field, which can change, which can transfer energy in addition to the momentum. So we shall consider a charged particle's motion in the field. First, let's consider the perpendicular case, and then we will take the other thing. Okay. Now, you might ask, sir, where did we do this? This particular part. Let me go back and show it to you where we have done. Right at the beginning. Shreyas sir knew it will come. So Shreyas sir did it. Force is perpendicular, work done by it is 0, no change in the kinetic energy. So speed, that means magnitude can't change, but the direction can change. The direction can change. But this is not the case with electric force. Electric force can definitely change the speed. We have seen that. It can also change the direction. So electric force can change speed as well as direction, but magnetic force, can it change the speed? No. Can it change the direction? Yes. So a statement based question can come from NCERT. Statement based questions can come from NCERT like this in your NEET exam also. Electric force can change magnitude and direction. Magnetic force can change magnitude and direction. That statement will be wrong. Magnetic force can change speed but can't change direction. That would be also wrong. Magnetic force can change direction but not speed. That would be correct. Is that clear? Give me a thumbs up, then we'll proceed. Give me a thumbs up, then we'll proceed. That is what is mentioned here. So let's start with the first case then. The first case under our consideration. First, consider the case of V perpendicular to the magnetic field. So the particle will describe a circle to each other. Okay, we'll come to that. Say for example, this is how the magnetic field is. It is inside the plane of the board. It is inside the plane of the board. Imagine there is a charged particle Q like this, and it is given a velocity in this direction. Okay, it is given a velocity in this particular direction. Now what happens is, because the magnetic field is there, velocity is there, so it will experience a force. And which direction will it experience the force? Think about it. The force will be V cross B. It will be in this direction. V cross B. The thumb comes out here. So the force will be here. But this can't change the speed. It can only change the direction. Okay. So the particle will basically continue to go maybe like this. It will continue to go like this. Direction is changed, but magnitude is not changed. And this will always happen, that velocity and force will be perpendicular, only direction will change, which means this should end up doing circular motion. There is no other option only for it. There is no other option for it. It will end up going in a circular path, and only in a uniform circular motion will you see, no matter where you go, no matter where you go, the force will be perpendicular to the velocity. The force will be perpendicular to the velocity. So this has to be a uniform circular motion. And this uniform circular motion is in a transverse field, transverse magnetic field. I have seen such questions on statement based in some competitive exams. A charged particle in a transverse, meaning perpendicular, meaning normal. You can see velocity is perpendicular, velocity is here, magnetic field is inside, is perpendicular to the magnetic field, then it performs a uniform circular motion. So options were parabolic motion, straight line motion, elliptical motion, circular motion. See, if it was planets, Kepler's laws, then it will go to elliptical motion. If it was maybe a ball dropped, it will be a straight line motion. If it was a ball thrown at an angle under gravity, it will be a parabolic motion. but this is a charged particle. Throw in magnetic field perpendicular to it, it will go in a circular manner, in fact uniform circular motion. Correct. So a uniform circular motion has some parameters which you should definitely know and find out. The first one being the radius and the second being the time period of the motion. So if you want to find the radius, start off with this. The magnetic force provides, because it's a circular motion, you need centripetal acceleration. So it provides centripetal acceleration. So the centripetal acceleration, of course, is towards the center. That's why it is called centripetal acceleration. So the magnetic force is mass into AC. This is your second Newton's laws of motion. So that force will be the charge into the velocity, into the magnetic field, into sine 90. Why? Transverse, clearly mentioned, means 90. Acceleration, we have seen this in circular motion, is V square divided by R. Sine 90 is 1, VV cancels. So it will just become QB is equal to MV divided by R. Therefore, you will see R is nothing but mass into velocity divided by QB. Very important formula which again you are supposed to remember. You can play around with this formula a little bit and write it in slightly different forms, like how mass into velocity is momentum. So momentum divided by charge into magnetic field. Also momentum is root of 2 times mass times kinetic energy. So again divided by QB. So if momentum is given, use this. If kinetic energy is given, use this. If speed is given, use this formula. Accordingly, you can use any of them. But if you remember this, it is better because you can get this or this very easily, because those are dependent formulas. You can't sit and remember everything, just remember one thing. That's more than enough. Correct. Right? Now that was the radius, of course. We can also find what is the time period of revolution. We can also find the time period of revolution. So the time period of revolution is given by T is equal to circumference, the circumference of that circle. Time is distance by speed upon that speed. Circumference is 2 pi r, speed is v, but wait a minute, your r is nothing but mv divided by qb. How? I just got it now over here, mv by qb. vv cancels, so I'm just left with 2 pi m divided by qb. That's your time period of revolution. Best part, it is independent of speed. It's independent of the speed. Can be useful in some questions. They might give you a particle is thrown with 100 meters per second. Another similar identical particle is thrown with 500 meters per second. Which one will take more time to complete a circle? The answer will be both will take the same time. Yes, the radius will be different. The one which is thrown with less speed will go in a smaller circle. The one which is thrown in larger speed will go in a big circle. But both of them will come back in the same time. That's very, very important. Okay, this is very, very important. So lower speed versus higher speed, the only difference is the circle's radius. This will go in a smaller circle. This will go in a larger circle, but it will take the same time. Is that clear, everyone? Yep. Awesomeness. Great. So these two components, these two formulas you must remember, guys, for solving problems. Now, I think there is a question on that. Before that, going to the next topic, first I think we'll do this. Yep, this is a very interesting question. What is the radius of a path of an electron and charge moving at this speed in a field perpendicular to it? What is the frequency? Calculate the energy in blah blah blah. This is the question. Let's try to solve this. First part, radius of a path of an electron which is moving in a magnetic field which is perpendicular. I can see the word perpendicular. I immediately know it will be uniform circular motion. Uniform circular motion in a perpendicular magnetic field, exactly like this. Okay. So quickly, I jump to the formulas which I already have by hearted. mv divided by qb. Mass is the mass given. Yes. 9 into 10 to the power minus 31. Is the speed given? Yes. 3 into 10 to the power 7. Is the charge given? Yes, it's an electron, so it will be nothing but 1.6 into 10 to the power minus 19. Is the magnetic field given? Yes, 6 into 10 to the power minus 4. All these values, solve this guys and see what is the radius that you get. They have, I think, got the radius as 28 centimeters, or basically 28 into 10 to the power minus 2 meters. Basically, you get the radius as just 28 centimeters. So this electron will go in a circle of about this size, 28 centimeters. So it will keep going round and round about this size. That's how you do it. Same way, we can go to the second part. What is the frequency? Frequency is 1 by time period, and time period is 2 pi mass divided by qb. So therefore, frequency will be charge. Where is the charge? Where is the charge? 1.6, 10 to the power minus 19. Magnetic field, how much is it? 6, 10 to the power minus 4 Tesla. 2 into 3.14 into the mass, which is 9 into 10 to the power minus 31. So that frequency, after solving this, you are getting it as 17 megahertz. 17 into 10 to the power 6 hertz. Frequency's unit is hertz. 10 to the power 6 is mega. So megahertz. So just imagine how many times it is going. Not 5-6 times or 17 times. It's 17 mega. So it is 17 million times in 1 second. In 1 second, so quickly, tuck, 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 it was going so fast. It's crazy to even think about it. Lastly, they have asked about the energy. Lastly, they have asked about the energy of it. What is the energy? Now, how do you find the energy? Well, there are many ways to do that. See, if you go back to our original formula, you can use this from the radius to find out the energy. Okay. Or forget that. You can just say it is nothing but half mv square. Because speed was already given, so don't have to break your head so much. It will just be half mv square. So therefore, kinetic energy will be half into mass 9 into 10 to the power minus 31. Speed 3 into 10 to the power 7 square. But this answer, mind it, it will be in joules. It will be in joules. Yes. So whatever you get, it will be in joules. 9 into 9, that's basically 81 divided by 2. 7 into 2, 14. Correct? And you have 31 with a negative power. So 31 minus basically 14 will be minus 17, 10 to the power minus 17. This will be in joules, but I don't want the answer in joules. I think it is in electron volt. So 81 into 10 to the power minus 17 by 2 divided by 1.6 10 to the power minus 19. The answer will be in electron volt. Finally, you solve the question and you get the answer as 2.5 kilo electron volt. 2.5 kilo electron volt. 2.5 kilo electron volt. That is the answer that you get. Understood how to solve these questions, guys? Everyone with me? Okay. And if you have joined the channel very late, please subscribe. And if you have joined the lecture also late, first of all, after subscribing and probably, you might have missed joining the Telegram group or turning on the notifications, turn it on. And if you are watching it recorded, but watching it sincerely. Still, kudos to all of you. Very good. Keep it up. It shows your commitment that even if you can't attend the lecture live, for some reason, you're watching it in the recorded manner. Keep it up, guys. All right. Thank you so much. Great. Thank you for liking. In case you have not yet liked the video, please like it. All right. So this was one peculiar case. Now there is another case which we need to see after this, and that is this particular case of, at an angle. So we'll come to that. So imagine there is this charge again, but this time it is thrown with this velocity at an angle to the magnetic field. At an angle to the magnetic field. This is the second scenario. When this happens, what I'm going to do, I'm going to split this velocity into two components. One component of the velocity is here. If this is theta, this would be v cos theta. The other component will be here, which is v sin theta. Now tell me one thing, when magnetic field and velocity are parallel, how much force does it apply? When velocity and magnetic field are parallel, what will happen to v cross b? Cross product will be 0, parallel vectors, sine 0 is 0. So that means what should happen? Won't this component v cos theta be unaffected by the field? Do you get it? V cos theta is basically, this particular v cos theta is nothing but parallel to the magnetic field. So therefore, v cos theta should be constant. Should be constant, since there will be no force only on it. No force on it. V cross b will be 0. Very nice. Okay. But what about v sin theta? Oh, that will experience a force, guys. That will definitely experience a force. Magnetic field is right, velocity is up, so v cross b will be towards you. V cross b will be definitely towards you. So the force will be like this. And this force will be q v sin theta into b. Q v sin theta into b. Oh, sorry, v cross b was inside, my bad. I did b cross v, so sorry guys. It will be inside, my bad. Yeah, that force will be inside on this v sin theta. So can I say v sin theta, but v sin theta will change the direction, due to magnetic force without changing the speed, without changing its magnitude, Okay, so how will it look like, you might wonder. How will it look like? Let me show that to you. It's a very, very interesting thing. Just imagine this is your vertical axis. This is the axis which is coming out of the plane of the board. I'm trying to show it in 3D. The force is inwards. That means on that charge, the force is like this. I'm trying to show a 3D view of this. The v sin theta component is over here. The magnetic field is over here. So because of that force, what will happen? This velocity which is there will go like this, and the force will always be perpendicular to it. So it will go in a circular path in a weird direction. Let me show that to you. Try to visualize this. This is in the YZ plane. Are you able to visualize this, guys? It's basically in the YZ plane, my dear students. See if you are able to think about this. It's in the YZ plane. Are you able to visualize that? Think carefully. It's in the YZ plane. Yep. This V sine theta, this particular V sine theta, right? It goes like this, then it goes like this, then it comes like this, it comes like this, goes like this. So it is always V sine theta which is going round and round and round like this. I hope you are able to visualize. But at the same time, the V cos theta is trying to push it in this direction. V cos theta is trying to push it in this particular direction. So because of both of these two things happening simultaneously, what will end up happening is this. It wants to come back to the same point, but it won't. Rather, it will go like this and it will come back slightly in front of it, and then it will go like this, and then it will come in front of it, and then it will go like this, and again it will come in front of it like this. This motion, where the circular motion is slowly shifting ahead in its axial direction. This is the axis, the x-axis is the axis of the circular motion. It's slowly going ahead. So this is basically called as a helical motion. So when velocity is not perpendicular but at an angle, both these components play a role. The V sine theta is responsible for circular motion. The V cos theta is responsible for the motion along the axis. So both of them combined, it does a helical motion. That diagram is beautifully drawn by me also and by NCERT also. See this, how it is going in a helical motion. I hope you can visualize this. I hope you are able to visualize this. So this particular helix which I have drawn, that helix has many parameters. First is, obviously we can talk about the radius of the helix. We can talk about the radius of that helix. So maybe this would be the radius. There would be radius. Then it will have a time period. So radius will be, instead of mv, it will be mv sine theta. Because just think about it, this is the radius. Okay, so radius will be mv sine theta divided by qb. Time period still the same, no effect, it won't get affected by speed. So 2 pi m by qb. There is one more parameter which is the distance from this point to this point, or from this point to this point, or from this point to this point. Basically, after one rotation, how much does it go ahead? That is called as the pitch. What is the meaning of a pitch? After one rotation, how much did I move ahead? Just imagine, I take my hand like this, I am moving it like this. I am not moving, I am just moving my hand. So after one rotation, my hand comes exactly at the same point. But just imagine, I move forward. So after some time, my hand comes here instead of here. So it has moved ahead exactly after one rotation. So from this point to this point, that distance is called as a pitch. So what do you think will this pitch depend on? Obviously my speed. If I move fast, I will have a more pitch. If I move slowly, then I will have less pitch. I will move less. So this particular pitch depends on the axial speed multiplied by how much time I take to complete a revolution. Distance is speed into time. That speed horizontally is v cos theta. So just put v cos theta over here, and the time is exactly this time. So 2 pi m divided by qb. So mainly don't remember this, just remember this. This is enough. radius and time period are still the same, only speed will be v sine theta. Is it clear, everyone? What is the meaning of the pitch? Time period is the same as circular motion and radius is as it is. Oh, thank you, Madhumati. Thank you, Atluru. Thank you, everyone. Let me hydrate quickly. Thank you guys. What would I do without you? I'll forget even drinking water. है ना? So that's how you should be involved in your studies. That's how you should be involved in your learning. And that's how a teacher should be involved in his teaching. That you forget about all the luxuries in life or even the necessities in life. Drinking water is not even a luxury, isn't it? So thank you guys. I mean, only because of you, I keep involved. I keep myself, occupied, and I feel myself as lost in teaching or probably involved in this, platform or just physics. It's pure satisfaction, isn't it? And I want you to do the same thing years down the line when you guys become a doctor. You should be so involved in your medical research, in treating patients or whatever work you are doing that you should probably forget, and probably the patient only should remind you, doctor, did you eat food? Doctor, did you eat your lunch? Doctor, did you sleep? Doctor, did you have water? Isn't it? That would be amazing. Right. So this is that. Moving ahead. That is what is mentioned right over here. Cool. This is fine. Okay. Now we are going to the next part slowly. Here we are talking about the magnetic field due to a current carrying element. So till now, whatever we did, let me show you right over here. How magnetic field affected charges or currents. Now we are coming back to the original part, how a current produces this magnetic field in the first place. So we did this and this. Now we are slowly coming to current producing magnetic field, which was actually given by Ørsted long time back. How does this current produce magnetic field? Now we know that a current around it produces magnetic field in circular loops, and magnetic fields are always loops. They never basically end at any point. They are always in the form of closed loops. How much is the magnitude can be found by a law called as Biot-Savart's law. Biot-Savart's law is a law like your Coulomb's law, which tells you what's the field at any point. Newton's law of gravitation also tells me gravitational field and force at any point. Coulomb's law gives me the field or force at any point. So Biot-Savart's law gives me what is the field due to the current carrying wire. What is this particular field at this point due to this current carrying wire, okay, around it. That is what it is. So it is the source of magnetic field. So going ahead, wow, so much done already. Where are we? Here. Yeah. Magnetic field due to a current element given by Biot-Savart's. All the magnetic fields light below are due to intrinsic moments. Here we shall study the relation between the current and the magnetic field it produces. So basically this particular law, it shows us the relation between the current and the magnetic field that it produces. So there is a conductor, etc. They have described this, and then finally they have given a beautiful formula right over here. So I'm blocking it, where mu naught by 4 pi is the constant of proportionality, and it is dependent on the medium. Okay, fine. So the magnitude of this is given by this formula. This is the more important formula. and the constant value is also given. Mu naught is called as the permeability of free space. The differences are some. Okay, electrostatics. Okay, this is given, and then they start describing different things. All right, let's start one by one. Imagine there is a wire. This is a wire carrying current. Obviously, it will produce magnetic fields around it, and I'm interested in finding the magnetic field at any location. So let's say that location happens to be somewhere over here, and every part of the wire is at different distance at different angles. So they might produce magnetic fields also in different angles and different directions. I will first start by finding the magnetic field due to any one such small part of the wire. So if you take a small part of that wire, maybe here, the current is going like this, so that element will also be treated like a vector quantity. That element is dl. So dl element in the direction of the current. dl is a small element in the direction of the current. I want to find the magnetic field here, so I will just draw a line like this, and I will say that, listen, this is the position vector. This is nothing but the position vector of the point where you want to find the magnetic field. Next step, just do the cross product of dl with r. dl with r, you will see the thumb going here. That is exactly the direction of the magnetic field. So the magnetic field at this point is coming towards me, but since it's being produced by a small element, the field will also be very, very small. Later on, I will see that the total magnetic field produced by the entire wire will be, you take all such elements, you take one element here, you take one element here, you take one element here, you take all the elements of that wire, and each of these elements will be at different distances. Each of these elements will be at different distances, different angles. So you add all those magnetic field due to all those elements. That's it. So it will be nothing but equal to integral of dB. That's it. So the magnetic field as a total will be integral of dB. As simple as that. Is this point clear? You find the magnetic field due to each part, you add them up, you will get the net magnetic field at that given point. How much is that dB? That is given by as follows. This dB is, there is a constant, that constant I will call it as mu naught by 4 pi. Just like you had permittivity, here you have permeability. I'll come to it in a bit. Then you have the term IDL, and then you cross product it with r vector, that is the position vector, and divide it with r cube. This is the vector form, but if you write it in magnitude form, magnitude form, then what will happen is, this will be some constant mu naught by 4 pi. Here you will have I dl r into sine theta. Look at this, the angle between them. If it is theta, then here you will have sine theta. R and r cube will cancel, and I'll be left with r square. What happened to that r? It cancelled with this r. I'm just left with r square. So this becomes the magnitude part of it. So this is the formula for the small field due to a small element. What is this mu naught called? Permeability. Permeability of vacuum. And this value is 4 pi 10 to the power minus 7 SI units. Very, very important. This value of mu naught is 4 pi 10 to the power minus 7 SI units. Just like you had permittivity, you have permeability. Remember how the electric field formula looked like? Electric field formula looked like in electrostatics. Try to recollect. You had 1 by 4 pi epsilon naught, and then you had the charge on the top, and then you had distance square. Do you remember this? This was the formula for electric field due to a charge. Very similar looking formula. Instead of epsilon, you have mu. Instead of that constant being down, you have it upstairs. That's the major difference. In fact, throughout magnetism, you will see the formulas are same but different. The same part is this. The different part is wherever you see epsilon below, mu will be on the top. Wherever you see epsilon on the top, you will see mu below. Wherever you see charge, you will see current into something or the current length combination, ideal. You can see R square here, you can see R square here also. Do you see? Same but different. I'm just comparing it. This is just for comparison. This is just for comparison. Okay? Very important again. This is just for comparison. I'm just blocking it. So permittivity replaced by permeability, distance square inversely proportional, correct. Instead of charge, you have ideal. Also notice one thing, charge was a scalar. What is ideal? Ideal is not a scalar, it is a vector quantity. So here charge was scalar, here it is a vector quantity, correct. So these are some minute small differences and similarities that you can see over here. Okay, so that's exactly what they have done by writing over here. Let's have a look. There are some differences, there are some similarities. So if you thought that the reels and the memes that you see, is not read by NCERT people, but I think they were aware of it even in their 90s and maybe even 2000s, because this NCERT dude has written down same but different. So NCERT dude wrote same different, much before GTA 6 and much before the Gen Z. So they are really cool, guys. They are really cool. They were the original memers, isn't it? Okay, so both are long range, both of them depend inversely. Yep, perfect. Both of them depend inversely on the square of the distance from the source. This is definitely true. Electrostatic force is produced by scalar charge, whereas magnetic field is produced by a vector source ideal. This is something which I just told you over here. Field produced by scalar, magnetic field produced by a vector, which is ideal. Perfect. That is what they have told right over here. That part done. Next important thing, electric field is along the displacement vector joining the source, whereas magnetic field is perpendicular to it. So electrostatic field is along the displacement vector, whereas the magnetic field is perpendicular to the plane containing the vector, and that's blah blah blah. What does this mean? Going back over here, do you remember electric field is in the direction of that position vector? If this was R, wherever the position is, in the same direction the field also is there. But magnetic field is not like that. If you are here, it is perpendicular. If you are here, it is perpendicular. So that is what they are basically telling you at this point. Yes. So if you are here, the magnetic field is not in the same direction. Rather, it is in some perpendicular direction only to this particular plane. Whereas electric field is in the same direction of where you are. That is what this particular point says. There is an angle dependence which is not there in electrostatic field. Yes, angle dependence in the Biot-Savart's law which is not there in electrostatic case. That is also seen. Look at this, sine theta is there here, there is no sine theta here. So angle dependence is there between the position and that element. That is not there. Cool. Same but different. Also they tell you that there is a relation between this and this, which is given by this particular formula. So let me just block it. Actually, you don't have to remember this now because they have clearly mentioned we will discuss this in chapter 8, in the chapter 8 of electromagnetic waves. So what is it that they are telling me over here? Sorry. What is it that they are telling me over here? They are telling me, if you know permittivity, I can find out permeability. If you know permeability, you can find permittivity. The formula goes like this. Speed of light square is 1 by epsilon naught into permeability. So if I know this, I can find this. If I know this, I can find this. That's all that they are telling. So this is nothing but your speed of light. Speed of light, which is 3 into 10 to the power 8 meters per second. That's exactly what they are telling. Okay. C square is 1 by epsilon naught mu naught, or epsilon naught mu naught is 1 by c square. Okay. Thank you, Madhumati. Thank you, Krishna. Thank you, Atluru Warrior Pandus. Great. Okay. Let's see a question based on Biot-Savart's law. A very nice question coming up on your screen. There is a current which is placed element at the origin, carries 10 amperes. What is the magnetic field on the y-axis at 0.5 meters? Delta x is 1 centimeter. Let's visualize this, guys. So maybe it's a long wire. I'm just taking a small part of it and the current is going in this direction. If you talk about this, this is IDL and this IDL is same as I delta x. This current is 10 amperes. Delta x is 1 centimeter, meaning 10 to the power minus 2. So technically it is 0.1. Technically it is 0.1. I want to find the magnetic field here. That means this is my position vector. This is my position vector, which is 0.5 meter. Next thing, the angle between this and this is 90 degree. So theta is 90 degree. If you do DL cross R, the thumb comes outwards. So hence the magnetic field at this point is towards you. So if you ask me what is the magnitude of this, well, we have already seen the formula. It was mu naught by 4 pi. Then you had, what do you say, I and DL over here. And then you have sine theta over here. And then r square over here, correct? This was the formula which we have seen. So start substituting values. This is 10 to the power minus 7. This is nothing but 10 to the power minus 7. Current into DL is nothing but 0.1. Then sine of 90 degree. Sine of 90 degree. Whole thing divided by this distance, which is nothing but 0.5. And square. That's it. That will give me the small amount of magnetic field. This is 0.1, this is 0.5. 0.5 is basically half. Half square is 1/4. 4 will go on the top. So I'm left with 10 to the power minus 7, 10 to the power minus 1, sine 90 is 1. So 4 goes on the top. So this will be 4 into 10 to the power minus 8 Tesla. That's what the formula value is, 4 into 10 to the power minus 8 Tesla. Okay, yeah, it is extremely small due to this small part of the wire. So this is how you can use Biot-Savart's law for finding magnetic field. Very straightforward. Okay, I hope you learned the application. And my dear warriors, my dear Pandus, we are doing all the in-text questions in these NCERT series. That's very important, and you might be wondering why. This is of very high significance. You will see in many of these competitive exams, they directly end up picking questions from here, and many students skip this thinking this is solved examples. Yes, they are solved, but not by you. They are solved by the textbook makers. So you too have to solve it. So it's for you. And they directly pick up questions by changing the values. Great. Now there is a very nice interesting application of this Biot-Savart's law, okay, which we have studied over here, for finding the field due to different geometries. And they try to find the field due to a circular loop on its axis, and then they show the field diagrams, and they also find the field at the center of it. Let's try and understand it. So let's say we have a loop like this, and let's say the current goes like that, comes like this. You will see that okay, if this is a loop carrying current, this is also called as the axis of the loop. Axis of the loop. This is a current carrying loop. The magnetic field due to such a loop looks somewhat like this. Observe it very carefully. It comes like this, goes over here, goes like this, goes over here. This is how the magnetic field lines look like. This is how the magnetic field lines look like. As you can see, if you are close to the center over here, it's very, very strong. This is the center where it is basically strong because the field lines are very close enough to each other. Very far away from the axis, it starts becoming slightly weaker as they are diverging in nature. And because the magnetic field lines are coming over here, this is often on the right hand side, on this side because of the direction. This is the north pole of that electromagnet, and because it is coming in from here, this is the south pole. So basically the behavior is just like a bar magnet where this is the south pole, this is the north pole. So that's why this current loop is also called as an electromagnet. Electromagnet. This is your permanent magnet. This is your permanent magnet because it shows those properties forever. It shows those properties forever. North pole, south pole are there. This is electromagnet because only when you supply electricity, these poles are developed. If there is no electricity, these polarities go away. So you can turn on the magnetic properties on and off by turning on or off the current. Here you can't do that. It's a permanently made magnet. Is that absolutely clear? I hope you loved this diagram. Yes, thank you, Krishna. Hi, Gulshana. Welcome to the Vedantu NEET English channel. Yep. Now, how much is this field is what we are interested in. How much is this magnetic field is what we are interested in. So this is a current carrying loop. Okay. This is the axis. And let's say I am here. Oops. I am here somewhere on the axis. This distance is basically x. This distance is basically x at this particular point. This radius, this is your radius, and at this particular point I want to find what is the magnetic field. Okay, I want to find what is the magnetic field. So here is what I will do. First of all, I will take any element of the current. Let's say on the top, this is my small current element, which is IDL. Okay, a small current element. If you visualize this in 3 dimension, you will realize actually IDL is along the Z axis. Try to think about it little carefully. You will see why it is along the Z axis, because it will be like this. This particular axis. This is your Z axis, this was your Y axis. Are you able to visualize this? So imagine IDL is actually on the top, but it is coming towards you. You want to find due to that element at that point over there. From here you are looking here. From there you are looking here. What is the magnetic field there? So how will my position vector look like? My position vector will look like this. This is basically your R. This is basically your R. Now just do IDL cross R. Current DL is there. Position vector is there. IDL cross product with R. I think it will come like this. The thumb is going at an angle. Just try it out wherever you are sitting. Just imagine current DL is going here. The position vector is going there. It's not horizontal. It's downwards. So when you rotate your fingers, not horizontally, but slightly bend your hand and then rotate it, the thumb will go at an angle. See if you are able to do this. See if you are able to do this, then you will notice that this is the vector that we are talking about. So this is a small magnetic field which is generated. This is a small magnetic field which is generated, and this magnetic field, if you ask me the magnitude of it, it will be mu naught by 4 pi. You have IDL as it is, and divided by R square is there over here, and here you have sine theta. But what is the angle between these two? IDL is towards you, R vector is down. So if you think about it, it's actually 90 degree. It's actually like this. It's in a inclined plane. One is here, another vector is here. So it's actually 90 degrees if you think about it. So hence sine 90, or else people take this angle and do some nonsense. No. So this is basically your dB vector. So it is mu naught I dl divided by 4 pi small r square. Now this dB which you are seeing will obviously have two components. This dB which you are seeing will obviously have two components. One component of this is horizontal. The other component of this is here. Imagine you take all such elements. Every time you take an element, this green component is always there in the same direction, but this red component once is here, once is here, here, in all possible directions. If you take the element here, that component is here. If you take the element somewhere else, you will see the component, red component will keep changing the directions, and it will be there everywhere in a circular manner. Just try to visualize this. Just try to visualize this. If you take many such components, what will happen? It will be there like this, probably. Once it will be also there here, it will be there here, it will be also there here, it will be 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 there here. It will be there equally everywhere, but this horizontal component will always be in the same direction. So doesn't it mean that all these red components will end up cancelling out each other? won't they end up cancelling out each other? Are you able to visualize this, everyone? So they will end up cancelling out each other. So the red ones components cancel, but the green ones do not. So just worry about what is this dBx. Well, if I measure this angle to be theta, this angle is 90 minus theta. This angle is 90 minus theta. This is again theta. This is 90 minus theta. And again, this angle is theta over here. So that is how the geometry works. This is 90. So theta, complementary, theta, complementary, theta. Okay. So dBx is basically dB's cos theta component. But we know that the net field will be integration of only the x components, nothing else. So it will be integration of what is dB? Mu naught I dl whole thing divided by 4 pi r square. What is cos theta technically? Cos theta adjacent by, oh, there is one small mistake. Let me rectify it everywhere. I should use different symbols, capital R and small r, or else it will create a lot of confusion. Radius of that loop versus small r is completely different things. So let's write it only separately. Okay. Cos theta is adjacent, which is basically r divided by hypotenuse, which is basically small r. Is that right? So this formula will just become r by small r. Now out of all these people, only dl is a variable, current is same, mu naught 4 pi r, everything is a constant. So put all these gentlemen outside, mu naught I r divided by 4 pi small r cube integration of dl. All of them were constants. So just put it outside, don't do anything. You might be wondering, sir, smaller, how is it a constant? Always, no matter whether you go like this, like this, like this, like this, all these distances are equal. It's like the surface of a cone. So they will all be equal. Okay. So mu naught I r divided by 4 pi. What is small r? This r, actually, if you see, it is a hypotenuse. So won't it be root of r square plus x square? R square plus x square, this is hypotenuse, if you notice. So just substitute this as your r square plus x square, root of it, that means half. But remember that whole thing is raised to 3. So just put 3 over here. So actually half because of the root, but 3 is also there. What is integration of dl? You add all the lengths, you will get the circumference. So it is nothing but 2 pi r. 2 pi r. 2 pi, 4 pi cancels. So final answer will come out to be mu naught current r square divided by 2. And then I have r square plus x square. That is your net magnetic fields derivation. That is your net magnetic fields derivation. Got it, everyone? So complex derivation, I hope I have made it very simple for you. It looks like you have to integrate some crazy stuff, but actually there was no integration involved much at all. So now coming back to this, the magnetic field, oops, what happened to this? The magnetic field on the axis is given by mu naught, if you notice mu naught is there, divided by 2. Then you have the current into r square, the whole thing divided by r square plus x square, r square plus that distance from the axis square, the whole thing raised to 3 by 2. The whole thing raised to 3 by 2. Yep. Whole thing raised to 3 by 2. This is the formula. Now this is something which you are supposed to memorize. Looks like the electric field on the axis of a ring. in electrostatics. Very, very similar. Very, very similar. Now what happens if you are at the center? If you are at the center, when I say I'm at the center, that means over here. At the center, think about it. At the center, what will happen to the x coordinate? The x coordinate will just become 0. So just substitute this as 0. Anything plus 0 is that anything. So this formula at the center, what will it be? Mu naught current R square divided by 2. R square plus 0 is R square, whole thing raised to 3 by 2, which is mu naught current R square divided by 2. 2 cancels, so it will just become R cube. R square cancels, so you will be just left with mu naught I by 2R. So that's the magnetic field at the center, guys. Magnetic field at the center of a coil. Again, a very important thing, this field will be over here. This field will be over here. These two formulas are something which you should remember. Is it absolutely clear till this point? Yep. Okay. Jasmine, we are just coming to the end of the lecture, just few more minutes. Yeah. So before the break, I think you will see the lecture only ending. Now, what happens is, see, if you have a complete loop carrying current, let's say like this, you use your right hand rule, the fingers are curling like this, the thumb is coming towards you. So at the center, the magnetic field will be like this at the center. So the magnetic field at the center will be mu naught I by 2 times of radius, where this is the radius. This is basically your radius. This is the current. But what if I don't have a complete loop? Or what if I have many loops? So you accordingly, just change the problem. Say for example, imagine it's having many turns. It's having n number of turns. If it has n number of turns, what will happen is at the center, the magnetic field will be mu naught I by 2R. Mu naught I by 2R, just multiply it with n, the number of turns that it has. It's a coil, that's it. Similarly, if it is not having n turns, rather is just can't do that here, is just an arc. Is just some arc which is carrying some current. It's just some arc of the wire which is carrying some current, and let's say this is how it is. What you will do? This arc will contribute some part of that complete circle. If it is a semicircle, it will contribute half. If it's a quarter circle, it will contribute 1/4. So it depends on what angle is there right over here. So if you try to find the magnetic field again, it will be mu naught current by 2R, but instead of the complete circle's contribution, it's a part of the circle. How much part of the circle is it? Think carefully. It will be basically theta by 2 pi. What is this? This is the fraction of the circle. Fraction of the circle. It makes sense. Example, if it is a semicircle, theta will be pi radians. So what will be theta by 2 pi? It will be pi by 2 pi, which is basically half. Makes sense. It's half of the circle. You can directly multiply it by half. You don't have to remember this formula. If it is 60 degree, what will it be? 1/6 of the circle. 60 is pi by 3. So pi cancels. Pi by 3 into half will be 1 by 6. That pi has cancelled. So 1/6. So it's 1/6 of the circle. That's it. So it's a fractional part of the circle. That's how you can solve those questions. Got it? Yeah. So these again are very, very important for you to remember. This is for n turns. This is for an arc. That's all. So there are some nice questions on this. Let's have a look over here. There is a wire which carries 12 amperes of current which is bent into a semicircular arc of radius 2 centimeters as shown. Consider the magnetic field of the center of the arc. What is the field due to the straight segment? What is the contribution of B from semicircle differs from that of a circular loop, and in what way does it resemble? Would your answer be different if the wire were bent into a semicircular arc the same radius but in the opposite way as shown in the other figure? Okay, let's do one by one. Let's do one by one. Let's do part A first. Let's concentrate on this part. What is the magnetic field due to the straight segment? Now, if you see this straight segment, this current and dl are in this direction. I am trying to find the magnetic field at the center. So this is my position vector. Can you tell me what will happen if I do the cross product of I dl multiplied by r? Why am I doing it? You might ask. It's because of Biot-Savart's law, nothing else. Just I'm trying to use Biot-Savart's law. So it has numerator I dl cross r. That's it. So if I apply that, what do you think will happen? What do you think will happen? This answer obviously will be big fat 0 because sine 0 is 0. There is 0 degrees between them. They are parallel to each other. So the straight parts, the straight wire on its line or basically axis has no contribution in the magnetic field. So even this part does not contribute over here. There is no contribution at all. Got it? So if you take any wire carrying current, you will see at this point the magnetic field will be 0 on that particular axis. Is the first part absolutely clear? Then can we go ahead? Yeah, they don't contribute. Perfect. Let's go to the second part now. The second part, B, in what way the contribution is different to the semicircle, different from the circular loop? See, semicircle means the contribution will be exactly half. So for the semicircle, if you take for the complete loop, it will be just into half. So it is mu naught I by 2r into half. This thing we have just seen right over here. If it's an arc, it's a fraction of that circle. That fraction being exactly half. So this number is very important. It is half of the circle. That is the answer for the second question. Now let's come to the third part. Would your answer be different if the wire were bent into a semicircle of same radius in the opposite way as shown? This versus this. Well, here if you curl your fingers like this of your right hand, curl your fingers like this, the thumb goes inside. That means the magnetic field was in the direction of that thumb. So that is how the field will be. Here, if you curl your fingers like this, the thumb comes towards you. That means the magnetic field will be in the exact opposite direction. So the direction has become opposite, but the magnitude obviously will remain the same. So hence that is the answer. That is exactly what they have said. Same direction, opposite direction, same magnitude. Okay, it will be half of this, and this is not going to have any contribution. So these were the three important questions, NCERT exercise 4.5. Let's go to the next question. Consider a coil of so many turns, radius, current. What is the field at the center? The moment I see turns, I remember this theory. If it has many turns, I have to use just this formula because each coil will contribute the same. So that's all. So the formula that I will be using will be mu naught I by 2 are just multiplied by n. Mu naught is 4 pi into 10 to the power minus 7 divided by 2 multiplied by the current. Current is 1 ampere. Okay. Radius 10 centimeter, which means 0.1 meter, multiplied by n, that is 100 turns. That's it. So 4 by 2 is 2. So 2 pi. 0.1 is 1 by 10. So it will become 10 to the power minus 7 into 10 into 100. This will become 10 to the power 3. And this is minus 7. So it will become minus 4. So this many Teslas. So 2 pi 10 to the power minus 4 Tesla. Yeah, 2 pi 10 to the power minus 4 Tesla, which is 6.28 10 to the power minus 4 Tesla. Perfect. That is how you do it. Just that this number n has come in play. That's all. Cool. Everybody with me? Awesome, guys. Awesome. Right? Okay. Let's start. Welcome aboard. Welcome aboard, everyone. Okay. So now, see, in the chapter of electrostatics, what we had was Coulomb's law. And then we also had Gauss law. If you remember, Coulomb's law was helpful when you had point charges, etc. Gauss law was helpful when there was symmetry to find out the electric field. You have seen applications like a long wire which is charged, what is the field around it? Or a shell or a sphere. How to use Gauss law for symmetrical bodies to find the field. Coulomb's law is used for point charges or rings and stuff like that, where it becomes easier to find the field. From this you can get this, from this you can get this. These both are dependent on each other. Same thing happens even in magnetism. We have just studied nothing but our Biot-Savart's law. This law is, like I showed you last time also, is helpful for elemental currents. If you remember correctly, it was good for elemental currents and how to find the field due to that. You take an element of the current, what's the field, which is very small, dB, due to that, and you can add them up to find out the net magnetic field due to all the current carrying elements. So is there a law which is like Gauss law but in magnetism? Something like Gauss law but in magnetism, which helps us for symmetrical geometries? The answer is yes. That is called as your Ampere's law. From Ampere's law you can get Biot-Savart's law. It is dependent, and so is this. They both are dependent on each other. Just like this is used for symmetrical bodies by choosing a closed surface, here it is used for symmetrical bodies in general, but instead of a closed surface you choose a closed loop. So there is always some small difference, like, it's same but different. So just like in electrostatics you had permittivity, in magnetism you have permeability. If permittivity was 1 by 4 pi epsilon was their denominator, in magnetism it was permeability which was there in the numerator. It became mu naught divided by 4 pi. So similarly, if there is Gauss law kind of a thing in electrostatics, which is for a closed surface, you had enclosed charges. This is for a closed path, and you will have, instead of closed or enclosed charges, you will have enclosed current. So that is what Ampere's law is all about. So there is an alternative in which Biot-Savart's law may be expressed, and Ampere's circular law considers an open surface boundary. When the surface has a current passing through it, consider the boundary to be made of number of small elements. So this is basically an alternative appealing way. Why they said appealing is because it is easier for symmetrical geometries. Instead of Biot-Savart's, therefore you use Ampere's law. Okay, and they have explained what the elements etc. are, and finally they have given the Ampere's law right over here, which is integration of B dot dl is mu naught I, and okay, so that's what they have given, where I is where I is the total current through the surface. All right. This is the loop integral. Loop integral is B dot dl, and the direction of the thumb gives the sense in which the current I is regarded as positive. For simplified version proves sufficient, okay, and all these things they have mentioned over here when there is a system, okay. So let's talk about what is Ampere's loop law. Say for example, you have a wire which carries some current, let's say I1. There is another wire which let's say carries current I2. Another wire over here carries current I3. Another wire over here carries current I4. Another wire which is over here, let's say, carries current I5. All these are random wires randomly placed here and there, carrying currents of different amounts in random directions. Now, around it, there will be a total magnetic field. Each wire will produce its own magnetic field. So, there will be magnetic field around those wires. So, let's say you are somewhere, maybe over here, and you note down what is the magnetic field, and what you do, you keep on traveling maybe around these wires, and you come back to the same point. As you travel and you come back to the same point, this entire closed path, this particular closed path, any such closed path is also called as an Amperian loop. It is called as an Amperian loop. So if a dog runs and comes back to his owner, so the path which the dog takes is called as an Amperian loop. You go to the school and come back to your house only, that path which you have taken, complete path, is again an Amperian loop because you have come back to the same point. Okay, fair enough. Now, once this is done, what you do next, at every single point, try to figure out what was the magnetic field and take the dot product of that magnetic field with the displacement that you undergo. Let's say that displacement is dl. So, you are taking the dot product of the displacement with the magnetic field. You go to the next point, there will be a new magnetic field, and take the dot product with the displacement there. So at every single point, there will be a new magnetic field, there will be a new displacement, and you keep doing the same thing, throughout that particular loop for all the points, B dot dl, B dot dl, B dot dl, B dot dl, and you add them up, because there will be many such points. In fact, a line is made of infinite points. So you're adding up infinite numbers, but each number is a very small value. So such a thing is nothing but called as an integration. So therefore, summation same as integration. Summation and integration means the same thing. But since you came back to the same point, that is why I will use this symbol. So this is a closed integral, but I am integrating not with respect to area, I am integrating it with respect to the length or the path or a line or a curve. So that is why this is called as a closed line integral. But this is of whom am I integrating with the rest of the magnetic field. Why closed? Because I came back to the same point. Integration because I am adding up. Line because there is a dl. Whom am I integrating? Magnetic field. Is this clear, everyone? Till this point? Okay. Now, when you do this, what you get on the right hand side is very important. What you get on the right hand side, you basically get mu naught, which is permeability, into a number. Now, what is that number? Let's understand it. This was the closed path. So imagine a film, soap film, which is enclosed by that line integral. Imagine a soap film. Imagine you take that path, you dip it in a soapy liquid and take it out. A soapy film will be formed, thin layer will be formed. and that is how you can visualize which currents are cutting through, are piercing through that particular, soapy film or that, Amperian loop. So these currents are basically the currents passing through this imaginary path. These currents are also called as enclosed currents. Why is I-phi not an enclosed current? Because it never pierces this particular thin film or this passes through inside that particular path. Even I4 is an outside current, it is not piercing through it. I1, I2, I3 are piercing or through that film, or they are passing through that particular, Amperian path. That is why they are called enclosed currents. So I will put over here currents enclosed. This is basically called as your Ampere's loop law. This is basically called as your Ampere's loop law. Is everybody clear till this point? Give me a thumbs up if you understood it till here. Okay. Now, please remember over here, this magnetic field is due to, this particular magnetic field is due to both, inside as well as outside currents. Inside as well as outside current, not just because of outside or not just because of inside, but the value of this integration is only because of the enclosed currents. Now you might be wondering, what is the value of this enclosed current in this particular case? What is the value of this enclosed current in this particular case? A lot of you might think, sir, I1 is there, sir, even I2 is there, sir, even I3 is there. So I1 plus I2 plus I3. That is not correct actually, because even these currents have a sign. Now you might be wondering, sir, what is the sign of this? How is current given a sign? Very straightforward. Take your right hand, take the fingers of your right hand and go in the same way the loop has been covered. I am going across the loop like this. So curl your fingers of your right hand, exactly in the same direction. Okay, in the sense in which you are covering the closed path. Then what happens is the thumb exactly points in the positive direction of the current. So if you notice, the thumb is going up, so I1 and I3 are positive. So I1 and I3 are basically positive currents. I1 and I3 are positive currents, but I2 is going down, so that will be considered as a negative current. So you use your right hand thumb rule to figure out which current is positive direction and which current is negative direction. I hope this is absolutely clear. Yep, very, very important. So that is exactly what they have mentioned right over here. They are finding the magnetic fields at all the points. They are multiplying it with the, or taking the dot product with the length, and then they are adding it all together, and then they are adding many elements. So it is integration, but since they are coming back to the same point, it is called line integral. It is called as line integral of the magnetic field. They have also mentioned the direction of the thumb gives the direction of the positive current. That is what they have mentioned. Okay. Now they have also given a simplified version of the magnetic, the Ampere's loop law, but that is not needed actually most of the times. All right. They are told B into L is equal to mu naught into current. Don't worry about it so much. That's simplified version. So I'll just explain to you what that simplified version is in a bit. Hold on. And then they derive the magnetic field due to a long wire which is carrying current. Okay, so they have derived the magnetic field due to a long wire which is carrying current. So what do they mean by this? See, if you take a long wire like this, if you take a long wire which is basically carrying current, and I want to find out the magnetic field at some distance from it. I want to find the magnetic field at some distance r from it. So what I do is I can use Biot-Savart's law. Second option is I can use Ampere's law. Ampere's law will be beneficial because it will simplify your problem. How? Let's observe. Due to this current carrying wire, the magnetic field lines will be circular in nature. Everybody agrees with this statement. The magnetic field lines will be definitely circular in nature around this particular thing. So there will be some magnetic field lines like this maybe. There will be some more magnetic field lines like this maybe. Then a magnetic field line exactly passing through that particular point, maybe somewhere over here. So this is how the magnetic field lines will look like around that wire which is basically carrying current. Around this particular wire which is basically carrying current. Okay. Now, in order to find how much this field is at any distance r, obviously as r increases, the field strength will reduce. I will choose an Amperian path now. I will choose an Amperian path or Amperian loop. Amperian path means I should come back to the same point. So I will start from here. I will go exactly around this particular wire along the magnetic field line. You will see why that is beneficial for me. I will complete my path by coming back to the same point. So that is my Amperian path. So what happens is, because of that, at every single point, whatever my displacement is exactly in the direction of the magnetic field. Displacement is in the direction of the magnetic field. So because of that, what happens is, if anybody does magnetic field dot the dl vector, the answer to that will be A dot B is A into B into cos theta, in this case cos 0. Why? They are parallel to each other, and cos 0 is basically 1. So hence I'll be just getting B dl. B is magnetic field and dl is basically that small length. Everybody clear till this point? Everybody clear till this point? Because cos 0 will be just 1. Okay. Next important thing is, if I apply Ampere's loop law, which is nothing but integration of B dot dl is equal to mu naught into whatever is the current which is enclosed. This B dot dl will be just B dl. That means that B will be constant, it will come outside. Inside the integration, I will be just left with dl. I'll be just left with dl. What happens in the next step? Think about it. If I add all the small lengths and come back to the same point, I'll get the circumference of this Amperian path. I'm just adding all the lengths and I'm coming back to the same point. It is circumference, and circumference of a circle is nothing but 2 pi r. So basically the LHS becomes B into the length of the path. This will just become the length of that particular path. That is what the LHS becomes. That's exactly what they have told over here. BL, that is what the left hand side becomes in a simplified version. Are you able to see that? B into L. So for a simplified version, the left hand side becomes equal to magnetic field into L, where L is the length of the path. L is the length of the path. That is exactly what has happened on the left hand side of the Ampere's loop law. Cool? Okay. So that length of the path in this case is 2 pi r. Alright. The magnetic field is as it is. If you talk about what is happening on the right hand side guys, right hand side, what is the current which is passing through that Amperian path? It is only I. So only I will come over here. So hence rearranging, I will get magnetic field as mu naught current, this divided by 2 pi and r. That's the answer. That's the magnetic field at some distance of r. Okay, mu naught I by 2 pi r. If you remember, for a circular loop, it was mu naught I by 2r. Let's go back and see that. Formulas look very similar, same but different. Just for a circular loop at the center, it was mu naught I by 2r. There is no pi here. Be careful about it. There is no pi here due to a circular loop. Remember, circular loop at the center. The magnetic field was mu naught I by 2r. Now this is magnetic field due to a long wire, and that is mu naught I by 2 pi r. Is this absolutely clear? A small difference over there. Correct. So this is a beautiful application of how, without actually integrating, you have found the answer in a much easier manner using Ampere's loop law. Okay. So guys, if you are loving all these derivations, I hope you are liking the session. If you have not liked the button, please do that. That is your Guru Dakshina, or else whatever you learn will never enter your head. You should always give Guru Dakshina, no matter YouTube, physical class, online class, this, that, should always be grateful. Okay. This quality content which I am getting for all of you, so which is made easy, decoded, NCERT line by line by your Capto. Okay. Now they are telling that there are some interesting things about the infinite wire, which we just did. This is an infinite wire. It implies the field at every point on the circle radius r is the same magnitude. In other words, the magnetic field, possesses what is called cylindrical symmetry, which is normally dependent on 3 coordinates, one r. Whenever the direction is symmetry, solution simplify. So they are saying about cylindrical symmetry, which makes sense. Just look at it. The magnetic field lines are concentric circles. Below this also there will be concentric circles. Below this also there will be concentric circles. You can see they form cylinders. So that is why they are saying cylindrical symmetry. Anywhere you go at the same distance, here or here or here, as long as these distances are same, the field is the same, and that is the reason why we were able to so easily do this problem. They are telling why the problem was easy. So the solutions were simplified because of this symmetry. The field at any point on the circle is tangent, thus the lines of constant magnitude of the field form concentric circles. The constant magnetic field lines form concentric circles. The iron filings are also in the concentric circles. These lines are called as magnetic field lines from the closed loops. This is unlike electrostatic field where they originate from positive and end at a negative charge. The expression for magnetic field which was provided provides a theoretical justification of Ørsted's experiment. Now, if you notice in this particular paragraph, they are telling how magnetic field is different from electric field, and this is exactly what Ørsted had told. So if you notice, these magnetic field lines are circular. So if somebody sprinkles iron filings which are themselves magnetic in nature, they are also going to be in concentric circles because they will align themselves, because they will be affected by the magnetic field. So they will also become circular. These iron filings will feel like as if they are, around that current carrying wire in concentric circles, which is justifying Ørsted's experiment. If you had forgotten, we have done this at the beginning of the previous lecture. Current carrying wire deflects any magnetic material, and if you sprinkle some iron filings, this is how the iron filings look like. It just proves exactly the same point, that magnetic field lines are circular along the tangent. They go around in loops rather than starting at some point and ending at some point. That is also something which I had mentioned in the previous lecture. They don't originate or terminate. They will be always in the form of closed loops. Everybody with me on this? Shall we go ahead? That is the second pointer. So it's like a summary of whatever we have done till now. Another point to note is that even though the wire is infinite, the field due to it is at a non-zero distance is not infinite. It tends to blow up only when we come very close to the wire. The field is directly proportional to the current, and the field is directly proportional to the current and inversely proportional to the distance from the current source. Now, this is also very interesting that somebody might say, sir, this wire, sir, was infinitely long. So the wire is infinitely long. So the current should also produce infinite magnetic field. That's not true. See, in this region, these currents will affect and create magnetic field. But these currents here, here, they are very far away. They will have negligible effects. So even if the current extends till infinity, this will have hardly any effect over here. So don't worry and think that, sir, if it is infinitely long, it will produce infinite field. No, the far away elements have negligible contribution in that. Okay, the closer elements have significant contribution. It's like saying people around you are paying you 100 rupees, 200 rupees, 500 rupees, 700 rupees, and the faraway people are not even paying you 1 rupee, they are paying you 0.1 or 0.01 rupees or 0.005 rupees. So you will ignore them because it's not going to add to your richness or your wealth. Making sense? So that's why we do not count it. That is exactly what they have told. And yes, magnetic field is proportional to the current and inversely proportional to the R. So if you go far away, the field will reduce. It will only become infinite in one case, when you become R as 0 or you are very close to the wire. That means you are somewhere here. That means when you are somewhere here, then the field will tend towards infinity. In fact, if you draw the graph of the magnetic field versus the distance, that graph will look something like this. The farther you go, field will reduce. The closer you come, the field will become extremely large. That is what the third point says. There exists simple rule to determine the direction of the field. This rule is called right hand rule. Very simple again, right hand rule. They say that grasp the wire in the right hand with your extended thumb pointing in the direction of the current. Your fingers will curl around the direction of the magnetic field. What it means is, say for example, I will hold a wire like this. Just trying to make it look as real as possible. This is a wire which carries current such that our thumb of the right hand is pointing exactly how the current is moving. If the current is going like this, our thumb also points in the same direction. If the current was going down, I will hold the thumb like this, the fingers will go the other way around. So whatever direction my fingers curl, exactly that's the direction of the magnetic field. If the current was going down, then the fingers will curl like this, then the magnetic field will be this way. Got it, my dear warriors? That's the simple way of determining the direction of the magnetic field, clockwise or anti-clockwise. Easily we can get it. Clear, everyone? Very good, Bhuna, Krishna, Madhumati, Sivali. Everyone with me on this? Right. Great. Now, they have told that Ampere's law is not new. They both are related to each other. Okay, I think this particular thing is related to this particular statement which I mentioned here. Coulomb's law depends on Gauss law. Gauss law depends on this. If this is not valid, even this is not valid. Same way, if this is not true, this won't be true. If this is true, this will be true. They both are basically different ways of approaching a problem. This is used for different geometries. This is used for symmetrical geometries, just like over here. And then they have given an application of Ampere's loop law right over here. It shows a long wire which is carrying current. It has a circular cross section and it is distributed uniformly. Calculate the magnetic field below A and above A, where A being the radius. Let's understand what this problem exactly means, and then they have solved it. This by far is one of the most important problem of NEET, because they have asked this question almost every year in the last couple of years. this particular question, and the graph, the formula, the problems, almost every last couple of years they have asked it. See guys, imagine there is a wire like this, okay, and this particular wire has a radius A, has a particular radius A. So if you look at it in 3 dimension, it will probably look like this. Okay, it might be carrying some current like this. This is that particular radius. It's a long cylindrical wire. Usually our wires are thin, but that thin wire will also, even this pen also has some thickness. It also has some cross section. Now, if you hold the thumb in the direction of the current, you can see the fingers are curling like this. Hold the thumb in the direction of the current. You will see the fingers are curling like this. That means around this, there will be magnetic field lines in this particular manner. So definitely there will be magnetic field lines around it like this. Even here. Not just that, even inside of this, there will be magnetic field lines. Even inside of this, there will be magnetic field lines. Yep. So there is magnetic field around the wire, not just outside but inside. The outside part, we have already done it. Yep. The outside part, we just figured it out. This is outside the wire. What is the magnetic field? But what is it inside? What is it inside? That is what you might be wondering. That is what you might be wondering. So, exactly that is our question. R more than A is already taken care of. This is when you are outside. Okay, check the previous slide. Check the previous slide. Definitely this was done. This part was done right over here. Right over here. This is the formula. Mu naught I by 2 pi r, where r is the distance from the central point or the central axis. Now the question is, what will it be inside? That is what our primary concern is. So now for finding that out, okay, I don't need this anymore. I will just draw a few loops here and there, magnetic field lines. This is how the magnetic field lines will be, circular in nature. Let's assume that the current is going inside. If the current is going inside, it will be going in everywhere. It will be going in here. It will be going in here. So basically the current is going inside the plane. That is the reason why then the magnetic field lines will be clockwise. You can see that the magnetic field lines will be clockwise in nature like this. Clockwise in nature like this. And I want to find it at any distance r. So let's just say this is that r distance at which I want to find the magnetic field. This is basically your r. Okay. Now at that particular point, obviously the magnetic field will be tangential to the circle. So the magnetic field will be always like this, correct? So that is your magnetic field vector. Everywhere it will be tangential along the circle. So I will choose my Amperian loop smartly by moving around that circle, because I know if I move around that circle, exactly the same thing will repeat over here. B into length of the path. If I make sure B is along the length that I travel, cos 0 will be 1 and the left hand side will be exactly this. isn't it? The left hand side will be exactly this. So I will choose a smart Amperian loop, and that smart Amperian loop will be basically going around exactly the same magnetic field line. So this is my Amperian loop. I will go exactly like this, and that will be my DL vector. DL and B are parallel. That is my Amperian loop. Amperian loop. So the left hand side of Ampere's law will just become magnetic field multiplied by the length of the path. The length of this path, because the radius will be r, distance was r, so it will be nothing but 2 pi r. So 2 pi r into b will be the left hand side of the Ampere's loop law. Everybody fine till this point? Clear? What's the left hand side? What about the right hand side? What about the right hand side of the same thing? What about the right hand side of the same thing? So let's try to do that. So what about the right hand side? Right hand side of Ampere's law. Now that is going to be slightly tricky. You have to just figure out what is the enclosed current. Realize one thing, only this much current is enclosed. This current so this current should not be even counted. I hope you see that. Only the current here should be counted, the outside current should not be counted. So how do I do that? How do I find the current which is passing through it? Yeah? Capto, please explain the tangent part once. Okay. See, like this, the magnetic field lines inside, where is it? So this was our wire, right? The magnetic field lines will be like this, concentric circles. The magnetic field lines will be concentric circles. So if I draw tangent to any field line, what does it give me? The direction of the magnetic field. If I again draw tangent here, it gives me the direction of the magnetic field. If I draw tangent here, it gives me the direction of the magnetic field. If I choose my Amperian loop also exactly along that magnetic field line, everywhere my magnetic field is parallel to the Amperian path. Everywhere the magnetic field is parallel to the Amperian path. So the angle between them is 0. Because the angle between them is 0, that's why it will become a very simple term, b into the length of the paths. Is that okay? So I've just gone around it in a circular path along the tangent. The reason why I went along the tangent is because field, dl, everything will be parallel at every point. So the cos 0 will become 1. Cos 0 will become 1. What am I talking about? Cos 0 becoming 1? This one. The angle between them being 0, cos 0 will become 1. So it becomes a simplified equation. So this is your simplified equation. This is your simplified equation. Cool till this point? Krishna, is it clear? Okay. Now coming back to the right hand side, what is the enclosed current? It is clearly mentioned that the current is distributed equally. So if the current distribution is equal, current distribution is uniform, it means that the current which is there per unit area should be basically the same everywhere. If you take any one unit area, whatever current passes here versus passes here versus passes here should be the same. So current per unit area will be the same. So if you see the total current of I passes through this entire area, which is going to be pi into basically a square. But the enclosed current, I enclosed, is only through this much So that will be having an area of pi r square. So these both should be equal. Current per unit area should be the same. Clear? Now, therefore, pi will cancel. What will I get as the enclosed current as? I will get it as I into small r square by a square. I into small r square divided by a square. So the right hand side will just become mu naught into I enclosed. So that I enclosed itself will just become I into r square divided by a square. So that's it. That will give me the final formula then. That will give me the final formula. So combining LHS equal to RHS now. So if I do LHS equals to RHS, okay, if I do LHS equals to RHS, where did it go? Yeah, LHS was B into 2 pi r. LHS was nothing but the magnetic field multiplied by your 2 pi r. RHS is nothing but your mu naught into enclosed current, which is I r square by a square. So therefore, I will get the magnetic field as mu naught current. R got cancelled, 1 r will remain, 2 pi will go below, a square will remain below, and then you just have r over here. So this is the magnetic field. This is the magnetic field formula that we are getting. Inside this is mu naught I r by 2 pi a square, slightly different from this mu naught I by 2 pi r. Here instead of r below, it is gone on the top, and then there is a square over here. So from this, we figure out that if you are inside, the formula is mu naught I by 2 pi a square into r. If you are outside, the formula is mu naught I divided by 2 pi r. Here it is proportional to r. Here it is inversely proportional to r. So basically, if I show it graphically, on the horizontal line is the distance, on the vertical line is the magnetic field. As long as you are inside, the magnetic field will be proportional to r, that means a straight line. But after that it goes down like this, and this point is exactly A. So this is the maximum field that you get, and this is at the surface. You get it maximum, and after that it is inversely proportional to that. Is this absolutely clear, everyone? Okay. So very, very interesting problem of going inside. There are magnetic field lines inside also, outside also. So for finding it inside, we take a small loop inside the cross section of that wire, apply Ampere's loop law, and we get this formula. Outside we had already figured it out, and it's exactly the same thing you will see even over here. They have done the same thing, and you can see the same graph is right over here. Okay, clear guys till this point? Now let's go to the solenoid, which is there over here, solenoid diagram. But before going to the solenoid diagram, let's solve a simple question on this. A cylindrical long wire carries a current I, and the cross section has a radius capital R. Find the ratio of the magnetic field at a depth of r by 3 versus outside from the surface at a distance of r by 3. Very interesting question. Let's try to understand this. Read the question again. Just check this out. Okay, just read that question. You are at a depth of r by 3 from the surface versus at a distance of r by 3 from the surface outside. And you have to find the ratio of the magnetic fields. Okay, fair enough. So what I will do first, okay, let me just get rid of this statement. I understood what the problem is. So let's just say that this particular radius is nothing but r, which is the radius of the cross section. You are once inside, once you're outside, which means, understand this, once you're inside at a distance of r by 3, that means from the center, your distance will be r minus r by 3, which is 2r by 3. This is basically going to be 2r by 3. Depth is r by 3 from the surface. That means from the center. This is from the center. Your distance is 2r by 3. Same way, when you are outside at a distance of r by 3, that means from the center. Again, from the center. This is r by 3. Your distance will be r plus r by 3, which is basically 4r by 3. I need these things without which I can't find the field, because all the field formulas are measured from the center. Mind it. So when you are inside, the formula looks like this: mu naught I divided by 2 pi. Radius is r square, and distance from the center is just proportional to it. So here our small r is basically 2r by 3. Rest of the things as it is. So r cancels and you will get mu naught I. 2 also cancels by 3 pi r. Mu naught I by 3 pi r is what is inside at a depth of r by 3. Till this point, is it clear? Everybody with me? Okay. Now let's go outside and see what the formula will be like. When you're outside, the formula changes to mu naught I by 2 pi r. So remember, we are just using this. When you're outside versus inside, right? So when you're outside, the radius of the wire does not even matter. So this small r is basically 4r by 3, distance from the center. So mu naught I by 2 pi into 4r by 3. So 3 goes on the top. So 3 mu naught I, 4 2s are 8. So 8 pi r. That's it. Now the final answer is finding the ratio. So magnetic field inside versus outside. Many terms are common. Mu naught I, pi r, everything is common except for this number 1 by 3 and this number 3 by 8. So 8 will go on the top, 3 3s are 9. So the answer is 8:9. So the answer is 8:9. Got it, guys? How to use and apply it in the problems? This is by far the most important concept, you can say, in the application of Ampere's loop law. Many times this question and this graph or even this formulas have come. So please read it properly. Okay, very, very important. I hope you now understood how to apply these formulas. All the times, make sure that you are measuring the distances from the center, not from the surface. Else you'll get a completely wrong answer. Yep. All right. Next is a solenoid. Now, what is a solenoid? Solenoid is nothing but, imagine you take a cylinder, something like this. Now you can see this bottle is like a cylinder, and you wind a coil across it. This turn is in this plane, then here, then here, then here, then here, then here, and you make many windings across this, cylinder. This device is then called as a solenoid. When you pass current, it will produce magnetic field, something like this. So you can see there are many turns. It will produce magnetic field like this. So it will behave like an electromagnet. It will have magnetic properties. It will have north pole and south pole, and that is exactly what a solenoid is. We mean that solenoid's length is large compared to its radius. That is the meaning of long solenoid. It consists of long wires which are wound in the form of a helix, where there is neighboring turns are closely spaced. So each turn can be regarded as a circular loop, and the net field is the sum of all the fields, and they are used as basically electromagnets. And then we have been asked to find out what is the magnetic field due to such a long solenoid. They have done this small derivation over here. So we'll just figure out how they have done this derivation. All right. So done this particular derivation over here. So let's figure this out, how they have done this. All right. So starting off in a very simple manner, guys, observe this. I will explain everything very simply so that you will never be confused. This is a short solenoid. This is a long solenoid. This is a long solenoid. The difference is only how the magnetic fields will approximately look like. Here, the magnetic field lines will look like this, maybe. This is the north side, this is the south side. North because it's coming out, south because it is coming in. Whereas in this case, it will look something like this. So like you can see, the difference is how the field lines are in most of the solenoid. How the field lines are in most of the part of the solenoid. Here you can see the magnetic field inside is non-uniform. Is non-uniform. Very, very important. It is not constant throughout. Here it is weak, strong, strongest, strong, weak, weaker, and it keeps on diverging or converging. Whereas over here, you can see that the magnetic field inside is roughly constant, or basically it is nothing but uniform in nature. It is just uniform in nature. So that makes a huge difference, and we basically study long solenoids where the length is much larger as compared to the cross section. Not just that, you will also notice one thing. These same magnetic field lines, now they will go like this. They will go probably like this over here. So as you go anywhere outside, let's say here or here or here, you will see that they are hardly close to each other. So as compared to this, the magnetic field outside is negligible. This is very important assumption which comes only for a long solenoid. So these assumptions play a very important role for our further calculations. So inside the magnetic field is constant and outside the magnetic field is negligible. Is this clear, everyone, till this point? Okay. Very good. Very good. Okay. Now, in order to find that out, what I will do, I'll just take a small part of the solenoid. I'll just take a small part of that particular solenoid. So this is the cross-sectional view. So let's just focus our attention on a small part of that large solenoid. Forget the ends because most of the part of the solenoid, the magnetic field lines are uniform. So what you will see is in this part, the wires are going in, they are coming from behind and coming out from here. They are going like this, going in, coming back from here, again over here. So if I show the currents, these currents will be going in over here. These currents will be going in over here. And they will be coming out from here. These are windings, these are coils which are wound on that solenoid cylinder. Okay, circular coils adjacent to each other. They are tightly wound. They are very close to each other. This is how these crosses and dots represent wires going inside versus wires coming outside. They are all carrying the same current I. Okay. Now what I will do in order to find out the magnetic field, first of all, let's imagine those magnetic field lines. They will be something like this. It will be, remember, uniform inside, roughly they will be constant everywhere. Yeah. Okay. Outside there is no magnetic field, so don't have to worry about it. I will choose an Amperian path which looks something like this. Very interesting Amperian path, guys. This is my new Amperian path. Amperian path to find out what's this value of the magnetic field right over here. This Amperian path, let's say it has a length of L and this width is H. This is H, this is L. It's like a rectangle. I start going like this, go here, come back to the same point. Come back to the same point. Okay. Now, next step, let's apply Ampere's loop law, nothing great. Let's apply Ampere's law and see what exactly happened. The left hand side we know is integration of magnetic field with respect to length. The right hand side will be just mu naught into the current enclosed. Because there is one length here, one length here, one length here, one length here. Maybe I can divide it into 4 small parts. Part number 1, part number 2, part number 3 and part number 4. So I can split it up into 4 parts. So integration plus integration plus integration plus integration. This is for part 1, this is for part 2, this is for part 3, this is for part 4. This is equal to mu naught into enclosed current. For the first part, magnetic field and the length are in the same direction. So think about it. Magnetic field dot dl, and this will be nothing but cos 0. For the second part, magnetic field is perpendicular to the length. So it will be b dl cos 90. For the third part, there is no magnetic field only. So it will be 0 vector dot dl. Magnetic field outside, remember, was a big fat 0 vector. I just told you over here, outside there is no magnetic field. So for the third part, this integration will definitely become 0. Again, when you start coming in, magnetic field is perpendicular to the length. So it will be b dl cos 90. And don't we know what cos 90 is? This cos 90 is nothing but 0. Even this cos 90 is nothing but 0. So this is 0, this is 0, this is 0. Only this term remains. So there will be basically 3 zeros, 0 plus 0 plus 0. Only this term remains. B comes outside. It will be just integral dl for that first part. Integral dl for the first part. So dl plus dl plus dl plus dl plus dl plus dl till here will be the total length of it. So it will be just this L and B into L on the left hand side. So that's what the LHS would look like. Everyone clear how we have used Ampere's loop law for the left hand side right now? They have not yet solved for the RHS. This is only the LHS. Yep. Now let's go to the right hand side. Enclosed current. Be careful. Enclosed current means only this much. Only how much is enclosed over here. Oh, I need a parameter of this solenoid, And there is a very important parameter of a solenoid which is called as the number of turns per unit length. This is how many turns are there. This is basically how many turns are there upon the length of the solenoid. Upon the length of the solenoid. This is small n, this is number of turns, and this is the length that you have considered. This is again a very important formula which is generally given to you. This solenoid has 1000 turns in 1 meter. So very tightly wound. This solenoid has 3000 turns in just a meter. So very, very tightly wound. So number of turns per unit length is small n. Total turns is n. The length which is considered is basically L. This will help me find out how much current is there over here. So think about it. There is current I. There is current again I over here. Again current I over here. Like that, there will be so many currents. How many such currents will be there? 1, 2, 3 till basically n. So the total current which you are talking, which is like enclosed current, will be nothing but I enclosed. This particular I enclosed. Won't it be I into I, sorry, I multiplied by n times? I plus I plus I plus I. How many times? N times will it be there? Everyone fine till this point? But what is n? What is n? N will be small n into L. Small n into L. So therefore, won't this be small n multiplied by length L? So just put that over here. I into n into L. So mu naught small I into n into L. Obviously what happens is this length and this length gets cancelled, and I am just left with magnetic field inside is mu naught small n into the current. That's it. That is our formula. That's exactly what they also would have got. Mu naught Ni. Yes. See this? Mu naught Ni. Is this clear? Everyone? How we got this? Very, very important. Shall we go ahead? Yeah. So you should remember this formula. Permeability into number of turns per unit length into current is the magnetic field inside. Outside, like I said before also, there is no magnetic field for a solenoid. So I think the question slide is missing somewhere. But anyways, let's go directly to the question. This is a NCERT exercise. A solenoid of certain length has a radius of 1 centimeter and is made up of 500 turns. It carries a current of 5 amperes. What is the magnitude of the magnetic field inside the solenoid? That's the question. That's the question. Let's do this. The number of turns per unit length is given, okay, or if we have to find it out, current is given, find the magnitude of the magnetic field inside. So you just have to use the formula B is equal to mu naught Ni, but N is not known. So how do you find the number of turns per unit length? Radius, I think this is useless information. Length is useful and number of turns is useful. This piece of information is useless. What will I do with the radius? What will I do with the radius? It is not needed only to the problem. So 500 divided by 0.5 will give me 1000 turns are there in a meter. Next, magnetic field is mu naught Ni. Mu naught is 4 pi 10 to the power minus 7. Number of turns is 1000 and the current, which is I, is given to be 5 amperes. That's it. It's multiplied, you get the answer as 6.28 millitesla. That's the magnetic field inside. Outside, naturally, it will be 0. The only job of the radius over here is for you to visualize. Radius is 1 centimeter, length is half a meter. So it is, yes, a long solenoid, which means the formulas that we derived over here are valid. Because all these formulas are only for long solenoid and you do not get short solenoids in your NEET examination. Is that okay? That's the significance of that radius. Otherwise, it was not used at all in the calculations. Yep. Shall we go ahead to the next concept, guys? And that is basically force between the parallel wires, and then we'll come to the torque part of it also. Shall we do this? Where is it? Yeah, force between wires carrying current. Start reading this, and meanwhile I'll also drink water. Thank you for reminding me. Okay, let's do this. See, if you have a wire which carries current, obviously it produces magnetic field around it. We also know if a wire is placed in somebody else's magnetic field, it experiences force, IL cross B. So if I have two wires nearby each other, this guy will produce a field, this guy will be affected by the field. Not just that, even this guy will produce a field and this guy will get affected by it. So basically, two wires carrying currents, if they are placed near each other, what will happen? They will exert action reaction forces, Newton's third law. They will exert magnetic forces on each other. They might end up attracting or they might end up repelling each other. So we are interested in calculating how much this force is. We are interested in calculating how much this magnetic force is. Okay. So basically, yeah, we have learned that there exists magnetic field due to current carrying wire. Further, we have learned external field will exert force. So these were the two initial statements. Magnetic field is there due to a current carrying wire. Also, external magnetic field will exert force on a current carrying wire. So from this, it is expected that two current carrying wires near each other will exert magnetic forces on each other. This is what we are interested to study. And then they have done this calculation part, and then they say this is also used for defining Ampere's loop law and all of that. So we'll come to it. Let's understand it first. Okay, let's draw two wires, guys, first. Let's draw two wires. This is one wire, and this is another wire over here, placed at some distance from each other. Let's say that distance is basically D. Let's say this wire carries current I1. Let's say this wire will carry current I2. Now you can do the same logical thing when the currents are not in the same direction. Maybe like this. They are opposite to each other. Now they are same direction. So each wire will produce a current, will produce a magnetic field around it. So let's say the magnetic field produced by this wire will be like this. Try to visualize this now. Something like this. If the current is in this direction, the magnetic field lines will be like this. So if I probably show it at the right place. Okay. Now, obviously the magnetic field lines will be like this. Magnetic field lines will be like this using right hand loop law. And you can see the current is here. The fingers are curling this way. So at this point on the second wire, the magnetic field line is basically going downwards. So this is the basic direction of the magnetic field at this particular point on the second wire. This magnetic field is given by mu naught, current number 1 has produced it, divided by 2 pi distance. Distance is nothing but d. That's the magnetic field. Now please remember, this magnetic field is definitely perpendicular to the length of this wire. Okay. So if you ask me how much is the force, I will use IL cross B. Length is here, cross product it with the magnetic field. Length cross B will go this way. That means my force will be like this. That means my force will be like this. Do not forget that our force is given by current which is going, which is basically in this case I2, into the length which is, let's say, L, and cross producted with the magnetic field of this guy. So cross B, IL cross B. So if you ask me how much is this force, magnitude wise, current is just I2 only, there is no change in that. Length is, let's say, L. Magnetic field, I just figured it out right over here, which was mu naught I1 divided by 2 pi d. Shift the length below, shift that length below, I will get force per unit length is nothing but mu naught I1 I2 divided by 2 pi d. Divided by 2 pi d. That's it. I have got the force per unit length. If you do the same analysis for the second wire, which is also producing magnetic field again, and then you find the force on the first wire, it will be exactly in this direction. It will be exactly in this direction. Obviously, these two forces will be equal. This force per unit length on both, basically both are equal. They are equal and opposite. This is using your third Newton's law of motion. Newton's law of motion. If the direction is same, it is attractive. Naturally, if the direction is opposite, what will happen? It will be repulsive in nature. So the forces will try to repel the currents. So same will attract, opposites will repel. Exactly opposite of electrostatics. Exactly opposite of electrostatics. Not just that, if I play around with this, F by L is again mu naught by 2 pi I1 I2 divided by 2 pi d. Say for example, if I rearrange this and I write I1 I2 as F by L, I1 I2 is F by L, and then I write 2 pi d on the top divided by mu naught. Mu naught is nothing but 4 pi into 10 to the power minus 7. This will cancel, this will become 2. So I'll just get F by or Fd by L multiplied by 2 into 10 to the power minus 7. Now this helps me define something called as the unit of current. If you remember, SI unit of current is amperes, and amperes is a fundamental quantity. Charge is not, charge is the derived quantity. So this is used to define the ampere, which is one of the fundamental quantities. That is what they have told. This is used to define ampere, which is the base unit, the fundamental quantity. And like I said before also, parallel currents will attract and anti-parallel currents will repel. Okay. This is exactly opposite in electrostatics. Same things would repel, opposites would attract. Here it is opposite in magnetism. Same will attract, opposites will repel. Now, how is it used to define the unit of current? Basically, if you end up passing some current which is same in both of them, and the distance between the wires is, if for example the distance between the wires is 1 meter and the same current is passed in both of these wires, and you find out that the force acting per unit length exactly happens to be 2 into 10 to the power minus 7 newtons per meter. So F by L is this value. This and this will cancel. Distance is 1 meter. Then I1 and I2, the product of it, then I1 and I2, the product of it will be 1. And since both of them are equal, I square will be 1 or I will be equal to 1. This current is then 1 ampere. So the current which you pass equally in both the wires for a separation of 1 meter, producing a force per unit length of 2 into 10 to the power minus 7 newtons per meter, that current is basically called as an ampere. That's how the unit has been defined. That's how the unit has been defined, and that's exactly what they have done over here. Ampere is that value of that current which maintained in each of the two very long wires so that they are 1 meter apart and they will produce a force of this many newtons per meter. That is a ampere. Exactly what I have done over here. Is this clear, everyone, how this came? Give me a thumbs up, then we will go ahead. Give me a thumbs up, then we'll go ahead. Okay, all right. So, charge is basically a derived quantity. Remember, we have done this in electrostatics. Charge per unit time is current. So, charge is basically current into time. So, ampere into second. So, basically, ampere multiplied by second is nothing but a coulomb. So, that's how coulomb comes into play. Okay, that's how coulomb comes into play. Very simple, very straightforward. All right. Let's go to the next thing, which is the torque on a current carrying loops and magnetic dipoles. And for this, they have given one diagram and they have derived something and they have found out the torque on it. And they have told that, you can change the orientations, etc. And then you can get some formula. Okay, let's understand what they have exactly done. So say for example, okay, so this is basically a current carrying loop like this. And let's say it is placed in somebody else's magnetic field. Maybe the magnetic field lines are like this. For example, and let's say the length of this wire is L. This is also L. Let's say a square loop is there. It's placed in this magnetic field. So let's find out what are the different forces acting on such a loop of wire. This is a loop of current carrying wire in an external magnetic field. One thing I know for 100% guarantee, that is the net force acting on any such loop will always be 0. How do I know this for so sure? Because we have done this in the previous lecture. Net force is always 0 on any loop which is placed in a magnetic field. If you have forgotten, no issues. I will show it to you. Right over here we have done this. Where did it go? The force acting on it. My God. Yeah, here. The magnetic field is passing through this loop. It is uniform. The net force on a loop is always going to be 0. This is something which we had concluded even in the last lecture. All right. So as long as it is a loop, doesn't matter which shape, square, circular, hexagonal, the net force on it will always be 0. So that is for sure. But torque may not be 0. That is exactly what we need to find. So if you consider this segment, this segment, this segment and this segment separately and try to find individual forces, and then maybe torque can be calculated. So let's do this. For this part, magnetic field is here, length is here, length cross B will go down. Just like for this guy, length is here, length is towards you, magnetic field is there, length cross B will go upwards. So try to do this by yourself using your hands. This wire is coming towards you, this wire is going inside the plane. So on this the force will be here, on this the force will be downwards like this. Try to visualize. Got it? It will be like this. Just check this out. Are able to visualize these two things? Okay. Length is going inside, magnetic field is there. So length cross B will go down. Here length is here. So length cross B will go up. What about this part and this part? L cross B will be 0. L cross B will be 0 because length is parallel to the field. So no force on them. So here the force will be 0 and on this also the force will be 0. Each of these forces will be current carrying through this particular wire. Let's say I call it as I. So it will be I. Length is, let's say, L, and into the magnetic field. Even same thing over here, guys. This force will also be again nothing but current into L into B. If you are wondering what happened to sine theta, well, it will be sine 90. Sine 90 is 1. Why 90 degrees? Because you can clearly see magnetic field is here, current is here, they are perpendicular to each other. So that's the reason why it is sine 90. Now, what happens? These two forces are equal opposite, they cancel each other out. That is why you can see net force is anyway 0, but they will definitely produce a torque. They will definitely produce a torque. One of the forces here, the other force is here, and the separation between them is this, which itself is nothing but the length of that loop. So what will happen? There will be definitely a torque which will be produced. There will definitely a torque which will be produced over here. How much will be the torque? Well, if I measure the torque about the center, if I try to measure the torque about the center, it will be R cross F, that means L by 2 into F, plus R cross F, again L by 2 into F. Each of the force is giving a clockwise torque, so that's why plus. This force is trying to rotate it clockwise, this force is also trying to rotate it clockwise, so that is why plus, else this would have been minus. So it will just be L into F. L is L only, okay. F is whatever I wrote over here, which is nothing but I, L, and then you have B over here. Now I'll just play around with this a little bit. I will just write current as it is. L into L is nothing but L square, and then magnetic field over here, and then this is basically your torque. Now, next step, I will think what exactly is L square? What exactly is L square? L square is nothing but the area of that particular loop, is nothing but area of that particular loop. Is that right, everyone? And magnetic field is basically as it is. Now, I think further, okay, if this is the scenario, then just imagine if by chance there were many turns, if by chance there were many turns in that same loop, something like this, okay, if there were many turns, if there were n number of turns in that same loop, then what would exactly happen to this particular formula? this torque will be for a loop, therefore for n number of turns, the total torque that you would have got, will be n times of this. Each one of them will get the same torque. So that's why this will be I, area of the loop, but multiplied everything with n. So n current into area of that particular loop, and that magnetic field is there. Got it? Everyone till this point? Very good. Now we know that torque is a vector quantity. We actually know torque, strictly speaking, is a vector quantity. Somehow can I find if the torque can be represented in the vector form? So then you will think, okay, torque is basically, we just saw over here, it is clockwise. That means it is going like this. That means the torque vector itself, will be like this. The torque vector itself will be like this, because it was clockwise means it will go that way, my bad. So the torque vector was this way. The torque clockwise, so it will go inside the plane of the board. But the magnetic field is here, so 100% it is not parallel. So maybe there is some other relationship over here. So what I do now, this NIA, which is there, number of turns into current into area, I write it as a new quantity, but as a vector quantity called as M, which is called as the magnetic moment. This B is as it is. This will then become the torque, where our M, which is number of turns into current into basically area of that loop, is called as the magnetic dipole moment. It's a vector quantity. Where is this vector? If the current is going like this, curl your fingers in the direction of the current, the thumb will point in the direction of the magnetic moment. The reason for that to happen is because, observe this carefully now, this is our loop. The magnetic moment will be perpendicular to that in the direction of the thumb when you wrap your fingers in the direction of the current, because you will notice very clearly that one side will be north, this side will be south, dipole, so it will have a dipole moment, hence magnetic dipole moment M, north pole and south pole. So this coil is like a bar magnet which is inside. So that's why magnetic dipole moment. Is this clear? So this is a new quantity which we have defined called as the magnetic dipole moment. So now this reminds me of electrical dipole moment into electrical field is torque, but this is a very special case. If you notice, the magnetic moment was up, magnetic field was here, so the angle between them was 90 degree. So maybe whatever was there in this scenario, magnetic moment was on the top, magnetic field is over here, whereas the torque which is there, it's inside the plane of the board. So clearly the angle between magnetic moment and magnetic field was 90. So whatever was multiplied here was 1. This 1 means actually it is sine of 90. So MB sine 90 was there, and whenever sine comes, it should be a cross product. Hence our torque in the vector form should be technically magnetic moment cross our magnetic field. This is very, very important. This is the torque which is acting on a loop carrying current. It is M cross B. As simple as that. This is the derivation for that. It's just like electrostatics. It was P cross E. Here it is M cross B. That's exactly what they have mentioned. They have done the same derivation over here. Okay, for that same loop. Okay, and they have said that, this is very similar to electrical dipole moments torque. So all these are, very important things. So magnetic moment of the current loop is this, where the area vector is given by the right hand thumb rule and directed into the plane of the paper as shown. This is just like electrostatics case. Okay, and then they have given some things over here. Magnetic moment is NIA. Okay, right. Now, just like in electrostatics, here also, say for example, first our loop is, let's say, like this. Then let's say our loop is like this. Then let's say our loop is like this. I'm shading the area so that you can visualize it even better. This is the area of the loop. It has some number of turns. So the magnetic moment in each case, let's say first time it is here, next time it is here, next time it is here. These are magnetic moments of that current carrying loop. Magnetic field, first case it is here, second case it is here, third case it is here. Magnetic field. In the first case, the angle between magnetic field and magnetic moment is 0. Here the angle is 90 degree. Here the angle is 180 degrees. If you ask me what the torque is, sine 0 is 0, it will be 0. Here sine 180 is also 0, so it will be 0. Here the torque will be mb sine 90, which is 1. So this torque is actually the maximum torque, and this torque will try to pull it like this. This torque will try to pull the magnetic moment in the direction of the field. Here, because the torque is 0 and anyways force was always 0, force is 0 always. Whenever force and torque both are 0, such as the condition of something called as equilibrium. So this is definitely in the equilibrium condition when angle is 0, the torque and force were 0. Even this is the condition for equilibrium. This is also in equilibrium. This is not, because torque is there, it will definitely rotate, the coil will spin for sure. Got it? But you know, this equilibrium is actually stable equilibrium. Yes. Whereas this equilibrium is actually unstable equilibrium. The reason for its instability is if somebody disturbs the magnetic moment either here or here with respect to the magnetic field, the torque here will, oops, sorry, my bad. Somebody disturbs the magnetic moment here or here with respect to the magnetic field like this. The torque will try to bring it like this or like this. So earlier it was in equilibrium, you slightly rotate it, the torque will immediately flip it over here. So it is not coming back to its original state. That is why it is unstable. Whereas over here, if you slightly move it up or slightly make it go down with respect to the magnetic field, you will see the torque will immediately try to bring it back. It will try to restore it back. So because it tries to restore, it is stable. Here also it was equilibrium, but if you disturb it, then gone. It will immediately flip onto the other side. Is this logic clear, everyone? Yes. Why opposite in electrostatics and magnetism? There is no real reason for it. It's just how things are happening as a coincidence. Like even electrostatics law is K Q1 Q2 by R square. Gravitational law is G M1 M2 by R square. So, you know, there is similarity in gravitation and electrostatics. So maybe when God made this universe, it's like probably, you know, he had to write or he had to make things with a mind, as in like Okay, I made this. Okay, I had this idea in mind for gravitation, so I'll make this for electrostatics. He just changed the numbers, he just changed the constants, or he just changed the values, that's all. But formulas were looking very similar. It's like a group assignment. Everybody is doing the same thing but changing the values. So maybe the universe was made like that, but each force was made by a different individual, or maybe just done again and again. So you don't want to repeat the same thing, but you have the same ideas, so you're just copying it. Who knows? We would never know. All right, cool. So that is what is important over here. Now let's go to the next point, which is circular loop as a magnetic dipole. And this equation might look confusing at times. So let me go back to this particular page. Field due to a coil. Remember, I told you here, a field which is generated by a coil carrying current looks like this, and this looks very similar to a bar magnet's magnetic field lines. So this is exactly what we are trying to study, and we had derived an expression over here which was like this. So let me just copy this over here. Wow, this is going to take a while. I think I might as well have drawn this now, I feel. Anyways. Now, we have also seen that it produces magnetic field lines like this. And this looks very much similar to just a bar magnet with south pole and north pole. Field lines are coming in a very similar fashion. And they continue. It's not like they don't. They continue even inside that magnet. They continue even inside that magnet. They are very, very similar. So is there some relationship? The answer is yes. So let's find that out. What is that relationship? So if you basically, go really far away, if you go really, really far away, then what happens is, oops. So if x is much, much larger than the radius, that means the loop is over here and you are somewhere over here. The x is much larger than the radius on the axis. Then what happens is that this number will be very large, this will be very small, r will be very small. So you can neglect it, and hence this same formula for the magnetic field along the axis will become, because this will then become negligible in front of whom? Who will it become negligible in front of? X square. So the formula will become, see this, mu naught is there, 2 is there, this current is there, r square is there, of course. This has become negligible in front of this, so it will be x square only. It will be x square only. The whole thing raised to 3 by 2. Whole thing raised to 3 by 2. Correct? Now 2 and 2 cancels, it will just become x cube. So it will just become mu naught by 2. You have just I r square on the top, and below you just have basically, what is it? X cube, x cube over here. Now, current into R square is for a single loop. Let's say the same thing was done for multiple loops. The same thing was done for multiple loops. Let's say, there are n number of turns over here. Let's say there are n number of turns over here. So if you had n number of turns, what would have happened? I would have to multiply it with n. I would have to multiply it with n. I would have to just multiply it with n. Right? That is the only difference. Okay. Now what I will do, I will just multiply and divide by the number pi. So what will happen? This will become mu naught by 2 pi. And then over here I have n I pi r square. And this whole thing divided by x cube. Notice what happens. Ni pi r square, Nia, number of turns current into area of that loop. What is it? That is nothing but the magnetic moment. Then, instead of mu naught by 2 pi, how about writing it as mu naught by 4 pi? Just put that number 2 on the top. Anyways, it is the same thing. And now, write down x cube over here. I will get the magnetic field on the axis. This formula looks very similar to, observe this carefully now, observe this very carefully. If you had a negative charge over here and a positive charge over here, minus q plus q, which will now create an electrical dipole moment, and you go on the axis at some distance, which is really far, the electric field on the axis is given by 1 by 4 pi epsilon naught 2 into you had electrical dipole moment divided by whatever distance you went divided by x cube. Exactly similar. Here you have the constant in electrostatics. Here this is the constant in magnetism. 2 is there here, 2 is there here. Electric dipole moment, magnetic dipole moment, x cube, x cube. So the formulas look very similar. So this proves that a current carrying loop is actually like a magnetic dipole. This proves a current carrying loop is actually like a magnetic dipole with polarities of north and south. The formulas are very, very similar. Yes, Krishna, our national flag color has come. Looks exactly. I was getting the same feeling. Saffron, green, white, naturally looking Indian flag. So we have got Indian flag in Shreyas sir's class before GTA 6 in magnetism. And that too in such a nice way. Beautiful. Same, but different. Very good. Excellent. So that is what they have mentioned over here. So this is similar to this. This is basically similar to this. This result becomes exact point magnetic dipole. Shown that any loop. Yep. This is the analog of electric dipole moment. Electric dipole moment is made up of two charges. In magnetism, very important, a magnetic dipole is most elementary element of equivalent charges. But remember, magnetic monopoles do not exist. Although we wrote it's like a magnetic dipole with two polarities, but remember you cannot ever separate the north pole and south pole separately, unlike electricity where positive and negative can be obtained separately. Okay. So we have shown, what is the final conclusion? We have shown that a current carrying loop produces a magnetic field and behaves like a dipole, which is basically north-south bar magnet. It behaves like it. It is also subject to torque. It will also experience torque like a magnetic needle. We know this. If you take a magnetic needle with north and south polarities and you place it in somebody's field, it will definitely experience a torque. Definitely. Yeah. And also there are no magnetic monopoles. Yep. No magnetic monopoles. These are the final conclusions. Till this point, all this theory is understood, guys. All right, this is exactly what they have done over here. Okay, neglecting x is much larger than r, etc. So the same derivation I have done it for you in a much simpler manner. Okay, let's go to the final topic, and that is called as the moving coil galvanometer. Moving coil galvanometer, and they have given the construction, the working, and how do we use it as a voltmeter versus how do you use it as a ammeter. Okay, that is the last part of this. So moving coil galvanometer. Galvanometer is nothing but a device to sense if there is current, if it is passing in this way or opposite way, and if there is no current also, it will show me. It's basically a sensitive ammeter or a sensitive current measuring device. It's very sensitive. It can't measure a large amount of currents. And it works on the principle of magnetism. There is a wire which is wound, it forms a coil, current passes through it, there are magnets inside, the coil will move, so the needle moves on that scale, and that's how you can measure everything. So basically, a moving coil galvanometer, whose principle is understood on the basis of the discussion previously, it consists of a coil. Yeah, a galvanometer basically consists of a coil with many turns, free to rotate about some fixed axis in a uniform radial magnetic field. There is also a cylindrical soft iron core which makes it radial. Okay, and when the current flows through the coil, there is a torque which acts on it, and based on that torque you basically measure everything else. Okay, since blah 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 blah, resulting in a steady direction, this where K is the torsional constant of the spring inside, and from that you basically get this formula. The quantity in the brackets is a constant for a given galvanometer. It can be used in different ways. A galvanometer can be used in different ways. It can be used as a detector to check if current is flowing in the circuit, and example Wheatstone's bridge, blah blah blah. And it can be also used as an ammeter to measure the value of the current. Okay, and also it can be used as a voltmeter to measure the voltage across a given section. So construction, working, and applications, all of them one by one. Let's start by the construction part. Let's understand this, what exactly happens. Everybody pay attention. Everybody pay attention first. So say for example, if I have a horseshoe magnet, okay, if I have a horseshoe magnet, something maybe like this. If I tell you this is the north pole, this is the south pole, then what will happen is magnetic field lines will go from here. Probably they will come here. Some of them will go from here, will come here. Definitely. Some will go like this. Some of them will again go like that, and they will come back over here. This is how the magnetic field lines will roughly look like for a horseshoe magnet. Imagine I take a cylindrical magnet, meaning it looks something like this. You have to visualize it a little bit. It is a cylindrical magnet, guys. So cylindrical magnet. So something like this. Imagine it's like the horseshoe magnet, but the polarities have come very close. And it has been scooped out instead of flat surfaces. A scooping out has been done as if you can fit an imaginary cylinder inside of it. Just imagine you can put an imaginary cylinder inside of it. So you have taken out a cylinder outside. Are you able to visualize this? Are you able to visualize this? What is the meaning of the shape? Just check this out. Yep, very good. So now what we will do, how will the magnetic field lines look like? The magnetic field lines will look very interesting, going from the North Pole to the South Pole, maybe something like this, maybe going like this, maybe going like this, maybe even going like this. And outside of it, there might be some stray magnetic field lines. That's ignored. We are just interested here. Mainly, what happens is, if I look at it from the side angle, very important, I will see the magnetic field lines doing this. Doing this. This is from the side angle. This is from the side angle. This is North Pole and this is South Pole. This is how the magnetic field lines will look like for cylindrical magnets. What are these magnets called as? Cylindrical magnets. Cylindrical magnets. Cylindrical magnets. This was your North Pole. This was your South Pole. Now this field is very interesting because, see, the magnetic field lines go like this, they turn. The magnetic field lines go like this, they go straight. They go like this and they turn. Approximately at the center, you know, they are concentrated, and it feels like if you ignore the central part, if you just ignore the central part for most of the practical purposes, observe this carefully. Ignore that central part. If you just concentrate on the ends, it feels as if the magnetic field lines go here, go here. Observe this now. Go like this, 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 and they come back over here. Probably they come back over here. Probably they come back over here, over here, over here, and of course over here. It feels as if it is like this. Ignore this part. Doesn't it feel as if, you know, the magnetic field lines are, you know, just continuing over here? They're just continuing on the other side. It just gives you that notion, isn't it? It feels like they're just continuing over here. So guys, this kind of field is called as a radial field. What is this called? Radial field. Radial field means the magnetic field lines are, you know, along the radius of that particular circle. So when this happens, a very interesting thing, you know, occurs. So imagine you are in a radial field. Imagine you are in a radial magnetic field. So there is magnetic field line here. There is magnetic field line here. There is magnetic field line here. There is even magnetic field line here, like this. So this is your radial field. And now in such a radial field, you are placing a coil. You are basically placing a coil. Now, no matter how the orientation of the coil is, observe this carefully now. No matter what the orientation of the coil is, you will see that their magnetic moments, let's say in this case the magnetic moment is like this, in this case the magnetic moment is like this, in this case the magnetic moment, the magnetic moment is like this. Every time you will see that the respective magnetic moments are, in the plane, or sorry, the coil is in such a plane that it experiences the force due to these magnetic field lines. This magnetic field line which is there, it's in the plane of this particular coil. It's acting on this magnetic moment, and they are always going to be perpendicular. Same way, when you take this particular loop, it is this magnetic field line which affects this particular loop, which is having this magnetic moment. Again, this magnetic moment is being affected by this magnetic field. Every time the magnetic moment is perpendicular to the magnetic field, that means theta is 90 degrees. That means the torque, which is mb sine theta, it will be mb sine 90, which is just mb. And this means the torque is constant for all the orientations. Is this absolutely clear? This is one of the most critical criteria for a moving coil galvanometer. Every orientation, it will experience the same torque. Very, very important. Okay, keep that in mind. So, just reiterating it over here. This was our coil. Visualize this particular plane. Other magnetic fields will not play a role except for only this magnetic field which is passing. Other field lines are passing through some other plane. Don't worry about them. So only this magnetic field will play a role, and it will affect the magnetic moment of that coil, that is perpendicular. And it is always going to be perpendicular. You take any orientation, you'll find some or the other magnetic field line which is in the plane of the coil or perpendicular to that magnetic moment. Now what happens is, imagine you take any object and you connect it to a twisted spring. This spring can be twisted like this. So you can turn this object like this. So you twist it by some angle, let's say theta. The spring gets twisted, because of which what will happen, it will experience a torque which will try to restore it. So there will be a restoring torque. This torque is found to be proportional to how much you have twisted it, and that constant is K. Again, that constant is K. This torque is some K into theta. This K is called as the torsional constant of the spring. Why not spring constant? Because spring constant is when F is Kx. This is displacement in meters. This is in Newton. When you have Newton per meter torque and radian, this is torsional constant whose units is Newton per radian. Is this clear? This is torsional constant. How many Newton meters of torque is needed to rotate it by 1 meter? That is torsional constant. So when you twist something, it will try to restore it back. Which means now, just imagine you have a coil. Okay, imagine you have a coil, let's say like this, and it is placed in between, it is now placed in between cylindrical magnets. It is now placed in between cylindrical magnets. This coil will generate its own magnetic moment, and there is obviously some magnetic field, of course, over here. There is some magnetic field over here. Let's say I call it as M, which will definitely produce some kind of a torque, Sorry, this is not M, this is B. Magnetic field. So there was a torque now. So because of the torque, it will rotate, but I want it to stop. So that's the reason why I have taken this coil and made sure that it is connected to a spring like this, which will then get twisted by some angle theta. And when it twists, it will apply a restoring torque. Like this. And this loop will be in equilibrium. It will be in equilibrium if the restoring torque by the spring, which is trying to bring it back, is exactly balanced by the torque this way by the magnetic field. The magnetic field is producing a torque like this, is trying to rotate it, and at the same time, the another torque is trying to bring it back. This torque by the spring is nothing but K into theta. This torque by the magnetic field was just MB. M is nothing but number of turns into current into area, and this is B. This is just K theta. Think about it. If current increases, theta increases. If current reduces, theta reduces. Current becomes 0, theta becomes 0. Is that clear? So more the current, more is the deflection. So therefore, our theta will be NBA divided by K, and this is current. Very important formula. So you can see the deflection is directly proportional to the current passing through the coil. This is important functioning of the galvanometer, because when you see a galvanometer, right? What it has is basically a scale. Let's say this is 0 like this, and also on the other side. And then there is this needle which will deflect, and this particular galvanometer, some current is passed in, some current comes out, some current is passed in. This is the current passing through the galvanometer. There is obviously some kind of deflection that happens, theta. This theta is proportional to the current passing through the galvanometer. More the current, more the deflection. No current, no deflection. Got it? So this is exactly how current is measured using a galvanometer. You see how much is the deflection. From this, you can find the current through the galvanometer. Now, number of turns, field, area, and spring constant, obviously they are constants together. So these parameters will never change for a galvanometer. It will be always the same. Is that okay? So N, B, A, and K all will be the same. And very easy to remember this. NBA is associated with basketball. So just imagine your basketball. Imagine your basketball, which is there. It's being thrown, not thrown, actually it has been kicked by your Pandu. Your Pandu does not know how to play basketball. So what he has done, he has kicked it. He has kicked that basketball, so that basketball goes inside the basket. So NBA is associated with basketball. K is kick. Where do you kick from? Below. So K is below. K for kick. When you push it by hand, hand is on the top, numerator. K is kick. Kick is below. So basketball has been kicked by Pandu. So current is, over here. Deflection is over here. That's how you remember it. Got it? Everyone? Oh yes, Sumi, definitely. I'll take water. Thank you so much for reminding me. Now this constant NBA by K will be how much deflection is there per current. This is called as the sensitivity of galvanometer. Basically, how many radians is deflected per unit ampere. For an ampere, if it deflects more, it has more deflection. Is that okay? Keep that in mind. Now remember, always any instrument can measure a maximum value. So there will be obviously a limit till which it can measure. So say for example over here, if this was obviously your theta, there is a maximum limit till which you can measure it, and that is only till here. So what you get over here is theta max, maximum deflection. So full scale deflection is basically theta max. So there is obviously maximum current which can be passed through the galvanometer. That will be I max, also called as a full scale deflection current, So if the current is more than the full scale deflection current, the galvanometer may spoil. It may spoil, or it may burn, or it may be irreparable. So that is why you try to maintain the currents within the limits, within the deflection of the maximum value over here, else the coil will definitely burn. Yes. Next important thing that you need to remember is that a galvanometer also has its own resistance. This is also called as the coil resistance. Coil resistance of that particular galvanometer. So any galvanometer has a resistance. Obviously, it is made up of many windings, like I told you over here. It's made of a coil. So definitely it has some resistance, and it can only measure a limit of the current, which is not too much. So you have to make sure the currents are well within the full scale deflection limits. Are all these pointers clear, my dear students? Shall we go ahead? This was your sensitivity of the galvanometer. This was maximum current, which is I max, and this is your coil resistance of the galvanometer. All these are important parameters. Okay, so that is exactly what they have done over here. If you realize, okay, this is exactly what they have done. The torque, the derivation, everything. Deflection is NBA by K into current. This is the constant for a galvanometer. It can be used to check if current is flowing or not. Do you remember Wheatstone's bridge? 4 resistors are placed. You place a galvanometer. If the potentials are equal, no current will pass. No current, no deflection. So that is why null deflection method. So when there is no deflection in the Wheatstone's bridge, no current is passing, and you can say R1 by R2 is R3 by R4. That is what we have studied in Wheatstone's bridge. So that is one of the first application to check if current is even there or not there. Okay. Next important thing, it can be also used to measure the value of the current in a given circuit, which is basically an ammeter, and the second usage is as an voltmeter. So what is this? How do you use it as an ammeter versus a voltmeter? So let me give you a very simple example. Just imagine there is a road which goes inside your neighborhood, okay, and if there are few cars going in it, then it's okay. But if many cars are going, many vehicles are going, it becomes crowded, it becomes like a traffic jam, the road cannot handle too much. So same thing also happens in your blood vessels. If there is a blood vessel, too much of blood is going through that vessel, the blood vessel can't handle it, or maybe there is some obstruction here, there is a limit till which the blood can go. So what you do is basically you bypass that movement of vehicles or the blood or whatever has to flow through another tube, through another road, through another path, so that this part remains unaffected. You basically bypass the flow. Got it? That is also called as bypass surgery, etc. Everybody clear till this point? So same way, just imagine if my galvanometer can't handle anything more than some few milliamperes, but I want to measure 7-8 amperes of current or 50 amperes of current, then I can't pass such heavy current through the galvanometer. So I'll be like, okay, galvanometer, no issues. I will do one thing. Whatever current was coming from here, I will bypass most of the current. Over here, and again let it mingle on this side. That's okay. Let it mingle on this side. And I will pass very little current through you. So if the total current was I, most of the current will flow here. A very small current will flow here. This would be probably Ig. So naturally this would be I minus your Ig. That is the current which will go through here. And this current which is passing over here will have to pass through a resistance. This is in parallel. This is also called as the shunt resistance. Shunt means parallel. This word means parallel. So this resistance has to be chosen in such a way that this galvanometer does not get burnt. So then indirectly I am measuring the current. So that is what is the principle of an ammeter. So this thing, if it is packed inside a box, this then is called as your ammeter. So ammeter is nothing but a galvanometer connected in parallel to another resistor. That's it. So if you buy a galvanometer in the market in an electronic shop for 500 rupees and somebody sells you an ammeter for 2000 rupees, that means you have become one fool, because there is no difference as such, in a galvanometer and ammeter except for one resistor, and the resistor you can get it for 1, 2 rupees, 5 rupees. So take a galvanometer, connect a resistor in parallel, automatically it has just become an ammeter, because now it can measure heavy currents. It will bypass most of the current through it. Got it? Very good. Now usually the shunt has to be very small resistance. So remember this. So the shunt resistance is usually very small. So because of which, think about it, the resistance of the ammeter is also very small, and an ammeter is always connected in series with the circuit. Ideally, an ammeter has 0 ohm resistance. Ideal, but in reality, it can definitely have some resistance value. Ideal ammeter has 0 resistance. The symbol for ammeter is just this. You can use this or just this. This is also the symbol for ammeter. So an ammeter is actually a galvanometer plus a resistor in parallel. So just use our regular formulas of series parallel. You will get all the required data. This is the resistance of the galvanometer. There is some current entering. You bypassed it through a shunt resistance like this. This current was I. This is I minus Ig. over here, this is basically RG. That's it. So now, because they are in parallel, obviously the voltages are same across both the resistors. One is galvanometer, another is the shunt resistance. Voltages will be same. So I can write V is equal to current through the, this was IG. Current through the galvanometer into galvanometer resistance, or I can also write it as I minus IG into shunt resistance. So therefore I minus IG into shunt resistance will give me current through the galvanometer into galvanometer resistance. Usually this is given to you, or this is given to you, this is given, and one of the things you have to find. So this is very simple equation. Don't sit and by heart it. Don't say that, sir, I minus Ig into Rs is equal to Ig into Rg. No, don't by heart it. Just remember there are two resistors in parallel. So what will be same? Voltage will be same. So voltage is IR. That's it. Don't break your head over it. So say for example, a galvanometer of let's say 10 ohms, okay, or a galvanometer of 100 ohms with a maximum full scale deflection current of just 1 milliampere has to be converted into an ammeter up to for example 2 amperes. Find the shunt resistance to be used. Find the shunt resistance which has to be used. Let's do this question. It's not at all difficult. Show the galvanometer as a normal resistance, 100 ohms resistance. That is your galvanometer. The maximum current which can flow over here is 1 milliampere. That means 10 to the power minus 3 amperes. But you can't allow that much current to flow inside. The actual current which has to go is 2 amperes. So you bypass the current through a shunt resistance, which I do not know. How much will this current be? It will be 2 minus 10 to the power minus 3. Guys, 2 is a very large number. 10 to the power minus 3 is a very small number. So won't it be approximately 2 amperes only? Everyone? Very good. Now we know that the voltages have to be same across both. So voltage across the shunt will be voltage across the galvanometer. Across the shunt, it is I into R, resistance I do not know. Across the galvanometer, current 10 to the power minus 3, resistance 100. So from this you will get Rs. This will become 10 to the power minus 1. This will become 1 by 2. So this will become 1 by 20, which is basically 0.05 ohms. So the shunt resistance is 0.05 ohms. If you use that small resistance, then you can measure currents up to 2 amperes. Are you able to understand it? How to solve this kind of questions of ammeter? Don't remember formulas. That's why I did not block anything. Many teachers make students by heart formulas. I pity such students and I wonder why those teachers make them by heart such formulas. You don't have to. You just have to remember voltage is IR and it is the same. It's a parallel circuit. That's all. And most of the times you will see that this approximation will help for solving the problems. Cool? Yep. Very good. Now, the next application, like I said over here, is as a voltmeter. I want to measure it as a voltmeter. So how do I make use of it as a voltmeter? What you do, a voltmeter is nothing but voltmeter, symbol for that either this or this. A voltmeter is usually connected in parallel across a device, in parallel across any device. Let's say so this is my device across which I want to measure the voltage difference. Because it is connected in parallel across the device which you want to measure the voltage. It also means one more thing, guys. What? You cannot have too much you cannot have a small resistance, because if the resistance is small, all the current will go here, the device will stop working. Imagine you want to measure the voltage across a fan. If you connect the voltmeter, imagine the fan only stops working or it starts rotating slowly, then you are not doing a true experiment. It should be as it is. It's like I want to measure the pulse rate of a human being or the BP of a person. Imagine I put some device to measure the BP and the person only stops working. Imagine he's shivering. Then it is not a correct measurement. It should not affect the device. It should not affect the measured value. Getting my point? Like measuring the blood of a person. You cannot draw 1 liter of blood or some 7 liters of blood from a person and say, okay, let me test the blood. What are you testing the blood for? Got my point? So that's why you cannot draw too much of current. The device has to stay unaffected, which means the voltmeter has a very high resistance, and draws a small current only. It draws a small current only. It also means that an ideal voltmeter has infinite ohms of resistance. An ideal voltmeter has infinite ohms of resistance. Yes, correct. So, coming back to the point, how do I make a very large resistance from a galvanometer? No issues. You just take the galvanometer. It has Rg resistance. You add to it one more resistor, but this time this resistor is in series, not shunt, it is series. If you add both of them together, that's it, and you package it very nicely. Oops. That is exactly what a voltmeter is. So voltmeter is not too different from a galvanometer. Just you connect a resistor in series. That's it. If galvanometer is available for 500 rupees, you buy a 5 rupees resistor, 505 rupees, that's it. It becomes a voltmeter. You cannot charge 1000 rupees for it. That is now the two terminals, which is like the probes where you attach across the device to measure the voltage. So let's say the voltage that you want to measure is over here. This is the voltmeter reading. This voltmeter reading will be the net current multiplied by the net resistance. So whatever current goes through the galvanometer has to go through the series resistor. They are in series, obviously. So the net current is just Ig. The net resistance, though, is nothing but resistance of the galvanometer plus the resistor of the series resistance. That's it. So this then becomes your voltage measured value. So this is how you can measure the voltage if I measure the galvanometer current. If I know the current, I can measure the voltage. This is the working principle of a voltmeter. Is this clear? Let's do a simple example so that you understand it. Again, I would repeat over here. Please don't by heart this equation. You know Ohm's law, just apply Ohm's law. Let me show this to you. Example. The full scale deflection current of a 100 ohm galvanometer is 1 milliampere. In order to convert it as a voltmeter of 10 volts, find the series resistance which will be needed. Find the series resistance which I will be needing. Let's try this out. Just draw a simple circuit. We know voltmeter is made of two resistors in series. This is galvanometer of 100 ohms. Remember, I can't pass more than 1 milliampere, which means 1 into 10 to the power minus 3 amperes of current. In series, you have one more resistor. I will call it RS. As a whole, it cannot measure more than 10 volts. That's the range of the voltmeter. That's it. This is our diagram for the voltmeter. So now I know voltage. Now I know voltage is nothing but your current multiplied by the resistance. V is IR. So what will be the current? Current is 10 to the power minus 3. What is the resistance? Both are in series. So 100 plus RS. 100 plus RS. This goes over here. This will become 10 raised to 4 is 100 plus RS. So RS will be 10 raised to 4 is basically 10,000 minus 100, which is 9,900, which is 9.9 kilo ohm. So the series resistance required is 9.9 kilo ohm. Then you have converted into a voltmeter of how many volts? 10 volts. Is this absolutely clear, everyone? This is how you convert it. So these are very beautiful examples to show how you can convert it into a voltmeter as well as previously ammeter. Now in this chapter, basically we talk about, permanent magnets, usually like a bar magnet, north-south pole, horseshoe magnet, and how do these properties come, and the different types of properties of materials related to magnetism. That is what you study. Just one sec. So that is what you're going to study in this chapter. So here they say magnetic phenomena are universal in nature. That means it is there everywhere. There are distance, galaxies, invisible atoms, human beings, everything has some kind of magnetic property associated with it. In fact, the earth itself is magnetic in nature. And we know this, that so many birds and animals navigate their migrational patterns via the earth's magnetic field. And for centuries now, old navigators have been finding and exploring different areas using the earth's magnetic field. So this word was derived from an island in Greece called as Magnesia, where that magnetic ore deposits were found as early as 600 BC, that's 600 years before Christ. That is what, this ore was found in Greece, and they found that it attracts other things, and that island name was Magnesia, and that's how that name came. Don't worry, this won't be asked in NCERT, that's why in your NEET exam, that's why I'm not underlining it. So in the previous chapter, we have learned that when you move charges or you pass a current, magnetic fields are produced. We remember this. You take a wire which carries current, immediately it behaves like an electromagnet, right? We have seen this. Also, this was made by Ørsted just very lately in the 19th century, and Biot-Savart's law and Ampere's law tells me how to find this magnetic field. Ørsted was that guy who discovered this phenomena. Biot-Savart's and Ampere's law tells me the magnitude of the magnetic field calculations for any kind of geometry. Now in the present chapter, what do we see? So some of the commonly known ideas regarding magnetism are: the earth behaves as a magnet with the magnetic field pointing approximately from the geographical south to the north. Now this is the first thing. Okay, let me just underline. Earth behaves like a magnet with the magnetic field pointing approximately from the geographical south to the north. What do I mean by that? I will come to it. When a freely suspended bar magnet is left, it points in the north-south direction. The tip which points to the geographic north is called North Pole. The tip which points to the geographic south is called as the South Pole. So again, a bar magnet which is freely suspended points in the north-south direction. The tip of the bar magnet which points towards the geographical north is called as the North Pole, and the other way around is called as the South Pole. Okay, now let me explain this. Let me get the earth for you. So you might have heard about some, Pandu Champas saying, I will bring the moon for you. So your captain Shreyas sir brings the earth for you. Yes, I can't get the moon for you. That is for Pandu and Champa. I'll get the earth for you. So in this earth, we know earth spins around like this, and this is where we are, somewhere over here. This is India. I hope you can see that on your screen. Anyways, that's not the point. This is the North Pole. This is where your Europe, North America, Canada, Alaska, Russia, somewhere and all, it's here. So this is your Arctic region. So here you have the North Pole. If you go down below over here, lot of oceans, somewhere below Australia, somewhere below Argentina, right? Some people support Argentina team in football. So somewhere here you have Antarctica, and somewhere down here you have the South Pole. This is South Pole, this is North Pole. Now as per this, the earth behaves like a magnet with the field pointing approximately from the geographical south. This is the south and this is the geographical north. So the magnetic fields go from south to north. So what do I mean by that? Let me explain. Okay. So see guys, very simply put, let me put it on the next slide. That will be better. If this is our earth, okay, this is our South Pole, but this is also called as the geographic south. This is called as geographic north. And the earth behaves like a magnet from south to north, meaning you can imagine earth to be a magnet like this, where the earth's magnetic north pole is actually over here and the magnetic south pole is over here. This is very, very important. The north pole is here, the south pole is here. Now because of this, what happens is, by the way, let me put it over here. This is your magnetic. This is the magnetic north. And this is your magnetic south. Very, very important. Because of this, what happens is, this was your geographic south, this was your geographic north. The magnetic field lines from the earth, they will travel something like this. This is how they will travel. Obviously, they continue inside, but I have not shown it. They will continue inside as well. But you get the idea. It goes somewhat like this. It goes somewhat like this. There will be many more field lines. They will be going like this too. So these are basically your magnetic field lines around the earth. They go around like this. This is how they go around. There will be even more field lines like this. So can you see near the surface? Imagine there is some Pandu. Imagine there is some Pandu over here. He's standing on the earth. This is the Pandu somewhere here. What does he see the magnetic field lines doing? What does he see the magnetic field lines going? The magnetic field lines are going from the south to the North Pole geographically. From the south to the North Pole geographically, but actually what is happening is at the South Pole, you have the north of the magnet, and that north is emitting the magnetic field lines and it is terminating at south pole, but it continues inside, we know that. Is this point very, very clear? Is this point very, very clear? How the magnetic field lines are going from south to north. That is what they have mentioned, the magnet with the magnetic field going from south to the north. With the magnetic field going from the south to the north. So whenever we say south, do we say geographic south or magnetic south? So whenever they say south, anybody says south, it is understood it is geographical south. We do not talk in magnetic terms. We know at the back of our mind, at the south pole, Earth's magnetic north pole is present. Okay, that is one thing. Next important thing which you should also know is that if Pandu was holding a compass, then what will that compass do? Now we know the behavior of a compass exactly. So let's say, for example, so this is a magnetic needle, let's say. Now, if the magnetic field is somewhat like this, then what will happen is there will be a torque on this particular magnet, and that torque we have already seen. It is basically magnetic moment cross magnetic field. It will try to align the magnet. It will try to align the magnet in equilibrium along the field, along the magnetic field. This is what happens. So remember, there will be a north pole over here, there will be a south pole here. So definitely there is a magnetic moment which experiences a torque, because of which it tries to align itself. So eventually, if the magnet has aligned in the direction of the magnetic field, so if somebody brings in a magnet or a magnetic needle, they will see that the magnetic needle will behave something like this. Observe this carefully now. This is our magnetic needle. This is how it will behave, where this is the north pole, this is the south pole. This is the north pole, this is the south pole. This is north. Generally, the north is shaded in a magnet to make it recognizable that it is the north pole. So the north pole will align in the direction of magnetic field, because that's how the magnetic moment will be. So the magnetic moment will be in equilibrium with the Earth's magnetic field, Does that make sense? So can I say that the part of the magnet which points to the geographic north is called the north pole, but actually what is happening is the north pole is getting attracted by the magnetic south, and the south of this needle is getting attracted by the magnetic north. So that's why the south is attracted by this north, but it feels as if the south is attracted by the south pole of the earth. Don't think like that. We know north and north should repel, north and south should attract. So some people think, sir, how, sir, the earth's north pole is there, and how the earth's how the magnetic needle's north gets attracted by the earth's north? No, actually at the north of the earth you have the magnetic south. So this needle's north gets attracted to this guy. Keep that in mind. Is this absolutely clear now? Everyone, thank you Madhumati for that compass, and Krishna too. Yes, very, very clear, Vetri. So glad. Very good, Inshu. Okay. So that is what exactly happens. If I put a needle, it will align. The north will be closer to the south of the earth, which is the geographical north. That is what exactly they have mentioned right over here. The bar magnet is freely suspended. It points in the north-south direction, and the geographical north is where the tip points of the magnetic needle. The next important point which they talk about is over here. There is a repulsive force between north poles, and yes, there is an attractive force between the north pole of one magnet and the south pole. Makes sense. So there is a repulsion pole, a repulsive force between the two north poles or the south poles. Basically, when poles are alike, they repel, and there is attractive force between north pole and the south pole. Basically, opposite poles attract. We know this as a matter of fact. So north and north versus north and south. Here the force will be repulsive. Here the force will be attractive. We cannot isolate north or south pole of a magnet. If a bar magnet is broken, then we get two similar magnets with somewhat weaker properties, unlike charges, which can be isolated as positive, negative. Magnetic monopoles do not exist. We can't isolate north or the south pole of a magnet, and magnetic monopoles do not exist. What does it mean by this? If you take a magnet and you break it down into smaller parts, and this magnet lets you break it down into more smaller parts, no matter what you do, you will always find it will have the north pole and the south pole. North, south, north, south, north, south, north, south. You can never ever isolate it, no matter how much breaking you do. So individually you cannot separate the poles. It's like, imagine the universe made Pandu and Champa. Pandu and Champa can't be separated. No matter how much you break Pandu and Champa, even in the tiniest bit, even in their toe, there is one Pandu, there is one Champa. There is always some bit of Pandu, there is some bit of Champa. Their love is so great. So same way, the north pole and the south pole can't be segregated, can't be separated. Even in an atom, even in an electron, you might say, sir, I have just one particle. Will there be north and south? Yes, if the electron spins, it generates its own north and south, they come simultaneously. But that is not the case with electricity. You can have a proton, you can have an electron separately. That is possible. It is possible to make magnets out of iron and alloys. We begin with the description. This is not so important. I mean, that is understood. These things you will see that iron and its alloys, okay, this thing what we are saying, it is possible to make magnets out of iron and alloys. This thing you will see are basically ferromagnetic materials. Slowly after this chapter proceeds, you will see the different types of materials. We also talk about Gauss's law. We also follow it about Earth's magnetic field. We describe how magnetic materials can be classified, blah, blah, blah. They are just telling what are we going to do in this chapter. Okay, let's talk about the bar magnet. One of the earliest childhood memories of the famous physicist Albert Einstein was that a magnet gifted to him by a relative. What did you get as a gift? I never got magnet as a gift by some relative. I would have hated that relative if somebody gifted me magnet. But okay, Einstein loved it. I got 10 rupees or 20 rupees. Hey, I'm leaving. I'm your auntie. Take 20 rupees. These days, I think kids get 500 rupees or 100 rupees or maybe some gift or 1000 rupees. I don't know. What was your gift? Did you get a magnet as a gift from some relative? At least I did not get. Einstein was fascinated and he played endlessly with it. He wondered how the magnet could affect objects such as nails and pins away from it and not in a way connected by spring or sling. We begin our study, blah, blah, blah. Okay. So the pattern of iron filings suggests that the magnet has two poles similar to positive and negative charge of electric dipole. As mentioned in the introductory section, one pole is north, one pole is south when suspended freely. Again and again they repeat the same thing. A similar pattern of iron filings is observed around a current carrying solenoid. Okay. So let's have a look. Yep. Oh, thank God. So I am considered as normal as you guys then. So I did not get fascinated. Cool. Thank God. I thought I was abnormal because Einstein got fascinated. I was also fascinated, but no relative gifted me. That's all. Anyways, now the pattern of the iron filing suggests that the magnetic bar magnet has two poles, one positive, one negative, just like the charge of a dipole, positive, negative charge. Similarly, the pattern suggests there are two polarities. When suspended freely, the point approximately, okay, all right. Now, see guys, if you take a sheet of paper, Okay, if you just take a sheet of paper, you sprinkle iron filings on it. Iron filings get affected by Earth's magnetic field or bar magnet's magnetic field. You place below this some bar magnet, It is a magnet which is having North Pole and South Pole. And you tap this paper, tap, you tap it. So these iron filings are free to move, then they will start aligning themselves in the magnetic field of that bar magnet. You will see the pattern looks something like this. This suggests that, it feels as if they are coming from somewhere, going somewhere, and they are also passing within the magnet. So this point, one was called a South Pole, the other was called the North Pole. Now, who is decided North and who is decided South? It depends on how they align with the Earth. So the pole which is closer to the Earth's North Pole was called North Pole. The pole which is closer to the Earth's South was called as the South Pole of that particular magnet. So this is also representing how the magnetic field is around a bar magnet. Alright. So they also say that, listen, this pattern is similar to a current carrying solenoid. Because at the end of the day, what is a solenoid? A solenoid is an electromagnet. Whereas the actual magnet over here, this is nothing but your permanent magnet. You don't need to turn on electricity. A bar magnet does not need a switch. It is always a magnet. It's once a magnet, always a magnet, right? They say once a Vedan, always a Vedan. That means once you are a Vedantu student, you are always a Vedantu student, no matter where you go, no matter which college you graduate from. So that's a permanent magnet. Electromagnet is where you turn on the electricity, then it behaves like a magnet, otherwise it doesn't. So electromagnet is like a solenoid. Now, the magnetic field lines. How do the magnetic field lines look like? We have seen this before, but again, it's like a revision, or we are again revisiting this. So, the pattern of the iron fillings permits us to plot. My God, we have to take permission from it. So guys, we took permission from the iron fillings to plot the magnetic field lines. This shows both for the bar magnet and the current carrying solenoid. For comparison, refer chapter 1. Why do they talk like this, as if they are writing some law book? Chapter 1, this figure, electric field as in this figure. Okay, I think these people are lawyers who wrote this book, at least this paragraph. The magnetic field lines are a visual and intuitive realization of the magnetic field. Their properties are blah blah blah. Now they start with the properties. Observe this carefully. This is for an actual bar magnet. This is for basically, an electromagnet. So basically an electromagnet, basically a solenoid. And this one is for electrical charges. They all look similar, but there is some difference. Same, but different. Same, for different. What is it? If you observe, see, for the bar magnet and for the electromagnet, it is very similar. Even the field lines continue inside the magnet. But that's not the case for electric dipole. They originate from the positive, end at the negative, but they do not continue inside. Rather, they start from the positive and end at the negative. It's not the case with an actual magnet or an electromagnet. They do not start from north and end at south. There is no start and there is no end. It's always closed loops. But for an electrical dipole, it is never a closed loop. There is a start, there is an end. That's what you will see. So, the most important property is over here. Magnetic field lines, okay, are continuous closed loops. Very, very important. Unlike the electric dipole, where the field lines begin from the positive charge and they end on a negative charge, or they can even escape to infinity. If you take a point charge, the electric field lines go till infinity. For a negative charge, they come from infinity onto the negative charge. So there is a start, there is a end for charges, but for magnets, there is no start, there is no end. One of the most important property. Yeah, I hope this is absolutely clear. The tangent to the field line given at a point represents the direction of the field. This is again another important property. The tangent to the field line represents the direction of the net magnetic field. Makes sense. Think about it. If you have a, I don't know why this diagram is over here, but anyways, if you have this magnetic field, if you draw a tangent, then the direction of the tangent gives me at that point where is the magnetic field. So drawing a tangent helps me get the direction of the magnetic field. The large number of field lines crossing per unit area, the stronger the field is. So in figure 2.8, where the field is strong versus where the field is weak. So large number of field lines crossing per unit area, the stronger the magnitude of the magnetic field. So in this previous diagram, can you see over here the field is going to be strong versus if you go over here or here the field is weak. Same thing over here, guys. Here they are very close, so it is very strong, versus here there are fewer field lines per unit area. So the field strength depends on how many field lines are there per unit area or how close they are to each other. That is the density of the field lines. Obviously, magnetic field lines never intersect. Magnetic field lines will never intersect, because if they did, then at that point of intersection, I will draw two tangents. So which one is the correct direction of the magnetic field? Which one is the correct direction of the magnetic field? So such confusion can't happen. If there is a magnetic field, there is a unique direction of the field. So that's the reason why they should never intersect each other. One can plot the magnetic field lines in variety of ways. One way is to place a magnetic compass at different places, and this gives us an idea of the magnetic field direction at various points. Okay, fine. So if you are really jobless in life, you can do this instead of this. So what happens here is you pour the iron fillings on a sheet, you tap that sheet, the magnet below aligns all the iron filings in the field direction. So this is easy way. Another way is you can also take a magnetic needle and you can go around and you can see where the magnetic needle is pointing. If it is pointing there, you go there. If it is pointing there, you go there. If it is pointing here, you go there. You go in wherever direction it points and then you draw that curve that gives you the magnetic field line. And you can keep going at different places. You will get different field lines. So that is a little bit tedious, longer way. So after the NEET exam, when you have lot of free time, then you can definitely do this method where you can run around with a magnetic compass and then you can draw the magnetic field line. Okay. Yes. Moving ahead. Bar magnet as an equivalent solenoid. In the previous chapter, we have explained how a current loop as a magnetic dipole. We mentioned Ampere's hypothesis that all magnetic phenomena can be explained in the form of circulating currents. This resemblance for a bar magnet and solenoid suggests that a bar magnet may be thought of as large number of circulating currents. In analogy with the solenoid, cutting a bar magnet in half is like cutting a solenoid. We get two smaller solenoids with weaker magnetic properties. Field lines remain continuous, emerging from one phase to the other. One can test this analogy by moving a small compass needle in the neighborhood and a current carrying long solenoid. Noting the deflections of the needle are similar in both cases. To make this analogy more firm, we calculate the axial field of a long solenoid depicted by this, and we shall demonstrate at a large distance this axial field resembles of a bar magnet. This is also the far axial magnetic field of the bar magnet, which may be obtained experimentally. Thus, a bar magnet and a solenoid produce similar magnetic fields. Bar magnet and a solenoid produce similar magnetic fields. The magnetic moment of a bar magnet is thus equal to the magnetic moment of a bar magnet is thus equal to the magnetic moment of an equivalent solenoid that produces the same magnetic field. Explained how a current loop acts as a magnetic dipole. Okay, and yes, now okay, cutting a bar magnet in half is like cutting a solenoid. We get two smaller solenoids with weaker magnetic properties. Okay, and lastly over here, the resemblance of magnetic field lines for a bar magnet and a solenoid suggests that bar magnet may be thought of as a large number of circulating currents. Okay, so what do these lines basically mean? In the previous chapter number 4 only, we have done this, if you remember this properly. If you take a coil Okay, if you take a coil like this and you pass some current in it, the current goes like this, the thumb goes this way. So you will see that the magnetic field lines will go like this. This is how the magnetic field lines look like for a coil carrying current. This is for a coil carrying current. If you take it as many coils, if you take many such coils, one after the other, then what you get is basically nothing but a solenoid. If you put many such coils together, this is nothing but a solenoid which has some current passing through it, with a current I passing through it, and it also generates a very similar magnetic field around it. So I might have to draw a few more so that it looks like a solenoid. Like this. So you will see that the magnetic field lines go around like this. They obviously even pass through the solenoid. I'm just not showing them, but it is there. So there is definitely a north pole here, south pole here. This is the north pole, this is the south pole. And now comparing this with the actual bar magnet, with north pole and south pole, the field lines look very similar. The field lines look very similar. So that's the reason why they say in this paragraph that a current loop acts like a magnetic dipole. A current carrying loop acts like a magnetic dipole. The magnetic dipole moment formula, if you remember, it was number of turns into current into area. Number of turns into current into area. That was the magnetic moment. Do you remember this, guys? Everyone? Very clearly, we have discussed this. So even a solenoid is like a bar magnet. Now, if you break a magnet, it's like cutting a solenoid. It's like breaking a solenoid, and you are getting two smaller solenoids. Each of those smaller solenoids will also have individual north pole and south pole. That explains why whenever you break a magnet, you always end up getting a north and a south pole. Right? That's why you always end up getting a north pole and a south pole. So whenever you cut a bar magnet, it's like breaking that solenoid into smaller parts, but that solenoid will have, a lesser length, so you will get a smaller or weaker magnet. So the magnets keep getting weaker and weaker if you keep breaking it into smaller pieces. And all these things also point to that the magnetic field lines of a bar magnet and a solenoid look very similar. And that is the reason why the bar magnet and solenoid, because they produce similar field lines, the moments will also be similar. The magnetic moments will also be similar. So guys, this magnetic moment and this magnetic moment, because the field lines are very similar, it will be identical in nature. In fact, we have seen how to calculate the magnetic field on the axis of a solenoid. Magnetic field on the axis of a solenoid or on a bar magnet. How to do that? Well, do you remember electric dipole? Positive, negative charge. If you go on the axis, what's the electric field formula? 1 by 4 pi epsilon naught, 2 times electric dipole moment by the distance cube. So same thing is applicable here. Instead of 1 by 4 pi epsilon naught, you have mu naught by 4 pi. instead of 2 times of electrical dipole moment, you have 2 times of magnetic moment. And instead of the distance, it's the same thing, but you will have x cube over here. So x being the distance from the magnet, this is the point where you are trying to find the magnetic field. Looks very, very similar. This formula can be used for this, it can be also used for this, it can be also used for this. So everywhere you can use this formula. Is this absolutely clear? Thank you, Madhumati. Everybody clear about this particular statement? That is what they have mentioned. Mu naught by 4 pi 2m by r cube. Here they are using the symbol m, okay, small m, but you can also use capital M symbol, because some books use capital M because small m might look confused with mass or some other term. So that is what they have put down over here. Great. Now the next step. The dipole in a uniform magnetic field will also experience a torque, and there is also some potential energy associated with it, and they have done the calculation for this. So let's understand it. See guys, when you have a magnetic moment, that means there is a north pole, there is a south pole, and you place it in some external field, this is external magnetic field, then there is a torque acting on it. And that torque is given by basically magnetic moment cross the magnetic field. If you want the magnitude of it, the magnitude of the torque is basically mb sine theta. It is nothing but your magnetic moment into the magnetic field into the sine theta. This is what the torque is. This same formula was also there in electrostatics, if you remember correctly. Torque was electric dipole moment cross electric field, which was nothing but Pe sine theta. Instead of electric field, you have magnetic field. Instead of electric moment, you have magnetic moment. That's the only difference. Otherwise, everything is very, very similar, but different. Same, but different. Now in electrostatics, you also had the formula for energy stored in it. There was also a formula for energy stored in it, but that was electrical energy. Now we will be talking about the magnetic energy. How much is the magnetic energy of the dipole in that external field? Instead of the dot product of electric field moment into the electric field, here you will have nothing but magnetic moment dot producted with magnetic field with a negative sign. So if you expand this, it will become minus mb cos theta. If you do cos theta, you basically get the magnetic energy stored. So that's it. So this is our formula, guys. This is for energy stored, and this is obviously for the torque. That is exactly what they have mentioned right over here. They have calculated it. It is minus m dot b. Torque was m cross b. So this formula is the magnetic potential energy which is stored. Okay, very, very important. Let's understand this through simple examples. Imagine there is a bar magnet with a moment of 10 ampere meter square along the field of 0.3 Tesla. If it's rotated by 120 degrees, find the work done and the new torque on it. Find the work done and the new torque on it. Let's understand this problem. There is magnetic field like this. Earlier, our magnet was aligned in the direction of the field. Later on, that magnet has been rotated by 120 degrees like this. Okay, so you can think as if the magnetic moment was here. Now the magnetic moment has shifted. Okay, so earlier the magnetic moment was here. Now the new magnetic moment has shifted. This complete angle is 120 degrees. So let's try to do this problem. Very easy, guys. If the first question says find the work done, to find the work done, I need to find how much did the energy change. This magnet, when it is aligned in the direction of the field, it has some energy. We can find that out. So that initial energy will be minus m into b into cos 0, because it is perfectly parallel. Angle between these two vectors will be 0 degree. So therefore it will be nothing but minus mb. Cos 0 is nothing but 1. We'll do the substitution part later on. If you talk about the final energy, it is minus mb cos, the total angle is 120 degrees. What is cos 120? If you remember correctly, cos in the second quadrant, 120 is second quadrant, it is negative. In fact, cos 120 will be negative half. Cos 120 will be nothing but negative half. So put minus half over here, minus minus becomes plus, so it will just become mb. That's not the concern. The question is find the work done. Work is always final minus initial potential energy. This is external work done. It is plus delta U. If you remember correctly, we have seen this in electrostatics and numerous other places, even in work energy. It is just delta U, not minus delta U. That would be conservative forces work done if I put minus. So it is final minus initial. What is the final potential energy? It is mb. What is initial potential energy? It is nothing but minus, sorry, I forgot that 2, guys, sorry, mb by 2. So this was nothing but mb by 2, and this is just minus mb. So minus minus becomes plus, half plus 1 is 3 by 2, so it will become 3 by 2 mb. So what is that value of m that we know? It is 10 amperes meter square. Magnetic field is basically 0.3 Tesla. So basically 3 3s are 9. 9 by 2 is 4.5. 4.5 into 10 is 45. Again multiplied by decimal will again make it 4.5. So 4.5 joules of external work needs to be done. 4.5 joules. How many of you got it? Everyone? Clear till this point? Everybody clear till this point? All right. What about the next part of the question, which says find the torque? Torque is mb sine 120. Magnetic moment 10. Magnetic field 0.3. Sine 120 is positive root 3 by 2, because 120 second quadrant, sine is positive. Okay. 10 into 0.3 is 3. So it will just become 3 root 3 divided by 2 Newton meter. So that is the torque acting on it. 3 root 3 divided by 2. Clear how to solve these kind of questions? You will definitely find these kind of questions in your NEET paper as well. Great. Moving ahead now to another NCERT question. Shows small magnetized needles placed at point O. The arrow shows the direction of its magnetic moment. The other arrow shows different positions of the magnetic moment of another identical magnetized needle. In which configuration the system is not in equilibrium, which is stable, which is unstable, which is corresponding to lowest energy, and all of that. Now, in order to solve that question, you should recollect our previous discussion of electric dipoles alignment and their equilibrium configurations. Imagine this was magnetic field pointed like this, and our magnetic moment first time is aligned, next time is perpendicular, next time it is like this. This is our magnetic moment. In the first case, basically theta is 0, second case theta is 90 degrees, third case theta is 180 degrees. So what will happen to each one of cos and sine values? Cos 0 is 1, sine 0 is 0. Here cos 90 is 0, also means sine of 90 will be 1. Here cos 180 is -1 and sine of 180, sine of 180 degrees is basically 0. Okay. This will be useful for our torque and potential energy calculations. Let's start with torque first. If you measure the torque, in this case, torque is mb sine theta. mb sine theta, because sine theta will be 0, therefore the torque will also be a big fat 0. Here also sine 180 is 0, so here also the torque will be 0. Here sine 90 is 1, in fact this torque will be maximum and it will be just mb. Now what do you see over here? There is no torque acting, here also there is no torque acting. So such situations when there is no torque, that means if you leave it, they will stay as it is. So that is basically a condition for equilibrium. Equilibrium. This is also equilibrium. Now there will be multiple types of equilibrium. Just imagine somebody is nicely sleeping on this nice surface over here. This is our Pandu, who is a sleeping Pandu. So we have got a nicely sleeping Pandu. His eyes are closed. Just imagine this. Versus another Pandu who is sleeping on the top of a hill somewhere over here. Carefully they have been placed. If they are placed there, they will stay there as it is. Nothing will happen to them. They are in equilibrium, yes or no? This Pandu is sleeping inside a valley or a bucket like thing or a bowl or a, some bed sheet which has been tied to the trees, okay, like a hammock. And this person is sitting on or sleeping on the top of some mountain on a peak or somewhere. Both are in equilibrium. But let's say some dream comes, they get disturbed in the dream. So Pandu moves. If Pandu 1 versus Pandu 2, Pandu 1 gets disturbed and moves, rolls over here or here, what will happen? The gravity will pull him back over here. So when disturbed, you get pulled back to your original equilibrium. So that is definitely going to be stable. This Pandu gets some dream. He dreams about Champa being caught by a dragon and the dragon is flying off in the air. And when Pandu tries to catch the dragon is blowing out hot gases. So that dream comes like a nightmare. So this Pandu gets disturbed, he shakes. If he moves here and there, he will start rolling down the mountain. He will start rolling down the mountain. So definitely it is going to be unstable equilibrium. Here this Pandu had more potential energy. Here this Pandu had less potential energy in this locality. So whenever potential energy is high in that locality, then you can say it is unstable equilibrium, provided all the other forces and torques are 0. And when the energy is low in that vicinity, then assuming the torque and forces are 0, then it is said to be stable equilibrium. Correct? Yes. So coming back to this, if you measure the potential energy here, it will be minus mb cos 180 is -1. So hence this would be positive mb. Here if you measure the potential energy, it is cos 90, which is 0. Lot of you might think, sir, this is the least energy. Wrong. Look over here, minus mb, cos 0 is 1. So it will be minus mb over here. A negative number is lesser than 0. So this is the least energy and this is the maximum energy. From this, you easily understand this equilibrium over here, because less energy is definitely going to be stable, whereas this equilibrium will be unstable because of the large energy. So this is unstable equilibrium. So for stable, the field and the moments are aligned. For unstable, they are anti-parallel, and when it's perpendicular, it's not a equilibrium, it's just the torque is maximum and the energy is zero. Is this point absolutely clear? Everyone? Okay. Glad you liked that explanation, Krishna. Now you'll never forget about the dragon, kidnapping Champa, and blowing hot gases. Hopefully you guys get that dream today. It will be nice. Fantasy world. Okay, coming back to this particular question over here. In which of the following configuration it is not in equilibrium versus blah 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 equilibrium. So guys, see over here. A small magnetized needle P which is placed at point O. This is a magnetized needle. Oops. So that magnetized needle, which means the north pole will be here, south pole will be here. It will be generating magnetic field around it. It will be generating magnetic field around it. So one of the magnetic field line will just go like this. Say for example, will go like this. Oops. Other magnetic field line will come like this. Then more magnetic field lines are there. They will go like this before coming back over here. There will be also magnetic field lines going like this. I hope this is very, very clear. So there are multiple other things over here as well. Even at this point, the magnetic field lines will be perpendicular. So I've shown all the magnetic field lines everywhere for this magnet, this magnet, this magnet, this magnet, this magnet, and this magnet. Now observe carefully what are the angles at every place. If you look at Q4, magnetic field and magnetic moment are opposite to each other. So I'll start putting the angles over here very quickly. So it is basically 180 degrees. Here it is in the same direction, so it is 0 degrees. Here it is opposite to the field. Magnetic moment is up, magnetic field is down. So it is basically 180 degrees. Here the magnetic field is in the direction of the moment, so it is 0 degree. Here it is 90 degree. So here it is 90 degree. I think you got your answer now. Wherever it is 0 degree, wherever it is 0 degree, what will be the answer? Wherever it is 0 degree, the answer will be, it will be in stable equilibrium, minimum potential energy. Wherever you see it is 180 degree, 180 degree, what will be the answer, guys? The answer will be, it will be unstable equilibrium, no torque, potential energy will be maximum. Wherever you see 90 degree, wherever you see 90 degree, what will it be? The torque will be maximum, energy will be zero, but it is in neither kind of equilibrium. So that would be the answers of this particular question. Lowest potential energy, wherever the equilibrium is stable. Unstable, that's where it would be maximum. Okay, thank you for reminding me to have water. Yes. So just check your answers. Everybody got this? So this chart is very, very important. This should be there in your notes. Okay, this should be definitely there in your notes. And if you are wondering, sir, can you give me ready-made notes? Then I'll give you ready-made notes. You don't have to do anything. You just have to click few buttons and you can order these flashcards at your doorstep. These flashcards are truly amazing. This flashcards has every single thing that you want. Look at this. This is, I just plucked out a random flashcard. It has got the moment of inertia formulas for all the geometries, beautifully looking diagrams, and angular momentum, volumes, everything over here. So this is just like a rotational motion flashcard. So there are many such flashcards, guys. Such nice things. Okay, you can see right over here. So this is your magnetic field flashcard. Right over here you can see Biot-Savart's law, magnetic field for solenoid and long wires and circular loops. Amazing. So you can order them. I have already made a video for this, just a couple of days back. Okay, moving on to the next thing. This we have already seen, the electrostatic analog. I think I just told this to you. The magnetic field on the axis formula looks very similar to the, look at this over here. The magnetic field on the axis looks very similar to the electrostatics formula, where you have an electric dipole and you find the electric field on the axis. It's just that mu naught by 4 pi is replaced by 1 by 4 pi epsilon. Magnetic moment is replaced by electrical dipole moment, and magnetic field is replaced by magnetic field. So there is a lot of similarity between all of them. So that's why we can say it's like same but different. So what are the things? Electric field replaced by magnetic field, magnetic moment replaced by electric dipole moment, 1 by 4 pi epsilon naught replaced by mu naught by 4 pi. So everywhere you will see that this holds true. This basically holds true in electricity and magnetism. In fact, you can go back a little and you can say, sir, if this was the magnetic field on the axis, then do I really know the magnetic field on the equator? The answer is yes. The answer is yes. Definitely you know the magnetic field on the equatorial region. Remember, this was the equator, and the magnetic field on the equator will be very similar. Instead of 1 by 4 pi epsilon, you will have mu naught by 4 pi. Instead of 2m, it will be just m. Remember it. It is half on the equator as compared to the axis. And this distance, if it is y, it will be divided by y cube. So this is the magnetic field formula on the equatorial region. If you remember, on the axis, it is always double. On the equator, it is always single times. Yeah, there is a difference of that numeric 2. Yes, there is a difference of that numeric 2. That's exactly what they have mentioned over here, if you notice carefully. On the equatorial region, it's m, but on the axial region, there is 2m. So this is basically 2 times of magnetic field on over here on the equator. Okay, keep this in mind. Is this clear, guys? This is just reiterating, re-emphasizing again and again the same thing, that electricity and magnetism are same but different. Only the variables have changed. All right, let's basically now see the complete chart of the analogy for all the different things in electrostatics and magnetism. So wherever you had 1 by epsilon naught, you will have mu naught. Wherever you have epsilon naught, you will have 1 by mu naught. That's the same but different thing. Dipole moment P, magnetic dipole moment M. Field formula, torque formula, everything. Field, torque on a dipole P cross E, torque on a magnetic dipole M cross B. Energy of a dipole minus P dot E, energy of a magnetic dipole minus M dot B. Even the axial field and the equatorial field formulas are very similar. That is what this is telling us. So let's probably do some simple questions on this. If a coil of 100 turns and 0.2 meter square has a current of 2 amperes, or let's say 5 amperes. Find the field at a distance of 4 meters on the axis and 2 meters on 2 meters from the center in the plane of the coil. In the plane of the coil. This is the question. Very, very nice question. Many students will get confused at some or the other place. Let's try to solve this. Okay. First, let's draw the coil. Let's draw the coil. This is our coil, and this is our axis of that particular coil. If you see, there will be also y-axis, there will be also z-axis, something like this. Visualize this in 3 dimension, guys. Visualize this in 3 dimension. First time I'm standing at a distance of 4 meters on the axis somewhere over here. So at this point, I should use the magnetic field on the axis formula. The next says 2 meters from the center in the plane of the coil. Now, if you want to visualize the plane of the coil, visualize like this. This is that plane of the coil. Are you able to visualize this? Just quickly think and tell me. Are you able to visualize the plane of the coil? It is basically your YZ plane. It is basically your YZ plane. Just tell me. Are you able to visualize that plane of that coil? So from the center in that plane of the coil, you are at a distance of 2 meters. So that means you are basically somewhere here, maybe here. And this point is obviously an equatorial point. Why is it an equatorial point? Observe this carefully. Because a coil carrying current behaves itself like a magnet, where this is the north pole and this is basically the south pole. So you can clearly see the magnetic moment is right over here. The magnetic moment is right over here, and that is why this is axial point, this is perpendicular, so that's why this is equatorial point. Is this part of the problem visualization wise clear? Absolutely. Everyone? Okay. Yeah. Great. Sir, flashcards details solunga sir. Saravana? You can watch it here. It's there right on our channel. Okay, it's there right on our channel. You can just go back a little bit, go to videos, and where is it? Neat flashcards are here. Just check this out. Say bye-bye to your notes. Okay, it's right over here. Just check this out. Okay, you can order using the link which is given in the description box of this particular video. Neat flashcards. Click on this link and it will open up this particular page. You can say buy it now and it will be delivered to your address, which you will be putting it up right over here. Okay, as simple as that. So let's start doing the question. First, let's do it for the axis, but before that I need the magnetic moment magnitude. It is, remember, NIA, number of turns 100, current, how much is it? It is basically 5. Area, how much is it? It is basically 0.2. 5 2s are 10, decimal goes away. So it will be basically 100 ampere meter square. That is the magnetic moment. Okay, let's do the formula for axis. So at the axis, it is mu naught by 4 pi 2m divided by x cube. Mu naught by 4 pi is 10 to the power minus 7. 2 into m is basically 100. X is the distance, so that is basically 4 cube. Great. So what do I get? This is 10 raised to 2. 10 raised to minus 7 will make it 10 raised to minus 5 into 2 divided by 4 cube. 4 square 16, right? Into 4 will make it 64. So it will be 1 by 32. So it will be basically 10 raised to minus 5 by 32 Tesla. So that is the magnetic field on the axis. That is the magnetic field on the axis. Perfect. Yeah. Krishna, Kwanjam. Terida. Yes, I can understand a little bit because I do watch Tamil movies, right? I've been a fan of Tamil music, Tamil movies, their stories. I mean, they are very, very different. It's not the same old things. There are some directors and some actors who have done exceptionally well jobs. So thanks to the movies, I understand it, right? And I was born in Tamil Nadu also, right? Yeah. Anyways, coming back to the equatorial formula, it's the same thing, whatever you get on the axis, but exactly by 2. So whatever you got here divided by 2, so it will be 1 by 32 into 10 to the power minus 5 Tesla. So that's the magnetic field at that, but a lot of people forget this will only work if the distance is same. If you notice, this distance was 4, this distance was 2, so that's why it will not work. So just don't divide randomly by 2. That is a common silly mistake. See the distance. This is 2 meters, that is 4 meters. So obviously this will change. So you have to redo the entire thing. There is no other option. Mu naught by 4 pi. You just have m, and here you have y cube. This is 10 to the power minus 7. Magnetic moment is 100. Distance is basically 2. So 2 cube. So this will make it 2 cube, which is nothing but 8. So 1 by 8 into 10 to the power minus 5 Tesla. That's the magnetic field on the equator. Is this now absolutely clear how to solve these kind of questions? Oh no, Sumi, I don't know Bengali. Yeah. Thank you, Krishna, for all the respect from Tamil Nadu. Oh, by the way, we are going to do something really amazing for now. Yeah, students from Karnataka and students from Maharashtra, something really is amazing is going to come up. Yep, it's not what you are thinking. It's not exactly a Kannada channel. Well, it's going to be really cool because in Karnataka we have all kinds of students. We have students from Andhra, we have students from Tamil Nadu, we have students from obviously the original Kannadigas, and some Maharashtrians, some students from abroad. A lot of people who move abroad, when they come back to India, they usually settle down in Bangalore because of, it's got the title of Silicon Valley. And why not do something for all the Kannada students, because there are a lot of engineering and medical colleges in Karnataka, and 9th and 10th standard students too, right? So something really cool is coming up for all of you. Stay tuned for your KCT COMEDK exams, and also for Maharashtra students, especially like when 6 to 7 lakh students write the CET exam, and when nobody cares about them, and me being, a student from Maharashtra, I think I should do something. So something really cool is coming up, so stay tuned, guys. So for Tamil Nadu students, we already have a Tamil channel, right? Shimon sir is obviously taking care of the Tamil channel very beautifully. You have the V Master Tamil, you have, I think, the Tamil JEE and the Tamil NEET as well. So we have the Telugu channels as well for Telugu JEE, Telugu NEET, and also the board students, which is just the Vedantu Telugu channel. Now it's time for the other states to experience the best of the best teachers. Yes, don't worry, West Bengal and Kerala and other states also, it will come. We already have a Punjabi channel now, yep, for Punjabi students, right? So guys, it shows that Vedantu really cares for everyone. Yes, Sukanya, it will be Swalpa Kannada. Yeah. Okay, moving on to the next point, which is magnetism and Gauss's law. And there is a huge paragraph given over here. Magnetism and Gauss law. We studied Gauss law for electrostatics for closed surfaces. Number of lines leaving the surface is number of lines entering it. This is consistent with the fact that no net charge is enclosed. However, in the same figure for a closed surface, there is a net charge outwards, since it does include a positive charge. Situation is radically different for field where continuous field lines and closed loops are formed. Both cases visually demonstrate that number of field lines leaving the surface is balanced by the number of lines entering it, as the net magnetic flux is 0 for the surface. This is true for any closed surface. Very important. So that number of magnetic field lines leaving the surface is balanced by the number of field lines entering it. So the net flux is basically going to be 0 for the surfaces. This is true for any closed surface, okay, and therefore we get this particular formula, okay. Oh, sorry, not this one. This was electrostatics. So the net flux is given by this, and the difference between Gauss law and magnetism, that for electrostatics is a reflection the fact that isolated poles called monopoles are not known to exist. There are no sources or sinks of B. The simplest magnetic element is a dipole or a current loop. Okay, again some critical points. There are no sources or sinks of magnetic field. The simplest magnetic element is a dipole or a current loop. All magnetic phenomena can be explained in terms of the dipoles or current loops. Thus, the Gauss law for magnetism is saying that the net magnetic flux through any closed surface is 0. Okay, so let's understand this, guys. See, if you take an electric charge system, okay, so there is some electrical charges over here, positive, negative, and there will be a lot of electrical field lines which might be coming out of it, maybe like this. And if somebody takes a Gaussian surface, if you take a Gaussian surface, means a enclosed surface, there is no opening in it, there is no hole in this thing, then if you do the electric field dot area, electric field dot producted with the area, what you get on the right hand side is nothing but how much ever is the charge enclosed divided by epsilon naught. This was nothing but Gauss law in electrostatics. Now let's do the same thing for magnetism. For magnetism, the electric field lines never start, magnetic field lines never start or they never end. That means there is no source nor there is sink. Source means it originates, sink means it terminates. For electricity, there is always a source and there is a sink. On the negative charges, the electric field lines will definitely terminate, maybe, right? The electric field lines might definitely terminate, but that's not the case. That's not the case for magnetism. So you will see for magnetism, the magnetic field lines will always be closed loops. It will always be closed loops. So that's how the magnetic field lines are. Which means if somebody draws a Gaussian surface again, just like they have drawn here, which is a closed surface, and at every point you measure the magnetic field and do the dot product, just like you have done here for the entire surface, just like you have done it over here for the entire surface, you put that closed integral. What is this symbol called? Closed integral. Means you cover every part of that surface. Don't leave anything. That is called as a closed surface integral. Okay, that is called as the closed surface integral. I have already given you that example, of your mom asking you to clean the room. If your mom says clean the room and she puts that symbol D, that means you have to clean a small part of the room. If your mom says clean the room from A to B, that means you clean from that corner to that corner. But if your mom says, listen, do this, declean cyclic integral, then that means you have to clean entire room. Don't leave one surface also. If you leave one surface, you will get one flying slipper on your head. Got it? So if your mom is a little bit mathematical or your parents are mathematical, and if they say that, listen, cyclic integral declean, you should know what you should do. You should not leave anything. Okay? So try it out with your younger brothers or sisters next time. Just tell them cyclic integral declean, cyclic integral declean. They will be shocked. They will complain. Mom, dad, I think my elder brother, elder sister has gone mad. They are telling cyclic integral declean. But that's okay. You understand me. All right. So coming back over here, if I do cyclic integral of the magnetic field dot product with the area, at every single point. On the right hand side, I should not get anything, because no matter which area I choose, the amount of north pole and the amount of south pole are always in equal quantities. So the north polarities cancels the south polarities. They are always in equal amounts, and hence the net charge of magnetism will be 0. So this law is basically called as your Gauss law in magnetism. Gauss in magnetism. Gauss law in magnetism. What is then the definition of magnetic flux? The definition of magnetic flux will be like this. So magnetic flux, guys, if you have some area over here, and this is the area vector, and you find that there are some magnetic field lines piercing through it, maybe like this. Then our magnetic flux, which is also directly proportional to the number of field lines passing through, a surface. Yes. So guys, this magnetic flux phi is given by B dot A. Very, very important. The dot product can be also written down as cos theta. So here you put magnetic field, and here you put area vector. So BA cos theta, where theta is the angle between magnetic field and the area vector. So that is the formula for something called as magnetic flux, which is a quantity which describes how much is the flow of the field. If the flow of the field is more, it has more flux. If the flow is less, it has less flux. So the flow of magnetic field, that's why I'm saying it's proportional to the number of lines passing through a surface, is called magnetic flux. It is field dot producted with the area. If you ask me the unit of magnetic flux, it is Tesla into meter square, which is called as Weber, which is just called as Weber. So the unit of magnetic flux is basically Weber. Keep that in mind. Everybody fine till this point? Okay. So whenever you have a curved surface, instead of B dot A, it will be B dot dA and integration of it. That's all. So whenever you have basically a curved surface, there will be many teeny mini small area vectors at every place. These are the small dA area vectors, and at every point there will be some magnetic field which will be passing through that particular point. So the small flux d phi will be nothing but your magnetic field at that point and the area at that point. So the total magnetic flux will be integral of d phi. So that is why I will put integration of our magnetic field dot producted with our area vector. Integration. And if it is a closed surface, then I will put a cyclic integral. That is the reason why the term on the left hand side basically represents nothing but the magnetic flux for the closed surface, which is then called as our Gauss law in magnetism. Is this very, very clear how this formula came? Yeah, because it is cyclic, that means closed. Integration of B dot dA means flux, because just field into area is the flux if it is constant. If it is a curved surface, if it is non-uniform for any random thing, then you will have to obviously integrate it by taking small parts of that surface. That's why dA is integration. Hence, the net flux is 0. That is what this whole paragraph says. Instead of summation, I have put integration. That's all. Okay. So, there are no sources or sinks. Magnetic simplest element is not a north pole or a south pole. It is always a dipole or a current loop. You cannot go smaller than that. You cannot separate north and south. The smallest thing that you can get in a magnet is a dipole in itself. Pandu comes with Champa. And that is why the Gauss law says in magnetism, net flux through a closed surface is 0. Net flux through a closed surface is 0, because whatever comes in has to go out. Whatever comes in has to go out. Okay, so that is Gauss law in magnetism. Great. Now comes the next part, which is magnetization, magnetic intensity, and all the other things which are associated right over here. These are basically some magnetic properties of materials. Okay. Now imagine a material, okay, which is made of many atoms. Each atom has so many electrons, protons, etc. These electrons are revolving. These protons are also maybe shaking here and there. So whenever these teeny charges move, what do moving charges create? Whenever charges move, they behave like currents. And what does current create? It creates magnetic field around it. So they behave like small magnets. So an atom itself is a small magnet because there are charges which are moving inside of it. So imagine so many atoms in an object, in a liquid, in a fluid, in a gas, in a solid. So many atoms, so many charges, so many random motions. Won't that create so many teeny magnets? So the material as a whole will be magnetic in nature. Now it depends whether the magnets cancel out each other or they produce a net field. That's another story. But yes, any material around us, even the humans are made of small, tiny magnets. But yeah, the thing is, all these magnets end up cancelling each other. So that's why we do not behave like a normal permanent magnet. Or else, imagine if we were such permanent magnets, then somebody is walking past us, suddenly you will get attracted and both of you will stick. Or maybe you might just repel from a person. That would be really cool. Pandu would love it, because then Pandu would be the North Pole or South Pole and Champa would be the opposite pole. And then Pandu will see Champa is getting attracted to him, but it will not be because of his looks or because of his personality, but that is because of its magnetic properties. So we ourselves, although we are made of teeny magnets, there are no resultant magnetic property which is left in us. So we do not behave magnetic. But if there is a resultant magnetic property, then it will behave like a permanent magnet, like your normal magnets which you have. Yeah, is that right? Clear? Awesome. So now what do we see? Earth is, okay, first they talk as if they are writing Shakespearean language. The earth abounds with a bewildering variety of elements and compounds. Why do you have to do that? In addition, we have been synthesizing new alloys, compounds and even elements. So then they come to level. First they think they are Shakespeare. The earth abounds with a bewildering variety of elements and compounds, and then slowly they come to mathematics over here. We have seen that a circulating electron in an atom has a magnetic moment. In bulk, these moments add up and they can give a net magnetic moment which is non-zero. We define the net magnetization of a sample to be equal to, okay, we have seen that circulating electrons in an atom has a magnetic moment. Now, when you go to a bulk material, these moments add up vectorially and they can give a net magnetic moment which is non-zero. So magnetization of a sample is equal to the net magnetic moment per unit volume. Magnetization is net magnetic moment per unit volume. M is a vector. Yes, M is a vector with dimensions of per unit length and ampere. We'll come to that. Okay, it is measured in ampere per meter square. Sorry, ampere per meter. Consider a long solenoid, unit length carrying this given by the magnetic field inside is given by mu naught Ni. If the interior of the solenoid is filled with a material with non-zero magnetization, the field inside the solenoid will be greater or will be different, and the net field will be B naught plus B. Okay, we'll come to this also. The net field will be B naught plus B. So the net field inside the interior of this solenoid may be expressed as this, and then they go to other things where Bm is the field contributed by the material core, where Bm is the field contributed by the material core. It turns out that the additional field Bm is proportional to the magnetization M of the material and is expressed as the following. Bm is mu naught into M, where mu naught is the same constant permeability that appears in Biot-Savart's law. Okay, let's have a look. What does this entirely mean? Starting off over here. Okay, imagine guys, this is our nucleus, and then you have this electrons which are basically orbiting the nucleus, These electrons are basically the charges in motion, are basically like small current loops. That means they are magnetic in nature, so I will call it as if they are small electromagnets, and hence it will behave like a magnetic dipole. So just imagine all the teeny mini charges inside any material will have their own magnetic moments. All these small teeny mini particles which are revolving here and there, they will have their own, small magnetic moments in random directions depending on their orientations. So magnetic dipole with a moment of small m, again magnetic moment of that particular particles. So all these magnetic moments, if you add them vectorially, what you get is probably the net magnetic moment of that material. This is the net moment of that particular material, which obviously is the sum of the magnetic moments of all the particles, is the net magnetic moment of all the particles added together. So then we get a term called as magnetization. Now here the symbols that they have used is slightly different. Instead of, see guys, they have used small m instead of capital M. That's the one major thing. They have used small m instead of capital M. That's all. So let me also use the same thing so that you do not get confused over here. So this is the magnetic moment of that material. Now if you divide it by the volume of the material, if you divide it by the volume of that material, what you get is basically, just think, per unit volume, what is the magnetic moment? Per unit volume. So if this is representing unit volume, how much is the magnetic moment present per unit that? So that is what is called as magnetization. Magnetization. So magnetization, M is nothing but your magnetic moment which you got upon nothing but the volume of it. The volume. That's it. The net magnetic moment per unit volume. Is this clear what magnetization is? Magnetization is how much moment is there, how much north-south polarity is there per unit volume. Okay, I hope this is very, very clear. Thank you, Krishna, for encouraging everyone to smash the like button. Like you can see over here, the numerator had a unit of ampere meter square. The denominator has a unit of meter cube in SI. So naturally, magnetic moment, when you cancel things, meters, you will be left with ampere per meter. Ampere per meter is the unit of magnetization. So if the magnetization is good, means for that unit volume, there are enough number of dipoles which are aligned in a particular direction. If the magnetization is 0, what does it mean? Means maybe they are all randomly arranged everywhere. So there is a possibility magnetization can be 0. For example, just think of this. Just think of these three things. Here, some materials are here, some is here, some is here, some is here. One is here, 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 one is like this, one is like this, one is like this, one goes here, one goes here. So if you notice, for everything there is an equal and opposite thing. So the net magnetic moment will be 0, and also even our magnetization will also be 0. But imagine this. Versus this. If you see, most of the atoms moments are aligned in this direction. So the net magnetic moment here is high, whereas here the net magnetic moment, even though it is there, it is going to be low. So hence over here the magnetization is less, whereas here the magnetization is basically going to be more. Is this absolutely clear? When more and more are aligned in the same direction, it makes sense that the net moment will be more. If it is not, it's more random, then the magnetization will be definitely less. I hope this is clear. So that is what they initially define. Magnetization of a material is the moment per unit volume. Then they talk about placing this material in some external field, which is probably, let's say, generated by a solenoid or something. So the net field will be some value, and then they give this particular formula. It is convenient to introduce another vector called as magnetic intensity, which is defined by this. Okay, we'll come to that also. This is called magnetic intensity, which is defined by this, where H has the same dimension as M, and it is where H is measured in, again, ampere per meter, and then B will become nothing but mu naught H plus M. This is exactly from here, we repeat our defining procedure. We have partitioned the contribution to the field inside the sample into two parts. One due to external factors, one due to external factors such as the current in the solenoid. This is represented by H, and the other due to the specific nature of the material named by M. The later quantity, nature of the magnetic material divided by M, the later quantity is influenced by the external factors, and then they express this, okay, and then they get some more things. So guys, there are a lot of formulas over here. I'll explain it to you in a very simple manner. First, let me block all the important things over here. This B is also mu times of H, and they also define something called as susceptibility. It's a measure of how magnetic material responds to external field. Okay, we'll come to paramagnetic, diamagnetic, etc. And then they also relate permeability over here. The magnetic permeability is mu, same as the dimensions of mu naught. Okay, now I'll explain all this in a very simple way. Observe guys carefully. You have some material. You have some material. You have some external magnetic field. You have some basically external magnetic field. I will call that external magnetic field as B naught. This is your external magnetic field. When it passes through the material, then it might ask these small teeny magnets to move and rearrange, reorient, and because of that, the material itself might have its own magnetic moment. The material itself might have its own magnetic moment and its own magnetic field. This magnetic field is called as your induced field or magnetic field by that material. Magnetic field by that material. So usually the symbol for that is BIND or magnetic field of the material. Why did this come? Because external field is influencing it. External field is influencing it. So now think there will be a net magnetic field. Now there will be a net magnetic field. Sometimes, usually you use the symbol B only. This particular net magnetic field, won't it be the sum of our external field plus the magnetic field which is created inside our material, which is BM? Everybody understands this? The net field inside this will be the external field plus the field created within the material. All of them together will create your net field. So this is the first formula which you should know. Till this point, everything clear? Till this point, everything clear? Very good. Now, what happens is, they have also mentioned right over here, this magnetic field which is created inside that material is proportional to the magnetic intensity. Where is it? Magnetization is proportional to the magnetization, and there is a relationship between both of them. So that magnetic field is mu naught into M. Basically, it means if the magnetic moment is high, then even the field created by that magnet around it, will also be high, which makes sense. So therefore, magnetic field created by the material is proportional to the moment, and this is given by mu naught into M. That constant only is called as mu naught. That is what they have clearly told in this particular formula. This is experimental, completely experimental. Now, what happens is, how can you create the external field? The manner in which you can create the external field, many ways are there. You can use a solenoid, you can use another bar magnet, you can do anything. So many ways are there. So if this external field, whatever this external field is there, if you divide this with the mu naught value, then what you get is basically your H, which is called as magnetizing field or basically magnetic intensity. So this is the formula for that. If you divide external by mu naught, you get the magnetizing field, and that is a vector quantity. That is basically the vector quantity. I'll give you a simple example. Imagine there is a solenoid and it has some current of 2 amperes and there are 100 turns per meter. Can we find the magnetizing field inside the solenoid? The answer is yes. H will be nothing but magnetic field which is there inside the solenoid by mu naught. But the magnetic field of a solenoid is mu naught Ni. So mu naught cancels and you will be just left with Ni. N is 100, current is 2. So the answer is 200 ampere per meter. So that is the magnetizing field of this solenoid. This is telling me how much I'm trying to magnetize whatever is kept inside that solenoid. Whatever is kept inside that solenoid, how much I'm trying to magnetize it, that is given by magnetizing field or magnetic intensity. The symbol is H. The symbol is H. Okay, this is what H is. It's a vector quantity. Now, the material itself will get influenced. The material itself will get influenced. We just spoke about it. The material itself gets influenced. And what does it create? It creates induced magnetic field or basically magnetic field of that material. If you divide that with mu naught, what you get is magnetization. What you get is basically magnetization. What you get is basically magnetization. Very important formula again. Just like you divide external field with mu naught, you get H. Same way, if you divide induced or magnetic field of the material divided by mu naught, what you get is magnetization. Exactly the same thing which is written down over here. If you divide this with mu naught, you get magnetization. Till this point, everything clear? Till this point, everything clear? Okay. Now just imagine you have taken a solenoid. It has created its own magnetic field. In that solenoid, you place some material. That material creates its own magnetic field. So that's why inside that material, there will be a net magnetic field. That's why inside that material, there will be a net magnetic field. That has the contribution of the magnetic field of that solenoid, obviously, which is basically your external factor. And it also has the contribution of that induced field, which is because of that material. Does that make sense to you? Everybody with me on this? Clearly? Very good. Now, the formula for this magnetic field externally, I can just write it as mu naught into H. The formula for this BM, I can write it as just mu naught into basically M. And what I get is the net field, which is just your total B. So if you want, you can also write it down as mu naught and common, that is mu naught is just going to be a common thing, and then you have just basically H plus M. You have basically H plus M. So this is another simplification which is exactly mentioned over here. Mu naught into H plus M. If you rearrange this, you get this. You rearrange this, you get this. So there is no need of remembering this formula. If you remember this, automatically you can get this. You can automatically get this from this. Did you understand how this equation basically came? Did you understand how this equation actually came? Net field is mu naught into H plus M. Very good. Now, lastly, there are last few terms which we are going to, define now. The last few terms are as follows. One thing is called as susceptibility. Symbol for that is X. It is nothing but susceptibility. X is defined as your magnetization upon your magnetization, whole thing divided by magnetizing field. If you notice, magnetizing field is nothing but how much field is given by the solenoid. That means how much you give. So it's like your input. How much field are you giving? How much you get outside? How much is it magnetized? Is what you are expecting. So that is like your output. So magnetization is your M. Magnetizing field is your H. Their ratio is what gives you X. So this is how susceptibility has been defined. Susceptibility has been defined. It is dimensionless, unitless quantity. Yes, thank you guys for reminding me. It is dimensionless and unitless quantity. Same way, there is also another quantity which is called as permeability, magnetic permeability, magnetic permeability of that material, mu m, which is then defined as, which is just defined as the net magnetic field, the net magnetic field divided by the magnetizing field, by the magnetizing field. The terms look very similar, often very confusing. So magnetizing field, the symbol is H, magnetic field formula is B, and what you get over here, that is nothing but your mu. So this is your magnetic permeability of that material. All these things you should definitely know. Magnetic permeability of the material. Now these terms can be used here and simplified further. How? Observe. We just saw that our B is nothing but mu naught into H plus M. So let's do one thing. Instead of B, let's put mu into H. Let's put mu of the material into basically H. Okay, as it is equal to mu naught into H plus M. Mu naught into H plus M. Divide the entire equation with H. Divide the entire equation now with H everywhere. With H. Let's see what do we get. H cancels, so we'll just be left with mu m. This will be mu naught, and then I will have H by H is nothing but 1. M by H, you might be wondering what is M by H. M by H is nothing but susceptibility. It is nothing but your susceptibility. Perfect. So permeability of any medium is permeability in vacuum into 1 plus susceptibility. We got this. This is the Important formula again. This is a very important formula again. If you know susceptibility, you can find permeability. If you know permeability, you can find susceptibility. And also you can do one small thing over here. Shift mu naught below. So mu m by mu naught will be 1 plus x. This is permeability of medium and permeability of vacuum. So this is basically called as your relative permeability. This is basically called as your relative permeability because it's just a ratio. So relative permeability is 1 plus x, or you can just remember this. It's one and the same thing. Okay. Either you remember this or you remember this. It's one and the same thing. So these are all the formulas which they have given, guys, in a little bit complex manner. So I have broken it down for you. So let's recap. Any charged particles revolving, they have a magnetic moment. Together, if you add the magnetic moments, you get the magnetic moment of the material. If you divide it per unit volume, it's called as magnetization. It is called as how much has it got magnetized, that is magnetization. Okay. And magnetization can be written down as how much field does it induce upon mu naught. How much field does it induce upon mu naught? Yes, it is also a vector quantity. It is also a vector quantity. How much field you give is called as magnetizing field, H. It is external field by mu naught. Using this and this, we get the total field as mu naught into H plus M. That is the net field. Further, we defined two additional properties of the material called as susceptibility, which is magnetization by magnetizing field, permeability as magnetic field by magnetizing field. Using these two, in this equation, we got permeability of the medium is permeability in vacuum into 1 plus susceptibility. That is what we got. Yes. Cool? Till this point? Great. So let's have a look at a question and then we'll come back. And then it's like hardly 15-20 minutes are remaining. We'll finish off this particular chapter. Okay. So yeah, we'll disperse for lunch break. A solenoid has a core material with relative permeability 400. The windings of the solenoid are insulated from the core and carry a current of 2 amperes. The number of turns is 1000 per meter. Calculate H, M, B, magnetizing current, everything. Okay. So first of all, guys, relative permeability is 400. Relative permeability is 400. That means mu relative, which is magnetic permeability of the medium by mu naught, that is basically 400. Okay. Solenoid is carrying some current. The turns are also given. Can you find H first? Yes, finding H is easy. H is nothing but external field by mu naught. External field is the field of the solenoid is mu naught Ni. So mu naught cancels. It just becomes Ni. So H will become number of turns per unit length, which is 1000, current 2. So therefore H will just become 2000 ampere per meter. Okay. Next, from here I get permeability of the medium is 400 into mu naught. I think H, mu are related to each other. H and mu are related to each other. Can you see this? Magnetic field mu m and H, they are all related to each other. So I can use this to find B. Therefore, since mu m is B by H, therefore B will be mu m into H. Mu m is 400 mu naught and H is nothing but your 2000. So that is what your H was. So you can substitute the value of mu naught also and you can get the answer. So 4 2s are 8. You have 2 zeros here, 3 zeros here. So it will become 5 zeros. Mu naught is basically 4 pi into 10 to the power minus 7. So if you want to write it like that, you can write it, or you can just leave it as mu naught. So that is our net magnetic field. So that is also done. Can we find M? Can we find M somehow? Just think about it. Can we find M somehow? Just think about it. Yes, is there a formula for M? Yep, let's go back. M is induced by mu naught. I need to find induced, but how do I find induced? That is the question, right? So over here, I know the net magnetic field. Okay, what do I do, guys? Think about it. To find out M, they would have done something like this formula. Remember this formula which we used over here? Yes. B is known, H is known, mu naught is known. You just have to find M. So use that formula over here. That's all. So our B is mu naught into H. H is nothing but 2000 plus your magnetization. In fact, this B also I already know. This B is 8 into 10 to the power 5 mu naught. Mu naught cancels. So you will just get 8 into 10 to the power 5 is equal to 2000 plus your M. So therefore M will be, yes, this was 2000, my bad, 2000. So M will be 8 into 10 to the power 5, guys. 10 to the power 3 is 1000. 10 to the power 4 is 10,000. This is basically like 1 lakh, right? So this is like almost like you have 1, 2, 3, 4, 5 zeros minus basically 2000, which is close to again 8,000 only. Sorry, 8 into 10 to the power 5. Just check this out. Yeah, approximately the same thing. It will not change much. Yes. So that is also correct. Because if you subtract 2000 from 8 lakh, hardly any difference. It's going to be the same amount. So we found everything, guys, right over here. Is that clear, everyone? So we've used that formula. Yep. Now, they have put a term called as magnetizing current. The magnetizing current is that additional current that needs to be passed through the windings of the solenoid in the absence of the core, which would give a value as in the presence of the core. This is very important. This kind of question can come. The magnetizing current is the additional current that needs to be passed through the windings of the solenoid in the absence of the core, which would give the same value as in the presence of the core. What does this mean? What does this mean? See, this magnetic field which you got was when there was some material inside. But when there is no material inside, you will not get this much field. You will definitely not get this much amount of field. So, if you see how much external field you will get by just by just passing 2 amperes, it will be much lesser than this. So I will need some different amount of current to get the same field. So say for example, I write like this: to get that same field through that particular solenoid, mu naught n, number of turns per unit length, is basically 1000 into the current. I don't know, this is that new current which I need to pass. So guys, mu naught cancels. This is just 1000. So what will be my new current going to be? What is that new current going to be? 3 zeros cancel, 3 zeros cancel. So I'm left with 800. Okay, that's it. Mu naught has cancelled. So the new current is 800 amperes. If you pass 800 amperes, you will get back this same magnetic field. So how much is that extra current that I have to pass? That is called as the magnetizing current. That is nothing but 8000 amperes. Earlier it was 2 amperes. So 798 amperes. So that is that current. So 798 amperes. I think we missed something. Why did I write 794? It should be 798, I guess. Okay, just check that out. Yep. It was 2 amperes, right? Yeah. Is that clear, everyone? Yeah. So in NCERT, what happens is sometimes they define some new term in a in-text question, like this magnetizing current. Earlier, they have not given anywhere. Suddenly, through the question, they have defined what magnetizing current is. Don't have to sit and by heart this formula, but just remember that what it means. It means to produce the same field, how much current will you pass without any material inside. That extra current is called as magnetizing current. Okay? Is that clear, everyone, till this point? Great. All right. So, that was this. Now, there are different properties of material and how they behave, etc. I will explain this to you in a very simple way. And in fact, they have discussed this right over here only. Somewhere here. Where did it go? Yeah, here. What is the meaning of paramagnetic, diamagnetic and ferromagnetic? Okay, so we are coming to that now. So what is the meaning of dia, para and ferro? So these three paragraphs are purely theoretical. So we have to go through this. So let's understand what do they exactly mean. Okay, now just imagine, all right, something like probably Pandus. This example I often give. A Pandu is like an atom. If his eyes are open, then whichever direction he looks is the direction of the magnetic moment. If Pandu closes his eyes are closed, if eyes are basically closed, then there is no magnetic moment. The magnetic moment is basically zero. Okay, the magnetic moment is a big fat zero. If he's seeing somewhere, that's where the magnetic moment is. If he's closed his eyes, just think as if the magnetic moment is zero. If there is magnetic moment, think as if there is a north pole here and there is a south pole here. If he looks there, north pole is there, south pole is here. Imagine a classroom with many such Pandus. This classroom is like your material. What is this classroom? This is like your material. Okay. Imagine a teacher comes into this classroom. Champa teacher comes into this classroom. This Champa teacher is like your external field. If Champa is inside the classroom, there is external field. If Champa teacher is outside the classroom, there is no external field. Is this analogy clear? I will explain now all the three materials using this particular analogy. So let's talk about the first material, diamagnetic, then we'll go to para, and then let's go to ferromagnetic. When you talk about diamagnetic material, what happens is, in that particular classroom, all Pandus, just imagine all Pandus are sleeping. And our Champa teacher is right now outside in the staff room. Our Champa teacher is outside in the classroom, which means external field is zero. All Pandus inside the classroom are sleeping. That means the magnetic moment is zero. That means the magnetic field which is there of the material, or basically the B induced, that is also zero. Are you able to understand? Because all of them are sleeping. They don't have north-south polarity. That means each and every atom has no magnetic moment. Now what happens? Basically, the teacher enters the classroom. Basically, the teacher enters the classroom right over here. What do these Pandus do? These Pandus, they basically look away from the teacher. That is very, very crazy. Such a disrespect. These Pandus look away from the teacher. So, the magnetic moment is opposite to where the teacher's influence should be. So, the teacher is asking, listen, I am creating a field like this. This is how the external field is, but the induced field is basically opposite to it. So, because of which the net field will be basically external field minus our induced field. It will be slightly less. It's as if they are repelled by the teacher, as if they don't like the teacher. The moment the teacher again goes out, the teacher got angry, again what do all the Pandus do? They again go back to sleep. They again go back to sleep. The moment teacher comes, oh, teacher is here, we'll look away. The moment teacher goes, okay, let's sleep. Teacher has come here, okay, we'll look away here. Okay, teacher has gone, okay, we'll sleep. Oh, the teacher has come there, we will look here. So that is what they are doing. Such a behavior is called as a diamagnetic behavior. Diamagnetic behavior. What will the teacher say? Go die. So that's why diamagnetic. The teacher will say, go die. So that's why diamagnetic behavior. Is this clear? So diamagnetic materials repel. Diamagnetic materials repel from the external field. If you ask me the permeability of that medium, the permeability of the medium will be less than mu naught, and the susceptibility is basically a small negative number. If you are wondering how does this come, well, look at this. Look at this. In fact, I can also put this. Relative permeability is less than 1 and susceptibility is a small negative number. How did I get that? Remember, relative permeability is 1 plus susceptibility. Because the field will become less, it is less permeable. It does not allow the field lines. So that's why relative permeability comes out to be less than 1. And if this is less than 1, that means this should be negative number. Think about it. If this is like 0.9, so this will be 1 plus negative 0.1. So that's why susceptibility is a small negative number. Got it? Clear? Okay, awesome. So that is basically diamagnetism. They have explained the same thing what I told you in a very, very boring way so that you will sleep, you will only become diamagnetic. Okay, but I have explained it to you. Same thing. Simplest explanation for diamagnetism as follows. Electrons in the atom are orbiting around the nucleus, possess orbital angular momentum. These orbiting electrons are equivalent to current carrying loop and possess orbital magnetic moment. Diamagnetic substances are the ones which result magnetic moment is there in the atom and it is zero. When the magnetic field is applied, those electrons having orbital magnetic moment in the same direction slow down and those in the opposite direction speed up. This happens due to induced current. It looks very scary, guys. It's not needed. All this not needed. Waste of time. Just remember what is happening. Okay. Now let's go to para. Everybody wants to become para now. Shall we go to the next classroom? Everybody wants to go to the para classroom. So what is happening in the para classroom? In the para classroom, each Pandu is looking somewhere or the other, lost. It's like one mental classroom only. One Pandu is looking, daydreaming. Another Pandu is looking here. Another Champa is looking at another Pandu. That Pandu is looking at another Champa. That Champa is looking at some other Pandu. Another Champa is looking somewhere here. Another Pandu is looking down here. Random. If you look at that classroom, you'll be like, what is this? Everybody is looking everywhere. So, there are magnetic moments, but if you count the total magnetic moment of that material, it will be 0. The vector sum. The vector sum obviously will be, the vector sum will be 0 as such. And this is when our teacher, Champa teacher, is outside. That means the external influence is not even there. Now the teacher enters inside that classroom, demands that influence She says, listen, I have come inside the classroom. So there is an external field here. These Pandus immediately and Champas, they align themselves in the direction of that particular teacher. Earlier, each one to their own. They were looking randomly. It was completely random. The moment teacher came, they aligned themselves in the direction of the teacher. So the magnetic moment induced is in the same direction. So what will you say about the net field? The net field will be just the addition of the induced field to the external field. They get attracted by the teacher. Teacher is very nice, very charming. So they are looking at the teacher. Okay, they are influenced by the teacher. The moment the teacher goes out again they will start looking here and there. Teacher comes in, they look. Teacher comes there, they all align like this. Teacher goes out, they look randomly. Teacher comes there, they all look here. Teacher goes out, again look randomly. Teacher comes there, again they look here. Getting my point? That is the behavior. So it exhibits temporary behavior. This is your paramagnetic. What will the teacher say? Teacher will say, such para students. In Hindi, they say pyara means very lovely. So the teacher says, such pyara students. Such pyara students, that's why paramagnetic. That's why paramagnetic. Got it? Everyone? Clear? In this case, the relative permeability more than 1, because it will be influenced in the direction where the teacher is. It is supporting the teacher, so helps, attracts, so permeability is slightly higher. That means the susceptibility is definitely a small positive number. It is a small positive number, definitely. Example of this, remember, relative permeability is 1 plus susceptibility. Imagine this is like 1.2. So this will be 1 plus 0.2. So susceptibility is like 0.2, which means it is paramagnetic. Extremely clear. Very good. So that is exactly what has been explained here, and they have also given which are paramagnetic materials. Then we come to ferromagnetic materials. Let's go to ferro classroom. Let's go to ferro classroom, guys. What is happening in this ferro classroom? What is happening in this ferro classroom? Let's see. In the ferro classroom, first the teacher is outside. So external field 0. Here the teacher, Champa teacher. Oops, what happened to Champa's hair? Okay. So the teacher is inside. She demands attention in this direction. So this is the direction of our external field. It is there. Here it is not there. In this case, what happens is, in that classroom, there is a weird behavior called as a domain behavior. Domain is like a group. A group of 5-6 students will be looking here. Another group of some 7-8 students are looking here. Another group of 2-3 students are looking here. Another group of maybe 10 students is probably looking here. Okay. Another group is probably looking here. Another group is probably looking like this. It's scary. Just imagine, guys, if you ever go to some classroom like this, imagine 5-6 students looking here like this. Mental people only. Another group looking here like this. Some 7-8 students. Another group of students, some 7-8 students are looking like this. Be like, sir, I think I came to a wrong hospital or something. It is not a school, sir. I think it is some mental asylum only. Look at these kids, sir. They have formed groups and they are looking like weird fellows. They are completely dope students, sir. What has happened to them, sir? Something is wrong. They are just staring at some wall or some ceiling. Something has gone wrong. Mental students only, sir. So this is basically domain behavior, guys. So each domain looks in one particular direction. The magnetic moments. This is another domain. 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 Another domain. Now what happens When the teacher, Champa teacher, Pavam teacher only, imagine she has to go and teach to such a classroom, what will happen? Gone only. So this Pavam teacher goes inside that classroom. What happens is, all the groups which had magnetic moments in that direction, like this group, this will start growing in the size. They will start growing in size. That means they will conquer other group members. This guy will say to this guy, hey, listen, why are you looking there? Teacher has come there, come join my group. So they will expand their group. The domains will basically expand. This guy will say, okay, I'm also looking at the teacher. Hey, listen, you three people, what are you guys doing? Come on, let's look at the teacher. Let's look at the teacher. These people might also, some of them might join, some of them might not join. But more or less you will see the groups will begin to expand. Groups will begin to expand in the direction of the magnetic moment. That is what you will see. Because of which the net magnetic moment which is induced is in the same direction. Is in the same direction as the external field. And what you will see, this net magnetic field is definitely the sum of our external field and our induced field. But this is much, much higher. This is much, much higher than the paramagnetic case. And the best part is, if the teacher leaves the classroom, what do you think they will do? Will they come back to their original groups? Remember, this guy had said to this guy, listen, don't look there. Teacher has come, look here. So they started looking there. When the teacher leaves, what will they do? They won't change. If the teacher came, one group member who was looking here, started looking here, that's it. They have joined the group, guys. They will not change. So they assume permanent magnetic properties. So that is why ferromagnetic materials, are used to make permanent magnets, full mental only. Imagine these group members got conquered, now everybody is looking here. Everybody is looking here. It will be scary, guys. Got it? Clear? So it exhibits permanent behavior. Permanent behavior, even if the teacher leaves. Such cases, susceptibility and relative permeability. Well, relative permeability, of course, is much, much larger than 1. Susceptibility is much, much larger than 0. Like 200, 500, that is how the order is. Is that clear? So that is exactly what is explained here. Domain. See, such boring things. Such boring things. Okay, they have mentioned here. Who are ferromagnetic, etc. is mentioned here. After this explanation, read this theory. Trust me, you will never ever find this difficult. Now, this chapter deals with something called as electromagnetic waves. What is this electromagnetic wave? And where is it used? In fact, it is used everywhere. Even my mobile emits electromagnetic radiation. It also receives electromagnetic radiation. Forget that, even me right now, I am emitting electromagnetic waves and I am receiving electromagnetic waves everywhere. The light is there. Light is also electromagnetic wave. So electromagnetic waves are there completely around us and we depend on it in many, many different ways. And right now, in this particular introduction part, you will see that we have so far considered direct current sources. These do not change the direction with time, but voltages and currents which change with time are very common and they are used in our homes, offices, etc. like a sine function with time. Such a voltage which, oops, I think this is AC by mistake, this introduction. So sorry guys, this introduction was supposed to be changed. I am not sure why it was not changed. So sorry, that introduction is of AC, my bad. Alright, so in this particular chapter, like I said, you will be learning about electromagnetic waves, the application and the wave theory behind it. And one of the main person to talk about electromagnetic waves was James Clerk Maxwell. And I'll tell you one very interesting story. I don't know how many of you know this. Everybody wants to listen to a story. All right, let me tell you. J25, well, not problem-wise J25, theory-wise this should be enough. Yeah. Okay. So long time back, it was Newton who said that light behaves like a particle. Light behaves like a particle. But on the other hand, there was a person called as Huygens, and Huygens said that light behaves like a wave. And to uh, show that light behaves like a wave, in fact, there were many setups or there were many experiments to prove it likewise. And one such was done by Young. So Young performed the name of the person is Young. It's not an adjective, it's a noun. So Young was Thomas Young. He performed an experiment to show that light behaves like a wave, but people thought, no, how can you talk against Newton? It is wrong. So they thought something is wrong with these people only. So they believed, this is 200-300 years back, they thought light is a particle only. Even when Young proved it otherwise. Then there were other people like Fresnel and other scientists, okay, who proved that light is a wave. Still for the next couple of 100 years, people thought that something is wrong with these people. What Newton said only is correct. Light is a particle. Then what happens is, Maxwell comes into the play. Maxwell comes into the picture. Even before this, there were even more scientists. I have not mentioned all the names. All right. So Maxwell comes into the play, and he proves that light is a electromagnetic wave using some equations. So after some 100-200 years, people realize, oh, Newton was wrong. Actually, light was a wave. These people were correct. So that was how crazy things were back in history. But then there is always a party pooper, right? So to spoil the party, who came is basically Planck and Einstein. Einstein through photoelectric effect and Planck through the quantum theory proved that light is a particle, and the particle of light is called photon. And Einstein even won Nobel Prize for photoelectric effect, not for theory of relativity. So then people thought, what the hell? We thought Maxwell was correct. He disproved Newton. So was Newton right after all? Then people understood after all of this, listen, light has nothing but dual behavior or dual nature. Yes, dual nature. Sometimes it behaves like a wave, sometimes it behaves like a particle. And when I say it behaves like a particle or behaves like a wave, what exactly do I mean? See, when something is behaving like a particle, it has momentum. When it hits something, it applies a force. It makes its presence felt by the touch or that momentum or that impulse, right? So these are particle-like behaviors. But what is wave-like behavior? Wave-like behavior is where, you can say that it will get diffracted, refracted, reflected. These are properties of waves. So when a wave goes from one medium to another medium, it refracts. When a wave enters a small gap or a hole or around a corner, it will spread. That is called diffraction. All these properties were also shown by light. So that is why then it was concluded light has dual behavior. Like some of us have in the school, we are full mischievous. We are on our full excitement levels, and we are doing a lot of hangama masti. We are doing so much of fun. We are pulling each other's legs. But at home, very silent. So dual behavior. You might have seen some friends of yours at home, suddenly because of their parents or whatever reason, suddenly very quiet. You are only surprised. What is this? This is my friend. He's so quiet here. And then in the school, full masti, full on his or she's enjoying. So that is basically dual behavior of light. And what we talk about is Maxwell's electromagnetic wave theory. That is what we are going to talk about. And in that electromagnetic wave theory, there is one important concept called as displacement current and how he gets through it. And they have explained that displacement current concept and the modified Ampere's law modified Ampere's law. So you can see this is Ampere's law, and the total current is a sum of two different currents, and one of them current is called as the displacement current. All these things I will explain. And he modifies the Ampere's law into something like this, and he is then able to prove all of it. So what is exactly mentioned over here? Let me explain, guys. Let me explain. Okay, in the first few parts, because a lot of people do not really understand it. If you recollect Ampere's law, then if you have a wire which carries some, basically carries some current, and then you take a loop across it, that loop is basically a path. So you go around this particular path like this. This is called as an Amperian path, which is basically a closed path. And along that path, you will start seeing some magnetic fields. Maybe like this. And these magnetic fields, if you integrate it with respect to the small path lengths by taking a dot product, and you cover that entire closed path, that's why cyclic integral, what you get on the right hand side is permeability into the current which has been enclosed. This is exactly what your Ampere's law was. I hope you remember it. It's a small recap of that. Dot product of magnetic field with the path length around that loop is permeability into the current which passes through that particular section. That is what this is all about. So when I say passes through the section, what do I exactly mean? If you visualize a thin film which is being formed by that loop, imagine you take a wire frame or you take some object and you dip it in a soapy liquid, a film is formed, soapy film is formed. So imagine this to be like that soapy film, and this particular current is piercing that soapy film over here, So then that current is called as the enclosed current. But then, is it necessary the soapy film has to be a flat surface? The answer is no. Imagine there is a wire like this carrying current. There is a wire like this carrying current. There is a wire like this carrying current. In all the three cases, let me take my Ampere's loop law. All right. Okay. In the first case, let my film be like this. So the current pierces it right over here before coming out from behind of it. In the next case, what if my soapy film is slightly more curved? What do I mean by that? Observe this carefully. Slightly like this, or what if it is like this? Are you able to visualize that curviness? That solid shading is basically the inside of it. So the wire will go through it like this. It might pierce through it over here. The wire might go through it. It is not piercing here. It is not even piercing at this structure for this particular surface, because the wire abruptly is ending over here. Maybe. So now, if you look at all these three diagrams, is the enclosed current same in all three of them or not? Are you saying that the enclosed current will be same or will it be different? If you notice over here, in this particular structure, when the film is flat, the enclosed current is basically I only. Here, it might not intersect this part. Well, it is intersecting this curved part somewhere here. Fair enough. Still, that enclosed current is I. But imagine if this was like a capacitor. Imagine this was like a capacitor which is there, or some wire is abruptly ending over here. It is not exactly intersecting at this point. Even if the current is I, then the problem is the enclosed current will not be I because it is not piercing through it. There is no piercing. There is not intersecting that surface. It is not intersecting or cutting through it. It is not intersecting or cutting through that particular surface. So then, what exactly is my definition of enclosed current? What exactly is something wrong with it? The answer is nothing is wrong with my definition of enclosed current. Enclosed current is defined in such a way that if you take that Amperian path, you make a film, whether it is flat or curved, that wire must intersect it somewhere or the other. That wire must intersect it somewhere or the other, either here or over here or at that flat surface. Somewhere or the other it should intersect. But if it is not, then what to do? If it is not intersecting, then what to do? Here comes the solution. Well, observe this carefully. Observe this carefully. Imagine there is a wire which carries current. Imagine there is a capacitor, something like this. This is a capacitor. This is a capacitor. And somebody has taken an Amperian loop like this. Somebody has taken an Amperian loop like this. And our film which is there, it goes like this. It goes like this. Now, the problem is, this wire is not intersecting only that surface. So, if somebody applied Ampere's loop law and said cyclic integral B dot dl, B being B only, is equal to mu naught into I enclosed. The problem with this approach is that at all these points you still have magnetic field as before. The magnetic field is still there. The magnetic field is as it is and should not depend, and it should not depend on the choice of the Amperian loop or its curvature. Curvature as in whether it was flat, whether it was curved like this. Whether it was flat, whether it was curved, whether it was more curved. It should not depend on that. It's like saying, because I changed the sign convention, so my velocity in kinematic equations is 100 meters per second instead of 20 meters per second. That should never happen. If the car was moving at 20 meters per second, no matter what origin you take, no matter which direction you take positive, you should always get the car's speed as 20 meters per second. It should not depend only on those references or those origins or what is positive and negative. Same way, this magnetic field around this region, why should it depend on whether it is flat or curved or not? Because this was just an Ampere's loop law which was just made up. So that is the reason why we have to think a little bit differently. And when you take a curved surface like this, then you might be wondering, sir, there is no enclosed current in this case. Obviously, this is a big fat zero. So how is it that the RHS is 0 and the LHS is not a 0? not a 0. How is this possible? This cannot happen. The LHS has some magnetic field, but RHS has 0 term. So something is not matching over here. So definitely our LHS is not matching the RHS. RHS is 0 and LHS is obviously not 0. So to overcome this trouble, they finally understood where we were going wrong. The place where we are going wrong is that there is a missing term in the Ampere's loop law equation. Yes, there is a missing term in the Ampere's loop law equation, and the missing term is as follows: plus something called ID. Something called ID. This is basically called as your displacement current. Displacement current. And this displacement current is not 0. This particular displacement current is not 0. And in that peculiar scenario, you will see LHS will match the RHS. I'll explain to you what is this displacement current, but for now, understand there was a missing term because of which we never got LHS equal to RHS. So, what is this displacement current? This displacement current is due to changing electric fields. Changing electric fields, which creates magnetic field. Which creates magnetic field. Very, very interesting thing about displacement current. Observe this, what I'm trying to say. If you have just taken a charge, obviously it will create some electric field around it. It will definitely create some electric field around it. But let's say somebody, moves this charge from here to here. Somebody moves this charge from here to here. In this process, what will happen is that at any point, if you see the electric field at this point, due to this charge before was here, but due to this charge after some time will be here. This was electric field initially, this was electric field finally. So definitely there is a change in the electric field. This change in the electric field induces, that means it creates a magnetic field. This creates a magnetic field. But do you remember, we always have spoken that magnetic fields are created by whom? Magnetic fields are usually created by whom, guys? Magnetic fields are created by currents. Magnetic fields are created by currents. But here magnetic field is created by electric field. So we define a term called as displacement current. A displacement current is that physical current which would produce the same magnetic field as the changing electric field. So over here, if there was some kind of magnetic field which was created, that magnetic field which is created by the same current by a physical wire, that is then called as displacement current. It is not because of an actual current, but it is like the current which will produce the same magnetic field. I hope this is clear. This is like a substitute. You can think of it like a alternative, like a substitute. It's that alternate current, that substitute current, that current physically which produces the same field, magnetic field, that current is called as the displacement current. I hope this is absolutely clear. Hello Umesh, welcome. Yes. Is this part understood, everyone? So displacement current is due to changing electric fields which creates the magnetic field, and the value it is basically nothing but, you know, that current which produces the same magnetic field over here. So now our equation looks fine. Okay, there is displacement current, but your question will be, sir, what is that value of that displacement current? We can find that out very easily. It is not that big a deal, because see, the thing is LHS has not changed. So basically, you know, LHS has not changed. So basically, if you see over here, if you take a flat surface, then the enclosed current would have been I. But if you take a curved surface, then the displacement current should be I. This, understand, in the first case, if you take a flat surface, nothing is passing through the empty space between the capacitor, then the displacement current will be 0. But if you take a curved surface, then the enclosed current will be 0, but the displacement current will be I. Why? Because LHS is same, magnetic field did not change, so RHS should not change. So I plus 0 or 0 plus I, one and the same thing. I plus 0 or 0 plus I, one and the same thing. Keep that in mind, so that our LHS is not affected. Keep this in mind. So lot of times you will see this. Is the enclosed current value the same as the displacement current value? Yes, you can see that it is the same. But when this is there, this is not there. When this is not there, this is there. They substitute. That's what I told. It's like an alternative. It substitutes the enclosed current. Okay. So what is this value of this displacement current? How do I find it? This is also I. This is also I. So therefore, ID will be equal to I enclosed. I enclosed is basically that I, which is also dq by dt, rate of flow of charge. What is charge? What is charge? Q is CV. So I can write it as capacitance into voltage divided by dt. Okay. Can I do something with this? Yes, capacitance can be taken outside and we will have dV by dt. Capacitance is epsilon naught A by D. What is voltage dV by dt? Can I do something with this? Yes, I think I can do something with it. Think about it. Think about it. Can I do something with the voltage? Voltage is nothing but voltage. Well, electric field was dV by dx. Electric field was dV by dx. So dV will be EDX. dV will be EDX. So think of it like that. Yes. So that is one thing I can do. So instead of this, I can write it as electric field into that distance. Now electric field into that distance will be exactly this D, you can say. That distance will be basically D over here. And actually over here that D will come instead of dV. So think of it like this. Think of it like this. This voltage is nothing but, I'll just rewrite it again before. This voltage is nothing but electric field into distance. Electric field into distance. Don't get confused with this D and this D. This is derivative. This is distance between the plates of the capacitor. Okay. So what will happen is that D, if I take it outside, it will become epsilon naught A by D. That D is outside, and then we have basically dE by dt. This D and this D got cancelled. Now take this area inside, it will become epsilon naught D by dt of EA. Now what is electric field into area? What is electric field into area? Electric field into area is the electric flux. So it will be d phi of electric flux. Yes, by dt. So therefore the displacement current is permittivity into rate of change of electric flux. Permittivity into rate of change of electric flux. So that is the derivation for that, and hence I usually will write it over here. This particular displacement current is nothing but permittivity into rate of change of electric flux. This is permittivity into rate of change of electric flux. Electric flux, very, very important. Rate of change of electric flux. Sometimes this enclosed current, sometimes this particular enclosed current is also called as, this particular enclosed current is also called as the actual current, which is therefore called as conduction current. Conduction current is the actual current. It is the due to the flow of charges. So it is due to the flow of charges, whereas the displacement current is due to changing electric field. It is not due to charges, it is due to how electric field is changing. So there are two different things. So enclosed current is your actual current, conduction current, and displacement current is epsilon naught d phi by dt. So this becomes your modified law for Ampere. Earlier our Ampere's law was like this. So now it has been modified. It has been modified by adding one extra term over here and making the entire equation correct, no matter how curved or flat your surface is while measuring enclosed current. So now with this, what we have done is we have modified Ampere's law. So the modified Ampere's law will look like this. Modified Ampere's law will look something like this. Integration of magnetic field with respect to the path length is a mu naught into the actual conduction current plus permittivity into rate of change of electric flux. This is your modified Ampere's law. Then Maxwell wrote the Gauss's law also, the Gauss law in electrostatics. Gauss law in electrostatics, which looked very similar to this. Instead of magnetic field, you had electric field. Instead of length, you had the area vector. This was the electric flux, the total electric flux of the closed surface. This was always the charge which is inside or enclosed by permittivity. Then there is also Gauss law in magnetism. Gauss's law in magnetism, if you remember, and that was integration of magnetic field with area, which is the total magnetic flux on a closed surface, is always going to be 0. We have seen this in the chapter of magnetism. And the final law was your Faraday and Lenz's law. Faraday and Lenz statement, which said that the EMF, which is induced is negative rate of change of the magnetic flux. This is magnetic flux, how quickly the magnetic flux changes. And this EMF induced in a loop, can be also written down as integration of dV, V being the voltage, but it's a loop. That's why this cyclic integral, it's a loop, right? So closed integral of the voltage in that loop is minus d phi by dt. So these equations are there in your electromagnetism, and these four equations alone define the entire electromagnetism unit. And this is exactly what Maxwell used. That's why they are also called as Maxwell's equations. He combined these equations together, and then he was able to prove using these equations light is an electromagnetic wave. Right now, I know looking at these equations, it looks like as if a cockroach was dipped in some yellow and orange ink and it was asked to run over this board randomly. But it is not like that. These equations actually have a lot of meaning. We have seen this. This is the substitute for Coulomb's law. You can derive anything based on this. in electrostatics. This was for magnetic field due to currents and due to changing electric fields. This is for just magnets, how the magnetic field lines behave, and this is how when magnets move around here and there producing some changes, how is that electricity created. The entire of electromagnetism physics is right on this particular board. And he said that electric and magnetic theories are not separate, rather they are interlinked with each other, rather they have some common connection between them. And you can see one side you have electrostatics, voltage, other side you have magnetism. One side you have electrostatics, other side you have magnetism. So they are interlinked to each other. That's what Maxwell was able to say. I hope this is absolutely clear. So this is what is given over here, right? Exactly the same thing. Maxwell's equations. Maxwell's equation. So he was able to say that of this existence of electromagnetic waves, which we'll discuss right now, and all these equations, he was able to prove that light is an electromagnetic wave. Cool. So that is what is there in the starting part of the chapter. All right. So, sir, can we get some questions on this? Yes, you might get some very laddu-paddu questions on this. Something like, say for example, if electric field is 5t square, area is 2 meter square, this is volt per meter, can you find the displacement current? Can you find the displacement current? How do you solve this particular question? Let's go by the pure definition of displacement current and the formula. The displacement current is permittivity into rate of change of the electric flux. But wait a minute. Electric flux, I think I already know the formula for electric flux. It's nothing but electric field into area. Oh, do I know the electric field? Yes, why not? It is right over here, guys. It is right over here. So derivative of basically 5t square. Do I know the area? Yes, why not? It is basically 2. Okay, perfect. So 5 2s are 10. So it will basically become 10 times of E naught. And I'm just left with the derivative of t square. Derivative of t square is nothing but 2 times of t. 10 into 2 is 20. So 20 epsilon naught t is nothing but the displacement current. If you want, you can substitute the value of epsilon, which is 8.85 10 to the power minus 12, okay, and multiply it with 20. And if time is given, you can multiply with time. You will get the answer for the displacement current. I hope this is clear. Yes. Oops. Cockroaches. I don't like in the chats. I get scared, especially when they fly. Okay. So very straightforward, guys, and let's go to the main topic, which is electromagnetic waves. So how do electromagnetic waves look like? What is their equations and other parameters? In the NCERT, the way they have presented is so boring. I don't like it. So let's just have a look at Kapto's diagrams and Kapto's way of explaining, of course. So let me just block few things over here, like you have the electromagnetic wave equations, K definition. Okay. You will also see E and B are perpendicular. Okay. All these things, omega is 1 by this equation, all these things are there, and then there are problems. So let me explain this to you. Basically, imagine light to go in this particular way. This is the direction in which light is going. So this is light ray. If you have seen ray optics, you show rays of light, right? So this is the light ray. This is the direction in which the light is going. What is this c, you might ask? This c is nothing but the speed of light. This is nothing but the speed of light. And we know in vacuum it is 3 into 10 to the power 8 meters per second. When any electromagnetic wave, meaning light, X-rays, gamma rays, Bluetooth, Wi-Fi, infrared, ultraviolet, red color, blue color, white light, anything, thermal radiation, long radio waves, short radio waves, microwaves, all these waves, when they travel, they have very similar characteristics. If they are traveling like this, you will see probably the electric field going like this, up and down. And you will see the magnetic field going left and right. This one is magnetic field. This one is electric field. You will see electric field, magnetic field, and the velocity of light. All three of them are mutually perpendicular to each other. Mutually perpendicular to each other. This is how an electro, yellow one, magnetic, the green one, electromagnetic waves propagate. If somebody sees it from behind, imagine there was an observer, or maybe from the front also, doesn't matter. Imagine somebody had to see this from behind. What would that person exactly notice? That person would see that the electric field is continuously changing up and down. It's continuously going up and down, and the magnetic field is continuously changing left and right, and the light ray is going away from him, something like this. The light ray is going something like this. If the electric field at any instant is like this, then the magnetic field at that instant will be like this. And if the electric field is downwards, then the magnetic field will be towards the left side. How do I know magnetic field is right only when electric field is up and not towards the left side? There is a simple rule for that, and that is electric field and magnetic field, if they are cross-producted with each other, the vector that you get is always going to be parallel to the velocity of the light. Notice electric field is on the top, take the right hand, cross-producted with magnetic field, the thumb goes inside, so that's exactly the direction of the velocity of the light. Here also, if I do electric field cross magnetic field, the thumb goes exactly here, exactly what I am expecting it to do. How does it actually look like? For that I have created, I'm using a simulation over here. I can see electric fields or magnetic fields. Look at that. See how electric field is continuously changing up and down like a wave. This is electric wave. Similarly, look at this magnetic wave. See how the electromagnetic wave is traveling in this direction. Now let's see both of them together. One is in one plane, other is in perpendicular plane, and the wave is traveling in the third direction, mutually perpendicular. Don't worry, Krishna, chumma kidding, man. Yes. Now, how will it look like if they move? We'll see that, but let me show you the planes. Can you see the electric field wave? Can you see the magnetic field wave? Can you see that this green plane is perpendicular to the red plane of the magnetic field? Correct? Now let's see what happens if they start moving. See, this is how they go. So if you are standing at one point, suddenly the electric field is increasing, decreasing. Magnetic field increasing, decreasing. So at any given point, the magnetic field and the electric field will keep changing. How quickly they change gives me the frequency, the distance between two crests or two troughs. Gives me the wavelength of that wave. So when you are seeing light, Exactly, this is what is entering your eye. Electric and magnetic fields are entering your eye. When you see beautiful colors, they are just electromagnetic waves of different wavelengths. Yes, they are of different wavelengths. That's all. Is this visualization absolutely clear? Everybody with me? Yep. Cool. Beautiful simulation, right? Amazing it is. Yes. Not just that, there are some more things that you should obviously know about this. This electric field has an amplitude, let's say E naught. Then the electric field's wave equation is given by E naught sine or cos, anything you can use, sine or cos. And then you have, you have kx minus omega t. Similarly, if the magnetic field has a maximum value of B naught, that is the amplitude of the magnetic wave. So the magnetic field is given by B naught. If you use sine here, use sine. If you use cos over here. Doesn't matter what you use, but this is how it is. If you put kx here also, minus omega t. That's it. It can be plus also. So I'll put minus and plus both, depending on the direction of which it is moving. What is this E naught and what is this B naught? E naught is nothing but electric field's amplitude, the maximum value of the electric field. Any wave has an amplitude, right? So same thing. So this is nothing but magnitude of the magnetic field's maximum value, or you can say magnetic field's amplitude. What is E and B? E and B are the current values of the electric field and the magnetic field. Meaning, say for example, you are somewhere over here and let's say, you are interested what is the magnetic field at this location, what is the electric field at this location, and this point is at some distance from the origin. So that distance is basically x. This was, let's say, our origin. X is how far you are from the origin. So at that location, what is the instantaneous values? So what are these? These are basically instant values of the electric field and the magnetic field. What is this K? What is this omega and all these things? We'll come to that as well. Don't worry. Yes, what is this K and all these other things? So, yes, this K is 2 pi by lambda, which is also called angular wave number. And the unit of that is how many radians are there in a meter. K is 2 pi by lambda, lambda being the wavelength. Lambda is the wavelength. Yes, is the wavelength. Correct. Is the wavelength. What is omega then? What is basically omega then? Omega is 2 pi by t, which is also 2 pi into f. That is called as angular, we have seen this word, frequency. Angular frequency. Unit is radian per second. What is this f? F is just called frequency, not angular frequency. Angular frequency is radian per second. Frequency is just per second. Frequency is just how quickly it goes up and down. That is what these terms are. Apart from that, you should know one more thing, and that is if you use a plus sign, remember it is moving along negative x-axis, and if you use a negative sign over here, that means the wave is going along positive direction of the x-axis. So it is exactly opposite. If it is negative, that means the wave is going towards the positive side. If it is positive, then the wave is going along the negative side. So it is always opposite, the signs. Be careful about it. Next important thing which you should know. Over here. If you divide E with B, if you divide electric field with magnetic field, it is as good as saying you are dividing electric field amplitude with magnetic field amplitude. Both of them will be in the obviously same ratio. If I divide E with B, E naught with B naught, same thing, because this and this will get cancelled. This ratio is exactly what is going to give me the speed of light. This is exactly what is going to give me the speed of light, which is also f times of lambda, frequency into wavelength, which is also omega by k, angular frequency by angular wave number, which is also 1 by permeability and permittivity. So what is new over here? This is permeability, not refractive index, permeability, and this one over here is basically permittivity. Yes, permeability into permittivity. All these things will give me the same answer. This you already knew. Speed of any wave is frequency into wavelength, also omega by k from the chapter of waves. E by B, E naught by B naught, one and the same thing. This is something which you are learning new, either this or this. Keep this in mind. Also, you need to know one more thing. The amount of electrical energy per unit volume. If you take 1 meter cube of space, how much electrical energy it is carrying will be exactly equal to how much magnetic energy it carries, per unit volume. Do we already know the formula for electrical and magnetic energy? I think we already know. Electric energy per unit volume is given by half epsilon naught E square, and magnetic energy per unit volume is half B square by mu naught. Half of cancels, and if you notice what happens over here is that you get a very interesting thing. On the top you have electric field square. Take this permittivity below. Magnetic field you take it below over here, and this mu naught keep it as it is over here. In the next step, what will happen is, guys, a very interesting thing. This will be, if you take root on both sides, this will be electric field, this will be magnetic field, and on the right hand side what you will have is 1 by root of mu naught and epsilon naught, exactly what you got over here. That's how you prove E by B is exactly this. That's how you prove electric field by magnetic field is 1 by permeability into permittivity of that medium. Correct. And also keep in mind one more thing, and that is the total energy. The total energy will be the sum of magnetic and electrical energy. So whatever electric energy per unit volume or magnetic energy per unit volume you are finding out, that will be basically half of the total energy of the electromagnetic wave per unit volume. I hope this is Absolutely clear. Okay, total energy will be electric and magnetic energy sum. So electric will be half of total energy, magnetic will also be half of the total because both of them are present in equal amounts. So these are the only formulas and the things which you should know regarding electromagnetic waves. And then there are some questions on it. Let's have a look at the questions, my dear warriors. Okay, see, example 8.1. A plane electromagnetic wave of some frequency travels in space in x direction at a particular point. Electric field is 6.3 J cap. What is magnetic field at that point? Okay. In this particular question, electric field is given, magnetic field is asked. Oh, thank you for reminding me to have water. Thank you guys. We know electric field by magnetic field is speed of light. So magnetic field is electric field by speed of light. Electric field is 6.3 volts per meter. And speed of light we already know is 3 into 10 to the power 8 meters per second. So dividing both of them, that's exactly what they have done. 6.3 divided by 3 into 10 to the power 8. They get the value of magnetic field as 2.1 into 10 to the power negative 8 Tesla. So we found the magnitude of the magnetic field. But that's not all. We have to also find the direction of it. So I have an idea. See, where is the electric field direction? Electric field is in J cap. Electric field is basically in J cap direction. Where is the velocity of the light? Electromagnetic wave is going in X direction. So the velocity of the light is basically in the I cap direction. And we know magnetic field should be such that the electric field crossed with the magnetic field should be parallel to the velocity of light. Oh, so J cross something should give me I. J cross something should give me I. J cross obviously K cap. J cross basically K cap. Think about it. If this is K cap and if this is J cap, J cross K, what does it give you? It basically gives you nothing but I cap. So hence magnetic field must be along the K cap direction. So yes, the answer is 2.1 10 to the power minus 8, but in the K cap direction. Okay, so this property I have used over here. I just gave it to you. E cross B is parallel to C. This is what you have used. Okay, in this particular example, you will see many questions on that as well. Next question. The magnetic field is given by this 2 10 to the power negative 7 sine 0.5 10 to the power 3x plus 1.5 10 to the power 11, I think so 11. Okay, T. What is the wavelength and frequency? Write an expression for the electric field. Okay, let's do it step by step. First, let's find what is the wavelength and frequency. Compare this equation with B is equal to B naught sine, okay, kx plus omega t. The moment you compare, you will understand B naught is 2 into 10 to the power negative 7. K is nothing but 0.5 into 10 to the power 3. Omega is nothing but 1.5 10 to the power 11. So immediately B naught is this is basically K and this is basically omega. So now what we can do, K formula we know. What is the formula for K, guys? I had given you. K is nothing but 2 pi. K is nothing but 2 pi divided by lambda. So therefore lambda will be 2 pi. Will be nothing but 2 pi divided by this number, which is 0.5 10 to the power 3. That's it. So 0.5 is half, 2 2s are 4, so it will become 4, it will just become 4 pi by or into 10 to the power negative 3 meters. So lambda is that many meters, which comes out to be 1.26 centimeters. Okay, so that is how you find lambda. Similarly, you can find frequency, because this is omega, omega is nothing but 2 pi, omega is nothing but 2 pi into f. Therefore, frequency will be 1.5 10 to the power 11 divided by 2 pi. That's it. So from this you will get the frequency, and they have got the answer as 23.23. What is happening to my board? 23.9 into 10 to the power 9 hertz. Now 10 to the power 9 is a giga. 10 to the power 9 is basically a giga. Yes, that's how you do this. Alright, so this is also done. Now the first part was done. First part is taken care of. Let's go to the second part. Write the expression for electric field. See, electric field equation should look exactly similar, just that here you will have E naught and here you will have sine kx plus omega t. Omega I know, k I know, E naught I don't know. So what do I do for E naught? There is a simple trick. Because I know electric field by magnetic field is C, therefore E naught by B naught is also C. So E naught is C times of B naught. Speed of light 3 into 10 to the power 8. Magnetic field's amplitude 2 into 10 to the power negative 7. 3 2s are 6, and you will have basically 60. So 60 volts per meter. 60 volts per meter is basically E naught. Therefore, E will be, instead of E naught, I will put 60 sine k value already known, 0.5 into 10 to the power 3x, omega value already known, 1.5 10 to the power 11 into time. That is the answer. That is exactly what they have done. Is this clear, my dear warriors, how to do this question? Alright, everybody with me? Very, very straightforward. Great. Awesome. So these are the kind of questions you can expect, and then we talk about the electromagnetic spectrum. It's a very important thing you should know about electromagnetic spectrum. Now, although this diagram is not so colorful, maybe I can get the diagram of electromagnetic spectrum. To show you what I exactly mean. Okay, this looks like a good diagram. This is also fine. Look at this. This is a beautiful diagram to explain you what is electromagnetic spectrum. See, you should realize by now from all these discussions that since speed is equal to frequency into wavelength, and all of the electromagnetic waves have the same speed in the same medium, in a given medium, all of them have the same speed, which means if something has very low frequency, it will have very high wavelength. Whereas something which has very high frequency, like this, will have very short wavelength. I hope this is absolutely clear. But in 1 second, if it has traveled 3 lakh kilometers, even this will travel exactly 3 lakh kilometers. The distance that they travel is the same, the wavelengths could be different, frequencies could be different. So something is oscillating very quick, the wavelength will be very small. Something is oscillating very slowly, the wavelength will be very large. They are both inversely related to each other. So, different waves have different wavelengths, and their usages, their phenomena, their applications, how they are generated, where do you see it, all these things are also going to be different. Like obviously blue color is different from yellow color, is different from infrared, is different from anything else. What you see around you is only this much. It's a small portion of all the possibilities in the universe. You can have a wavelength of 1000 kilometers also. That's called as a long radio wave. You can have wavelengths of the size of buildings, earths, few hundred meters, huge wavelengths. They are called as long radio waves. That's what you will see over here. Long radio waves, their wavelengths is in tens and very, very high powers of 10. You can make the wavelength shorter, it becomes a short radio wave. You can make it even shorter, it becomes a microwave, meaning few centimeters or millimeters. If the wavelength is a few millimeter, then it becomes like a microwave. You make it even shorter, you take it to few nanometers. In the range of nanometers, you go to infrared. You make it even shorter, it becomes red. Then you have orange, yellow, green, then blue, violet. All these colors will come. You make it even shorter, it becomes ultraviolet. Ultraviolet, yes, it's going to be very, very small. It will be very close to a few angstroms. Yes, it will go to a few angstroms. Then you go to X-ray, it will go to even lesser than an angstrom or in the range of angstroms. And you go even smaller, it goes to femto, FM, 10 to the power negative 15th of a meter. And you go even smaller, you go to cosmic rays. It is not shown here, but that is also there when you go to very, very small wavelengths. If you talk about frequency, this is the highest frequency because the wavelength is small. Here, the frequency is very less because the wavelength is very large. So you can see one goes up, the other goes down, this goes down, the other goes up. Inversely related to each other. Is the electromagnetic spectrum clear to you? What you say is only this part. This is called as the visible spectrum. These rays, you can't see them. These rays, you can't see them. Just because you can't see them does not mean they do not exist. This range is from 400 nanometer to 700 nanometer. Now, who is 400, who is 700? I'll tell you that also. This is roughly 400 nanometers and the red wavelength is around 700 nanometers. That's such a small range in the world and the universe of possibilities. So you now know you should definitely have some kind of FOMO because you are really missing out on so many wavelengths which are around you. It's just that you can't see. Right now there are Bluetooth, Wi-Fi, radio waves around you, but it's just that you can't see them. But if you could see them, they would not look like blue or red or yellow. It's just that our brain just doesn't know it because we have never experienced it or not even capable of experiencing it. So understand, it's like talking about the Vibgyor colors to a blind person. No matter how much you sit and explain to a blind person what a violet color or red or green or orange or magenta is, they will never understand. But same thing, you apply it for yourself. So you are also technically blind to all these colors. So no matter how much anybody, even God comes and explains to you, you will not be able to understand it. Only a person with higher abilities or some divine person will be able to see all these colors. Understand that. But they have a lot of applications and they can be detected and generated in different ways. And that is what is given in NCERT last few lines, like radio waves. Radio waves, very low frequency. What do you use radio waves for? You use it for Earth to satellite communication, controlling some remote objects. You want to control a spaceship or you want to control some drone. They are typically using radio waves. Your AM, FM radio stations, which you have in your car, stereo system, radio stations, they also use that. Ham radio, walkie-talkies, all these things use radio waves. They usually have an antenna in them and they have an antenna in which the electricity keeps changing back and forth and that produces changing, fluctuating electric fields which generates electromagnetic waves and acts like a transmitter. You can also receive those signals. Microwaves. Well, microwaves, the name comes from microwave oven again. You can see Actually, the microwave oven name comes from microwaves. So microwaves are used in microwave ovens. They are very short wavelengths, and the best part is they are used for speed guns. You must have seen some police person is standing on the side of the road with some object, and what is he doing? He's not firing anything. That is called as a speed gun, meaning it can detect how fast the vehicle is moving. So if you are over speeding, then you will get to know, the police person will get to know using that speed gun. That speed gun emits microwaves. It reflects from the vehicle and comes back. So it uses some it uses some electromagnetic phenomena, and it will basically be able to detect the speeds. The same microwaves are also used to detect the speed of a ball. You might have seen in cricket or tennis tournaments, they detect the speed of the ball. How are they able to detect it? Using microwave technology. Microwave technology, the wavelength is very much similar and frequency is very much similar to the sizes and the resonant frequency of water molecules. So resonance is a phenomena when the frequency matches, my frequency matching with your frequency, you will dance, you will be like, yes sir, I'm able to understand everything. Same way, water molecules frequency matches with the frequency of the microwave, they will love it. They will say, yes, I'm loving it, just like McDonald's, and they will be like dancing. Once they start dancing, they vibrate, they will have thermal energy. And once they have thermal energy means they will get heated up. So that's why inside a microwave oven, you will see the water molecules get excited due to resonant frequency and they get heated up, thereby cooking your food. But it does not affect the plastic or the ceramic because their frequencies are way different than the microwave frequencies. Alright, so that is what it is. Next, you have infrared. Infrared is basically, you know, they're everywhere around us. We humans also emit infrared waves. Yes, just that you can't see it. So that's why soldiers and during spy missions, they use infrared goggles, because if it is dark, you can't see anything, but we humans emit infrared. So if you have infrared vision night cameras, you can see the person in the dark. In fact, some of the animals hunt their predator using infrared rays. Example, snakes and some rodents, I think they see, even dogs, they can see infrared rays. That means they have more capability than humans. So they can see something beyond the visible spectrum. They can see slightly beyond the visible spectrum. Those rays which we are blind to, they are able to detect and sense them. Alright. But apart from that, infrared rays are also called as heat waves. And this is because the water molecules present in most materials absorb the infrared waves, and after absorption, their thermal motion increases, they heat up and the surroundings. Infrared lamps are also used in physical therapy and also plays a role in maintaining Earth's warmth and average temperature throughout the Earth using greenhouse effect. So greenhouse effect is related to infrared rays because infrared rays can be absorbed by water very easily. Yes, so they can also act like thermal waves, thereby heating up the water and thereby, you know, participating in the greenhouse effect of the Earth. Yep. Your TV remote, even your AC remote, my AC remote right now, it has something over here. It uses infrared rays to communicate with the sensor on that AC or even your TV remote. Visible rays is the ones which you see, your rainbow, your colors, your paintings, human color, trees, object, everything around us is sensed by visible rays and we can see it very, very easily. Okay. Oh, so they have given an example. Snakes can detect infrared waves and the visible ranges. In fact, many insects can also extend into ultraviolet. So I don't know whom to blame. Imagine if we were able to see infrared and ultraviolet, then we could see people in the dark. So even if the electricity goes, it will be okay. We can even be sensitive to ultraviolet then. But thankfully we are not. That's why we use ultraviolet rays. You might have seen ultraviolet rays are used to repel some insects. In some hotels and restaurants, they have some violetish thing. What is that? Those are basically bulbs which emit ultraviolet rays which attract those insects and they get cling to it, and when they come close, there is an electric shock which is given and those insects will die. So ultraviolet rays which are detected by many insects, that is the application of it. So many things. Ultraviolet rays is also dangerous for human beings if you are exposed for a long time. So there is an ozone layer above the earth which protects the harmful ultraviolet rays into reaching the earth. The ozone, O3 molecules, they absorb those ultraviolet rays. But if the ozone layer finishes, then we are doomed, because then we will be getting exposed to those ultraviolet rays. Yes. And yeah, that is what has been mentioned. Ultraviolet rays are damaging to our eyes. That's why welding applications, you will see they hold one glass. When they are welding, two metals have to be joined. Sparks come out at that welding machine. You cannot see those rays directly. You should not see those rays directly because they are harmful to your eyes. So that's why they use a welder's glass which absorbs those, ultraviolet rays. So all these applications, please read it properly, guys. I'm explaining all the interesting things over here so that when you read it, you will immediately relate. Yes, sir told me this. And in the exam also, these applications come. X-rays, they are very small in Armstrong region, Armstrong wavelength, and they are very energetic because of the low wavelength, high frequency. And these X-rays are used to detect fractures in some structures, fracture in bones, to detect crystal lattice structure of atoms, how that, you might have studied in solids, I don't know whether it's deleted now in chemistry, how that solids are formed. Is it body centered, face centered, those things. So what is the size of the crystal? All those things are being detected using X-rays. But X-rays for a long time can be damaging to your muscles and skin. So you should be aware. That's why they say you should not keep on taking X-rays just chumma for time pass. Gamma rays. Gamma rays are even more energetic, high frequency, very small wavelength. Gamma rays are usually, going to come out from your nuclear explosions, nuclear fusions, those kind of things. Usually it comes through radiation, radioactive materials like uranium, thorium, all this, plutonium. They emit radiation, and those radiations are in the gamma ray range. They are extremely energetic. That means they will immediately burn you, and if you expose yourself for a few minutes or sometimes even few seconds, depending on the amount of the radiation, you might even die by radiation poisoning. That's what happened in Chernobyl and so many other nuclear disaster events. Also, it can be sometimes useful wherein you want to destroy some unwanted cells, like treating cancer. So that's where gamma rays are used. Yes, gamma rays are used for even treating cancer. So their wavelengths, how they are produced, how they are detected, just remember this table. Very rarely, they have not asked till now, but in case they ask it, you should just have an idea of it.